Joe Sun from Team Da Joy Peak. Hey guys, hello YouTube. I'm gonna be reading a couple of textbooks out loud and hopefully they'll turn into audiobooks, so it's gonna be a long recording, so we'll see. I'll be using the Pomodoro effect, so let's begin. Oh yeah, they're engineering textbooks, so everything will be around engineering and electrical engineering. So more details in the comments down below. But yeah, I hope you find this useful. Honestly, it's for a self thing, but we'll see. We'll see. We'll see. Okay. The essence of engineering is the utilization of resources and laws of nature to benefit humanity. Engineering is an applied science in the sense that it is concerned with understanding scientific principles and applying them to achieve a designated goal. Mechanical engineering design is a major segment of engineering. It deals with the conception, design, development, refinement, and application of machines and mechanical apparatus of all kinds. For many students, mechanical engineering design is one of their first professional engineering courses, as distinguished from background courses in science and mathematics. Professional engineering is concerned with obtaining solutions to practical problems. These solutions must reflect an understanding of underlying sciences, but usually this understanding is not enough. Empirical knowledge and engineering judgment are also involved. For example, from developing highly useful electrical devices. Similarly, scientists do not completely understand combustion processes or metal fatigue. But mechanical engineers use the understanding available to develop highly useful combustion engines. As more scientific understanding becomes available, engineers are able to devise better solutions to practical problems. Moreover, the engineering process of solving problems often highlights areas particularly appropriate for more intensive scientific research. There is a strong analogy between the engineer and the physician. Neither is a scientist whose primary concern is with uncovering basic knowledge, but both use scientific knowledge supplemented by empirical information and professional judgment in solving immediate and pressing problems. Because of the professional nature of the subject, most problems in mechanical engineering design do not have a single right answer. Consider, for example, the problem of designing a household refrigerator. There is a nearly endless number of workable designs, none of which could be called an incorrect answer. But of the correct answers, there are obviously better than others because they reflect more sophisticated knowledge of the underlying technology, a more ingenious concept of basic design, a more effective and economical utilization of existing production technology, a more pleasing aesthetic appearance, and so on. It is precisely at this point, of course, that one finds the challenge and excitement of modern engineering. Engineers today are concerned with the design and development of products for a society different from any that existed previously, and they have more knowledge available to them than did engineers in the past. Hence, they are able to produce distinctly better solutions to meet today's needs. How much better depends on their ingenuity, imagination, depth of understanding of the need involved, and of technology that bears on the solutions, and so on. This book is primarily concerned with the design of specific components of machines or mechanical systems. Competence in this area is basic to consideration and synthesis of complete machines and systems in subsequent courses in professional practice. It will be seen that even in the design of a single bolt or spring, the engineer must use the best available. Hold up, I'm gonna time this actually. I'm gonna zoom this in for you guys. And I'm on timer. Clock. Pomodoro effect, you know? And time for like every 30 seconds? 30 minutes? Uh-oh. That's not good. Okay, let's try again. Stopwatch? So the Pomodoro technique, for every 25 minutes I take a 5-minute break. So let's start. Scientific understanding together with the empirical information, good judgment, and often a degree of ingenuity in order to produce the best product for today's society. The technical considerations of mechanical component design are largely centered around two main areas of concern: stress strain strength relationships involving the bulk of a solid member, and surface phenomena including friction, lubrication, wear, and environmental deterioration. Part 1 of the book is concerned with the fundamentals involved, and Part 2 with applications to specific machine components. These components chosen are widely used and will be somewhat familiar to the student. It is not feasible or desirable for the student to study the detailed design considerations associated with all machine elements. Hence, the emphasis in treating those selected here is on the methods and procedures used so the student will gain competence in applying these methods and procedures to mechanical components in general. When considering a complete machine, the engineer invariably finds the requirements and constraints of various components are interrelated. The design of an automotive engine valve spring, for example, depends on space available for the spring. This in turn represents a compromise with the space requirements for the valve ports, coolant passages, spark plug clearance, and so on. This situation adds a whole new dimension to the imagination and ingenuity required of engineers as they seek to determine an optimum design for combination of related components. This aspect of mechanical engineering design is illustrated by a case study at yleague.com/college/juvenile. In addition to the traditional technological and economic considerations fundamental to the design and development of mechanical components and systems, the modern engineer has become increasingly concerned with the broader considerations of safety, ecology, and overall quality of life. These topics are discussed briefly in the following sections. Safety considerations. Chapter 1.2. It is natural that in the past, engineers gave first consideration to the functional and economic aspects of new devices. After all, unless devices can be made to function usefully, they are of no further engineering interest. Furthermore, if a new device cannot be produced for a cost that is affordable by contemporary society, it is a waste of engineering time to pursue it further. But the engineers who have gone before us have succeeded in developing a multitude of products that do function usefully and that can be produced economically. Partly because of this, increasing engineering effort is now being devoted to broader considerations relating to the influence of engineered products on people and on the environment. Personnel safety is a consideration that engineers have always kept in mind, but now demands increasing emphasis. In comparison with such relatively straightforward computations as a stress and deflection, determination of safety is likely to be elusive and indefinite matter complicated by psychological and sociological factors. But this should only add to the appeal of the task for an engineer. It challenges him or her to assemble all pertinent facts and then to make good decisions reflecting understanding, imagination, ingenuity, and judgment. The important first step in developing engineering competence in the safety area is cultivating an awareness of its importance. Product safety is of great concern to legislators, attorneys, judges, jurors, insurance executives, and so forth. But none of these individuals can contribute directly to the safety of a product. They can only underscore the urgency of giving appropriate emphasis to safety in the engineering development of a product. It is the engineer who must carry out the development of safe products. Safety is inherently a relative matter, and value judgments must be made regarding trade-offs between safety, cost, weight, and so on. Some years ago, the first author was associated with a particularly safety-conscious company and was in the position of frequently admonishing the staff safety engineer to reduce further the inevitable hazards associated with the company's equipment. When pushed a little too far one day, the engineer responded, "Look, I have made this model foolproof, but I can never make it damn foolproof. If someone tries hard enough, he can hurt himself with this machine." The next day, this gentleman inadvertently proved his point when he accidentally dropped the new model prototype on his foot and broke a toe. But the point to be made here is that when society makes decisions relative to safety requirements, engineers should contribute important input. Chapter 1.2.1 Imagination and Ingenuity. Following awareness, the second main point of safety engineering is ingenuity. The engineer must be imaginative and ingenious enough to anticipate potentially hazardous situations relating to a product. The old maxim that anything that can happen probably will happen sooner or later is relevant. The following are 4 cases in point, all involving costly liability suits. 1. A large open area with a high ceiling was to be heated and cooled with 3 cubicle units, each suspended from the ceiling by long steel rods at 4 corners. The cubicles were being fitted to with heat exchangers, blowers, and filters by workers inside and on top of the enclosures. The flexibility of long support rods permitted the cubicles to swing back and forth, and the workers sometimes enjoyed getting their cubicles swinging with considerable amplitude. Fatigue, fatigue failure of a support rod caused the death of one worker, since large steam pipes, not yet installed at the time of the accident, prevented significant sway of the completed units, and the rods were designed with a safety factor of 17. Based on based on the static weight of the completed cubicles, no further thought was given to safety. No one was responsible for the design and installation of the units had reviewed the installation sequence with the imagination and ingenuity needed to foresee this hazard. A boy was seriously too. A boy was seriously injured by collision with a car when the brakes on his new bicycle failed to respond in an emergency. The cause was discovered to be interference between a fitting on the 3-speed shift mechanism and a sharp edge on the caliper brake handle. Both with the shift control mechanism and the brake handle were of unusual design. Both were safe within themselves and were safe when used in combination with a conventional design of the other member. But when these two unusual members were used together, it was easy for them to be mounted on the handlebar in such a position that the travel of the brake handle was limited, thereby preventing full application of the brake. Again, no one responsible for the overall design of the bicycle foresaw this hazardous situation. 3. A worker lost a hand in a 400-ton punch press despite wearing safety cuffs that were cam actuated to pull the hands out of the danger zone before the ram came down. The cause was a loosened set screw that permitted the cam to rotate with respect to its supporting shaft, thereby delaying hand retraction after the ram came down. This case illustrates the old adage that a chain is no stronger than its weakest link. Here, an otherwise very positive and strong safety device was nullified because of the inexcusably weak link of the set screw. A very little imagination and ingenuity on the part of the engineer responsible for this design would have brought this hazard to light before the unit was released for production. 4. A crawling infant lost the ends of 3 fingers as he attempted to climb up an exercycle, being ridden by an older sister. When placed in the bottom of the chain, the infant's hand was immediately drawn into the crank sprocket. In order to minimize cost, the exercycle was very properly designed to take advantage of many high production, low cost parts used on a standard bicycle. Unfortunately, however, the chain guard, which provides adequate protection for a bicycle, is totally inadequate for the exercycle. Was it too much to expect that the engineer responsible for this design would have enough imagination to foresee this hazard? Should he or she not have been sufficiently ingenious to devise an alternative guard design that would be economically and otherwise feasible? Should it be necessary for this kind of imagination and ingenuity to be forced upon the engineer by legislation devised and enacted by non engineers? Chapter 1.2.2 Techniques and Guidelines. Once the engineer is sufficiently aware of safety considerations and accepts this challenge to his or her imagination and ingenuity, there are certain techniques and guidelines that are often helpful. 6 of these are suggested in the following. Review the total life cycle of the product from initial production to final disposal, with an eye toward uncovering significant hazards. Ask yourself what kind of situations can reasonably develop during the various stages of manufacturing, transporting, storing, installing, using, servicing, and so on. Be sure the safety provisions represent a balanced approach. Do not accept a dollar penalty to eliminate one hazard and overlook a 20-cent possibility for eliminating an equal hazard. And like the punch press example just given, do not focus attention on how strong the wrist cuffs are while overlooking how weak the cam attachment is. Make safety an integral feature of the basic design wherever possible, rather than adding on safety devices after the basic design has been completed. An example of this was the development of an electric static hand-operated paint gun. Earlier, stationary mounted electrostatic paint guns had metal atomizing heads operating at 100,000 volts. A handgun version incorporating elaborate guards and shields was quickly recognized as impractical. Instead, a fundamentally new electric circuit design combined with a non-metallic head was developed so that even if the operator came in contact with the high voltage head, he or she would have received no shock. The voltage automatically dropped as the hand approached the head, and the head itself had a low enough capacitance to avoid significant discharge to the operator. 4. Use a fail-safe design where feasible. The philosophy here is that precaution is taken to avoid failure. But if failure does occur, the design is such that the product is still safe. That is, the failure will not be catastrophic. For example, the first commercial jet aircraft were the British Comets. Some of these experienced catastrophic failure when the fatigue cracks started in the outer aluminum skin at the corners of the windows, caused by alternately pressurizing the cabins at a high altitude and relieving the pressurizing stresses at ground level. Soon after the cracks were initiated, the fuselage skin ripped disastrously, somewhat like a tour rubber balloon. After the cause of the crashes was determined, subsequent commercial jet aircrafts incorporated the fail-safe feature of bonding the outer panels to the longitudinal and circumferential frame members of the fuselage. Thus, even if a crack does start, it can propagate only to the nearest bonded seam. The relatively short cracks in no way impair the safety of the aircraft. This particular failsafe feature can be illustrated by ripping an old shirt. Once the tear has been started, it is easily propagated to a seam, but it is extremely difficult to propagate the tear through the seam or tear stopper. Failsafe designs often incorporate redundant members so that if one load carrying member fails, a second member is able to assume the full load. This is sometimes known as the belt and suspenders design philosophy. In extreme cases, a safety pin may be employed as a third member. Check government and industry standards such as OSHA and ANSI, and the pertinent technical literature to be sure that legal requirements are complied with and that advantage is taken of the relevant safety experience of others. The OSHA regulations may be downloaded from the government website at osha.gov. A search for specific titles of ANSI standards can be conducted at ansi.org. For regional, national, foreign, and international standards and regulatory documents, see nssn.org. 6. Provide warnings of all significant hazards that remain after the design has been made as safe and as reasonably possible. Safe as reasonably possible. The engineers who develop the product are in the best position to identify these hazards. The warning should be designed to bring the information to the attention of the persons in jeopardy in the most positive manner feasible. Conspicuous warning signs attached permanently to the machine itself are usually best. There are OSHA and ANSI standards pertaining to warning signs. More complete warning information is often appropriately included in an instruction or operating manual that accompanies the machine. To apply these techniques and guidelines in an alternative procedure form, consider the following list from 9 bracket 1. Delineate the scope of product uses. 2. Identify the environments within which the product will be used. 3. Describe the user population. 4. Postulate all possible hazards, including estimates of probability of occurrence and seriousness of resulting harm. 5. Delineate alternative design features or production techniques, including warnings and instructions that can be expected to effectively mitigate or eliminate the hazards. 6. Evaluate such alternatives relative to the expected performance standards of the product, including the following: other hazards that may be introduced by the alternatives. B. Their effect on the subsequent usefulness of the product. C. Their effect on the ultimate cost of the product. D. A comparison to similar products. 7. Decide which features to include in the final design. The National Safety Council, NSC.org, publishes a hierarchy of design that sets guidelines for designing equipment that will minimize injuries. The order of design priority is bracket 10. 1. Design to eliminate hazards and minimize risk. From the very beginning, the top priority should be to eliminate hazards in the design process. 2. Incorporate safety devices. If hazards cannot be eliminated or the risk adequately reduced through design selection, the next step is to reduce the risk to an acceptable level. This can be achieved with the use of guarding or other safety devices. 3. Provide warning devices. In some cases, identified hazards cannot be eliminated or their risk reduced to an acceptable level through initial design decisions or through the incorporated safety devices. Warnings are a potential solution. 4. Develop and implement safe operating procedures and employee safety training programs. Safe operating procedures and training are essential in minimizing injuries. When it is impractical to eliminate hazards, to reduce their risk to an acceptable level through design selection, incorporating safety devices, or with warning devices. 5. Use personal protective equipment. When all other techniques cannot eliminate or control a hazard, employees should be given personal protective equipment to prevent injuries and illnesses. Chapter 1.2.3 Documentation of a product design. The documentation of a product design is costly yet necessary to support possible litigation. Such documentation has been categorized (9) as in the following table. Design documentation categories. Category: hazard and risk data. Description: historical field and / or laboratory testing, causation analyses. Category: design safety formulation. Description: fault tree failure modes, hazard analysis. Category: warning and instruction formulations, methodology for development and selection. Category: standards. Description: the use of in-house voluntary and mandated design or performance requirements. Category: quality assurance program, methodology for procedure selection and production records. Category: product performance, reporting procedures, compliant file, follow-up data, acquisition and analysis, recall, retrofit, instruction and warning modification. Category: decision making. Description: the how, who, and why of the process. By documenting a design during the process, a safer product is generally produced. Also, imagination and ingenuity can sometimes be stimulated by requiring documentation of a product design. Alright, I'm gonna take a break here. My god. What am I doing? It was fun though. I am learning, but alright, we're back. Safety engineering inherently includes important non-technical aspects that are related to the individuals involved. Engineers must be aware of these if their safety-related efforts are to be effective. 3 specific points within this category are suggested. Capabilities and oh my god, let me drink some water. Oh my god. Characteristics of individuals, both physiological and psychological. When the device is used or serviced, the strength, reach, and endurance requirements must be well within the physiological limitations of the personnel involved. The arrangement of instruments and controls and the nature of mental operating requirements must be compatible with psychological factors. Where the possibility of accident cannot be eliminated, the design should be geared into limiting personnel accident imposed loads to values, minimizing the severity of injury. 2. Communication. Engineers must communicate to others the rationale and operation of the safety provisions incorporated in their designs, and in many situations, they must involve themselves in selling, quote unquote, the proper use of these safety provisions. What good does it do, for example, to develop an effective motorcycle helmet if it's not used? Or to provide a punch press with safety switches for both hands if the operator blocks one of the switches closed in order to have a hand free for smoking? Unfortunately, even the most effective communication does not always guarantee intelligent use by the operator. This unresponsiveness may cause controversies such as that surrounding the requirement that airbags be installed in cars, because a significant segment of public cannot be persuaded to use seat belts voluntarily. Resolution of such controversies requires intelligent input from many quarters, one of which is certainly the engineering profession. 3. Cooperation. The controversy just mentioned illustrates the need for engineers to cooperate effectively with members of other disciplines, government, management, sales, service, legal, and so on, in order that joint safety directed efforts may prove effective. Chapter 1.3 Ecological Considerations. People inherently depend on their environment for air, water, food, and materials for clothing and shelter. In primitive society, human-made wastes were naturally recycled for repeated use. When open sewers and dumps were introduced, nature became unable to reclaim and recycle these wastes within normal time periods, thus interrupting natural ecological cycles. Traditional economic systems enable products to be mass-produced and sold at prices that often do not reflect the true cost to society in terms of resource consumption and ecological damage. Now that society is becoming more generally aware of this problem, legislative requirements and more realistic total cost provisions are having increasing impact upon engineering design. Certainly, it is not important that the best available engineering input go into societal decisions involving these matters. We can perhaps state the basic ecological objectives of mechanical engineering design rather simply. 1. To utilize materials so that they are economically recyclable within reasonable time periods without causing objectionable air, ground, and water pollution, and to minimize the rate of consumption of non-recycled energy sources such as fossil fuels, both to conserve these resources and to minimize thermal pollution. In some instances, the minimization of noise pollution is also a factor to be considered. As with safety considerations, ecological factors are much more difficult for the engineer to tie down than are such matters as stress and deflection. The following is a suggested list of points to be considered. 1. Consider all aspects of the basic design objective involved. To be sure that it is sound, for example, questions are raised about the overall merits of some major dam constructions. Are there ecological side effects that make it preferable to follow an alternative approach? Before undertaking the design of an expanded highway system or a specific mass transit system, the engineer must determine whether the best available knowledge and judgment indicate that the proposed project presents the best alternative. 2. After accepting the basic design objective, The next step is a review of the overall concepts to be embodied into the proposed design. For example, a modular concept may be appropriate with wherein specific components or modules most likely to wear out or become obsolete can be replaced with updated modules that are interchangeable with the originals. The motor and transmission assembly of domestic automatic washing machine might be an example for which this approach would be appropriate. Another example is the provision of replaceable exterior trim panels on major kitchen appliances that permit the exterior surfaces to be changed to match a new decorating scheme without replacing the entire appliance. 3. An important consideration is designing for recycling. At the outset of new design, it is becoming increasingly important that the engineer consider the full ecological cycle, including the disposal and reuse of the entire device and its components. Consider an automobile. Parts appropriate for reuse, either with or without rebuilding, should be made so that they can be easily removed from a quote-unquote junk car. Dismantling and sorting of parts by material should be made as easy and economical as possible. It is somewhat facetiously suggested that cars be made so that all fasteners break when dropping a junk car from, say, a height of 30 feet. Automatic devices would then sort the pieces by material for reprocessing. A more realistic proposal is that attaching the wiring harness so that it can be quickly ripped out in one piece for easy salvaging of the copper. In developing recycling procedures along these lines, it is obviously desirable that the cost to a company for recycling versus the cost for abandoning the old parts and using virgin materials reflect total real cost to society. No individual company could stay in business if it magnanimously oh my god magnanimously okay, give me a sec. How do you say this word? Jesus.
Magnanimously.
Magnanimously undertook a costly recycling program in order to conserve virgin materials and reduce processing pollution. If its competitors could utilize inexpensive new materials obtained at a price that did not reflect these costs. 4. Select materials with ecological factors in mind. Of importance, here are the known availability and nature of the required raw materials, processing, energy requirements, reprocessing, pollution problems, air, water, land, thermal, and noise, and recyclability. Ideally, all of these factors would be appropriately reflected within the same pricing structure. And this will more likely happen in the future than it has in the past. Another factor to be considered is the relative durability of alternative materials for use and a perishable part. For example, consider the great reduction in the number of razor blades required and in the number of scrap razor blades made by changing the material to stainless steels. But would it be better overall to devise a convenient and effective way to resharpen the blades rather than throwing them away? The engineer should also consider the compatibility of materials with respect to recycling. For example, zinc die castings deteriorate the quality of the scrap obtained when present junk cars are melted. Didn't know that. Okay, 5. Consider ecological factors when specifying processing. Important here are pollution of all kinds, energy consumption, and efficiency of material usage. For example, farming operations such as rolling and forging use less materials and generate less scrap than cutting operations. There may also be important differences in energy consumption. Packaging is an important area for resource conservation and pollution reduction. Reusable cartons and the use of recycled materials for packing are two areas receiving increasing attention. Perhaps the ultimate in ecologically desirable packaging is that commonly used ice cream container, the cone. The matter of protecting our environment is a deadly serious one. As the late Adlai Stevenson once said, we travel together, passengers on a little spaceship, dependent on its vulnerable supplies of air and soil, preserved from annihilation only by the care, the work, and I will say the love we give our fragile craft. Societal Considerations, Chapter 1.4. As the reader well knows, the solution of any engineering problem begins with its clear definition. Accordingly, let us define in the broadest terms the problem to be addressed when undertaking mechanical engineering design. The opening sentence in this chapter suggests a definition. The basic objective of any engineering design is to provide a machine or device that will benefit humanity. In order to apply this definition, it is necessary to think in more specific terms. Just how does an individual benefit humanity? What yardstick, meter stick, can be used to measure such benefits? The formulation of these precise definitions of problems, objectives, and devising of means for measuring results fall within the special province of the engineer. The writer has suggested 2. That basic objective of engineering design, as well as other human pursuits to improve the quality of life within our society, and that this might be measured in terms of a life quality index, LQI. This index, in some ways, similar to the familiar gross national product, but much broader. Judgments about proper composition of the LQI would, of course, vary somewhat in the many segments of society and also with time. Kind of reminds me of ESG. Okay. To illustrate the LQI concept, Table 1.1 lists some of the important factors most people would agree should be included. Perhaps we might arbitrarily assign a value of 100 to the factor deemed most important, with other factors being weighed accordingly. Each factor might then be multiplied by the same fraction so that the total would add up to 100. The list in the table admittedly is a very rough and oversimplified indication of the direction of thought that would be involved in arriving at an LQI for a given segment of society at a given time. But this kind of thinking must be done in order to provide the sound basis for judgment with respect to the fulfillment of the engineering mission of service to humanity. The professional contribution of engineers engaged in the broad area of engineering design and development plays a major role in determining the LQI of a population. Figure 1.1 depicts the societal relationships involving engineered products. A major segment of the population works within organizations whose function is to do one or more of the following: research, design, develop, manufacture, market, and service engineered products. The efforts of these people, together with the appropriate natural resources, go into production systems that yield useful products. Waste, materials, and experience. The experience is of two kinds: direct working experience of the individuals, which is hopefully constructive and satisfying, and two, empirical knowledge gained about the effectiveness of the overall system, with implications for its future improvement. Table 1.1. Preliminary list of factors constituting the life quality index. 1. Physical health. 2. Material well-being. 3. Safety. 4. Environment. 5. Cultural, educational. 6. Treatment of disadvantaged groups. 7. Equality of opportunity. 8. Personal freedom. 9. Population control. New products. Okay, here's the graph. New products go into human resources, work experience, and knowledge feedback also go into human resources. And then it goes to the production system, which goes back to the products, which goes back to the new products. It's like a loop. Experience goes to work experience and human resources. Okay, material resources go into production system, and waste goes into material resources. Okay, basic societal relationships involving engineered products. Okay. Man, I have a long way to go. Mechanical engineering design in broad perspective. Table 1.2. Maslow's hierarchy of needs: survival, security, social acceptance, status, self-fulfillment. The products made serve all people until discarded, when they constitute long and short-term recyclable material resources and possibly pollution. A valid LQI must take into account psychological factors. A book of this kind could only be the briefest introduction to this vast subject, but hopefully this will aid in stimulating the student towards a lifelong interest and concern with the fundamental area. We know that people exhibit an infinitely varying and often baffling set of characteristics, but we also know that there are certain inherent human characteristics that need to remain fixed for all individuals and presumably for all time. These have been expressed as proposed levels of human need by the late Abraham Maslow, a psychologist at Brandeis University. As an aid to memory, these are expressed in table 1.2 in terms of 5 keywords beginning with the letter S: survival, security, social acceptance, status, self-fulfillment. Cool. The first level, obviously, is the need for immediate survival: food, shelter, clothing, and rest, here and now. The second level involves security, ensuring one's safety and future survival. The third level is social acceptance. People need to belong and interact with a family, clan, or other group. They need love and acceptance. The fourth level is status or recognition, and a need not only to fit into social group, but also to earn the received peer respect and admiration. The highest level is self-fulfillment, growth towards one reaching one's fullest potential and achievement of the resulting inner satisfaction. At a given time, both people and nations operate on more than one of these levels, yet the levels define a general path or ladder of advancement that leads from primitive existence to a mature, rich quality of life. Historically, engineering effort has been directed primarily towards satisfying needs 1 and 2, More recently, an increased percentage of production systems have been designed to provide society with products going beyond the basic survival and security needs, presumably contributing to satisfying the legitimate higher needs of the consumer. As for the workers, it is interesting to note that job enlargement and job enrichment programs are directed towards the workers' higher needs. 3, 4, and 5. A basic social acceptance, status, and self-fulfillment. 5. A basic ingredient of human society is change. Engineers must seek to understand not only the needs of society today, but also the direction and rapidity of societal changes that are occurring. Moreover, we must seek to understand the influence of technology and of mechanical products and associated production systems in particular on these changes. Perhaps the engineering profession's most important objective is to make its input to society such that it promotes changes in the direction of increasing the life quality index. Chapter 1.5 Overall Design and Considerations. Most engineering designs involve a multitude of considerations, and it is a challenge to the engineer to recognize all of them in proper proportion. Although no simple checklist given here can be adequate or complete, it might be helpful to list in some organized fashion the major categories involved. See Table 1.3. Table 1.3. Major categories and design considerations. Traditional considerations. Materials. Geometry. Operating conditions. Cost availability. Producibility, component life. Modern considerations: safety, ecology, quality of life. Miscellaneous considerations: reliability and maintainability, ergonomics and aesthetics, assembly and disassembly. Analysis. Traditional considerations for the bulk of body of the component include strength, deflection of weight, and size and shape. Traditional considerations for the surfaces of the component are wear, lubrication, corrosion, frictional forces, and frictional heat generated. Often, various design considerations are seemingly incompatible with until the engineer devises a sufficiently imaginative and ingenious solution. The design of the lift truck pictured in Figure 1.2 provides here the example. Here, the objective of achieving a desired aesthetic appearance was seemingly incompatible with cost limitations. Matched metal forming dies were too costly, and expensive tooling resulted in unattractive mismatches for mating parts. The solution here was to work deliberate mismatches into the design and eliminate the need for precision fitting. The mismatches were used to give the truck a rugged look. The gap under the hood, for example, creates a strong horizontal line while disguising the fit ups of the several frame and fender weldments. It also provides a handhold for lifting the hood. Another gap, not shown, makes the instrument pod appear to float from a steel pylon, again disguising a large tolerance. The large hood simplifies maintenance by providing wide open access to the engine. By serving also the seat support, it further reduces cost while adding to the clean, uncluttered appearance. Interesting. Okay. I always wonder why it only has like one attachment down here. It's gonna be a while. Chapter 1.6 System of Units Squared. Because of politics and the global economy, engineers seem destined to suffer the inconvenience of having to deal with different systems of units. 3 types are discussed in this book. Appendix A1 lists the units associated with these systems, conversion factors relating to them, and their standard abbreviations. The units of the physical quantities used in engineering calculations are of major importance. A unit is a specified amount of physical quantity by which, through comparison, another quantity of the same kind is measured. For example, inches, feet, miles, centimeters, meters, and kilometers are all units of length. Seconds, minutes, and hours are units of time. Because physical quantities are related by laws and definitions, a small number of physical quantities are called primary dimensions are sufficient to conceive of and measure all the others. Secondary dimensions are those quantities measured in terms of primary dimensions. For example, if mass, length, and time are primary dimensions, area, density, and velocity would be secondary dimensions. Equations from physics and engineering that relate physical quantities are dimensionally homogeneous. Dimensionally homogeneous equations must have the same dimensions for each term. Newton's second law, F equals ma, relates to dimensions force, mass, length, and time. If the length and time are primary dimensions, Newton's second law, being dimensionally homogeneous, requires the force and mass cannot be primary dimensions without introducing a constant of proportionality that has dimensions in units. Primary dimensions in all systems of dimensions in common use are length and time. Force is selected as a primary dimension in some systems. Mass is taken as a primary dimension in others. For application in mechanics, we have 3 basic systems of dimensions. 1. Force, mass, length, time. 2. Force, length, time. 3. Mass, length, time. It's also 1. Length, time, and both force and mass are selected as primary dimensions in this system in Newton's second law, F equals ma divided by g. Gravity. Oh, no. The constant of proportionality, g, is not dimensionless. For Newton's law to be dimensionally homogeneous, the dimensions of proportionality must be m, mass, L, length, divided by force and time, squared. In System 2, mass is a secondary dimension, and Newton's second law is a constant proportionality and is dimensionless. In System 3, force is a secondary dimension, and in Newton's second law, the constant of proportionality is again dimensionless. The units of measure selected for each primary physical quantity determine the numerical value of the constants of proportionality. In this text, we will use the SI British Gravitational and English Engineering Systems of Units. The base units employed for these are listed in Table 1.4 and discussed in the following paragraphs. Newton's second law is written as F equals ma for the SI and British systems, and F equals ma divided by g for the English engineering system. For each system, the constant of proportionality in Newton's second law is given by figure 1.3, which also compares three systems of units. In both the SI and British systems, the constant of proportionality is dimensionless and has the value of unity. The gravitational force on an object of mass m is given by W equals mg for the SI and British systems, and as W equals mg divided by g. The constant. The difference here is it's the constant between the British system and the English engineering system. Here's the chart. Feels kind of pointless to read this, so I'm gonna just put it on the screen and wait. Oh my god. Okay, how far are we? I'm gonna take a pause. Okay, be right back. I'll be back. Chapter 1.7 Methodology for solving machine component problems. An essential method of attack for a machine component problems is to formulate them precisely and to present their solutions accurately. Formulating the problem requires consideration of the physical situation and the matching mathematical situation. The mathematical representation of a physical situation is an ideal description or model that approximates but never matches the actual physical problem. The first step in solving machine component problems is to define the problem. The next steps are to define the structure, identify the interactions with the surroundings, record your choices and decisions, and draw the relevant diagrams. Attention then turns into analyzing the problem, making appropriate assumptions by using pertinent physical laws, relationships, and rules that parametrically relate to the geometry and behavior of the component or system. The last step is to check the reasonableness of the result and, when appropriate, comment about the solution. Most analyses use directly or indirectly statics and dynamics, mechanics of materials, formulas, tables, diagrams, charts, the conversion of mass principle, the conversion of energy principle. In addition, engineers need to know how physical characteristics of materials of which components are fabricated relate to one another. Newton's first and second laws of motion, as well as the third law and relations such as the convective heat transfer equations and Fourier's conduction model, may also play a part. Assumptions will usually be necessary to simplify the problem and to make certain equations and relationships are appropriate and valid. The last step involves checking the reasonableness of the results. A major goal of this textbook is to help students learn how to solve engineering problems that involve mechanical components. To this end, numerous solved examples and end-of-chapter problems are provided. It is extremely important to study the examples and solve the problems. For mastery of fundamentals comes only through practice. To maximize the results and rewards in solving problems, it is necessary to develop a systematic approach. We recommend that problem solutions be organized using the following 7 steps, which are employed in the solved examples of this text. Problems should be started by recording what is known and completed by commenting on what was learned. Solution known. State briefly what is known. This requires that you read the problem carefully and understand what is given. Find. State concisely what is to be determined. Schematic and given data. Sketch the component or system to be considered. Decide whether a free body diagram is appropriate for the analysis. Label the component or system diagram with relevant information from the problem statement. Record all material properties and other parameters that you are given or anticipate may be required for subsequent calculations. If appropriate, sketch diagrams that locate critical points and indicate the possible mode of failure. The importance of good sketches of the system and free body diagrams cannot be overemphasized. They are often instrumental in enabling you to think clearly about the problem. Record your choices and selections. Design problems that will require you to make subjective decisions. Design decisions will involve selection of parameters such as geometric variables and types of materials. Decisions are individual choices. To form a record of how you model the problem, list all simplifying assumptions, idealizations made to reduce it in one that is manageable. Sometimes this information could also be noted on the sketches. In general, once a design is complete, assumptions are still beliefs where decisions are true. Assumptions are theories about reality. Using your decisions, assumptions, and idealizations, apply the appropriate equations and relationships to determine the unknowns. It is advisable to work with equations as long as possible before substituting in numerical data. Consider what additional data may be required. Identify the table, charts, or relationships that provide the required value. Additional sketches may be helpful at this point to clarify the problem. When all equations and data are in hand, substitute numerical values into the equations. Carefully check that a consistent and appropriate set of units is being employed to ensure dimensionally dimensional homogeneity. Then perform the needed calculations. Finally, consider whether the magnitudes of numerical values seem reasonable and the algebraic signs associated with the numerical values are correct. Comments. When appropriate, discuss your results briefly. Comment on what was learned. Identify key aspects of the solution. Discuss how better results might be obtained by making different design decisions, relaxing certain assumptions, and so on. A mathematical or an engineering model forms a record of how you represent the physical system or problem, wherein simplifying assumptions and idealizations are listed to reduce the problem to a tractable form. Referring to methodology for solving machine component problems, the model is generally composed of schematic with given data, decisions, and assumptions. Once the problem has been modeled, analysis follows. Although iteration in design problems is common, approximations will be required for mathematical models of physical systems. The degree of accuracy required and the information desired determine the degree of approximation. For example, the weight of a component can usually be neglected if the loads on the component are many times greater than the component's total weight. The ability to make the appropriate assumptions in formulating and solving a machine component problem is a requisite engineering skill. As a particular solution evolves, you may have to return to an earlier step and revise it in light of a better understanding of the problem. For example, It might be necessary to add or delete an assumption, modify a decision, revise a sketch, or seek additional information about the properties of a material. A problem solution format used in this text is intended to guide your thinking, not substitute for it. Accordingly, you are cautioned to avoid the rote application of these 7 steps, for this alone would provide few benefits. In some of earlier sample problems and end of chapter problems, the solution format may seem unnecessary or unwieldy, or unwieldy. However, as the problems become more complicated, you will see that it reduces errors, saves time, and provides a deeper understanding of the problem at hand. Chapter 1.8 Work and Energy. All mechanical apparatus involves load and motion, which in combination represent work or energy. Thus, it is appropriate to review these basic concepts. The work done by force F acting on a point on a component as the point moves from an initial point S1 to final point S2 is W equals integral S1 S2 F times ds, where the expression for work has been written in terms of scalar product of the force vector F and the displacement vector ds. To evaluate the integral, we need to know how the force varies with the displacement. The value W depends on the details of the interaction taking place between the component and the surroundings during a process. The limits of integral mean from position 1 to position 2 and cannot be interpreted at the values of work at 1 and 2. The notions of work at 1 or 2 has no meaning, so the integral should never be indicated as W2 minus W1. Figure 1.4 shows a wheel being turned by the application of tangential force F acting at radius r. Let the wheel rotate through q revolutions. Then the work done, W, is given by W equals F parentheses 2 pi r. Q equals Fs, where S is the distance through which the force F is applied. Suppose that the wheel is turned through an angle beta by applying a torque T equal to the product of F times R. Then the work done, W, is given by W equals F times R beta equals T beta. The work done by the force or torque can be considered as transfer of energy to the component, whereas it is stored as gravitational, potential energy, kinetic energy, or internal energy, or both or all 3. It may be dissipated as heat energy. The total amount of energy is conserved in all transfer. Work has units of force times distance. The units of kinetic energy, potential energy, and internal energy are the same as that for work. In SI, the work unit is Newton times meter, called the joule. Commonly used English or British units for work and energy are the foot-pound force, foot times pounds, in the British thermal unit. Camshaft torque requirement. Figure 1.5a shows that a rotating cam. Sample problems. I'm going to skip the sample problems because we're not solving problems here, we're rating. These are just equations that we can probably skip. Engine output power versus engine speed. Typical 350 inches V8 engine. Let's pause at this. This is pretty cool. Damn. Specific fuel consumption of engine. I don't get it. Alright, bro, what? Um, engine output power? Cool. That's a lot of like horsepower and RPMs and a lot of curves. Um, moving on. More problems, more problems, more problems. Load analysis 2. Chapter 2.1 Introduction. This book is concerned with the design and analysis of machine and structural components. Since these are load-carrying members, and analysis of loads is of fundamental importance. A sophisticated stress or deflection analysis is of little value if it is based on incorrect loads. A mechanical component cannot be satisfactory unless its design is based on realistic operating loads. Sometimes the service or operating loads can be readily determined, as are those on some engines, compressors, and electric generators that operate at known torques and speeds. Often the loads are difficult to determine, as are those on automotive chassis components, which depend on road surface and driving practices, or on the structure of an airplane, which depends on air turbulence and pilot decisions. Sometimes experimental methods are used to obtain a statistical definition of applied loads. In other instances, engineers use records of service failures together with analysis of strength in order to infer reasonable estimates of loads encountered in a service. The determination of appropriate loads is often a difficult and challenging initial step in the design of a machine or a structural component. Chapter 2.2 Equilibrium equations and free body diagrams. Okay, summation F equals 0 and summation M equals 0. For a non-accelerating body, these equations can be expressed as, okay, for an accelerating body, these can be expressed as summation F equals MA and summation M equals L alpha, I alpha. I alpha. These equations apply with respect to each of the three mutually perpendicular axes through, although in many problems forces and moments are present with respect to only one or two of these axes. Is more problems. Okay. Okay, let's read one of the problems. Figure 2.3 shows an exploded drawing of the engine, transmission, and propeller shaft in a car. In figures 2.1, 2.2, the engine delivers torque T to the transmission, and the transmission speed ratio is R. Determine the loads exclusive of gravity acting on these three members. Figure 2.3 shows an exploded drawing of the engine, transmission, and propeller shaft. Equilibrium of moments about the x-axis for engine, transmission, and propeller shaft of a front engine. So I'm guessing that is the engine, transmission, and propeller shaft. T equals torque. The engine is supported at 2 points as shown. Okay, 2 points. The weight of the components are neglected. Transmission frictions losses are neglected. Consider the transmission. Consider first the transmission. This member receives torque T from the engine and delivers RT to the propeller shaft. The propeller shaft applies equal and opposite reaction to torque RT to the transmission as shown. For equilibrium, torque RT minus T must be applied to the transmission housing by the engine structure to which it is attached. Beam loading refers to the lateral loading of members that are relatively long in comparison with their cross-sectional dimensions. Torsion or axial loading or both may or may not be involved as well. By way of review, two cases are shown in 2.10. Note that each incorporates three basic diagrams: external loads, internal transverse shear forces, and internal bending moments. All expressions for magnitudes are the result of calculations the reader is advised to verify as review exercise. Cool. These are pretty cool problems. I guess this is to familiarize yourself with all these gadgets. A bell crank. Free body diagrams. Bell crank. Finger beam loading. A shaft of a uniform diameter. I'm guessing that's like a car shaft. A yoke nut connection, and this is a yoke. Okay, these are like on tankers and stuff. Springs. A triple riveted butt joint of specified geometry is loaded in tension. What is a butt joint? Butt joint. Oh. No internet. Haha. A lot of problems. A lot of problems. Physics problems. I don't know if these are design problems, but guess you really need to know the free body in equilibrium. Cool. Okay, chapter 3.1. The selection of materials and processes used in fabrication are integral parts of the design in any machine component. Strength and rigidity are traditionally key factors considered when selection of a material. Equally important are the relative reliability and durability of that part when made from alternative materials. Okay, pause. So first you think about like the safety, the ecological and LRQ, life quality of your item that might be affected. Then you think about like the design of the safety design of the product, of the mechanical machine components, and then you think about the ways that people might mess it up, and then you think about the equilibrium forces, and now you think about the materials, which is interesting. So you think about the design first, and then you select the materials. Okay. Equally important are the relative reliability and durability of the part when made from alternative materials. When the component is expected to operate at extreme temperatures, this must be considered carefully when selecting the material. In recent years, choices of materials have been increasingly influenced by recyclability, energy requirement, and environmental pollution. Cost, and so you revisit the idea. Cost and availability are also vitally important. The cost to be considered is the total cost of the fabricated part, including labor and overhead, as well as the material itself. The relative cost and availability of various materials vary with time, and the result that the engineer is frequently called upon to evaluate alternative materials in light of changing market conditions. In summary, the best material for a particular application is the one that provides the best value, defined as the ratio between overall performance and total cost. It is assumed that the reader has a previous background in the fundamentals of engineering materials. Moreover, it is acknowledged that the practicing engineer is faced with a career-long challenge to remain abreast of new materials developments as they apply to the products with which he or she is concerned. Fitting in between these two phases of engineering materials study, this chapter attempts to summarize some of the relevant basic information and emphasize the increasing importance of rational approach to use empirical materials properties test data. The useful life of the machine and structural components ends with fatigue failure or surface deterioration. Further information on the resistance of various materials to these modes of failure is included in chapters 8 and 9 respectively. Information concerning properties of materials is given in Appendix C. Appendix C-1 gives physical constants for a variety of engineering materials. Mechanical properties are given in subsequent tables and graphs. Appendix F introduces MIL HDBK 5J, a military handbook that presents extensive collection of properties for metals used for design of aircraft structure, including steel, aluminum, titanium, and others. This document is easily obtainable online. It is extensive, totaling over 1,700 pages. Appendix F also presents equations and relationships that are important in the proper use of the handbook. Okay, so there's a lot of books on material strength and screws and everything else. Okay. A lot of handbooks. Wow. Okay. The basic engineering test of material strength is rigidity is the standard tensile test from which stress strain curves are shown in figure 3 are obtained. The stresses and the strains plotted are the nominal or so-called engineering values defined as sigma equals P divided by A, where P is the load and A is the original unloaded cross-sectional area, and E equals delta L divided by L0, where Delta L is the change in length caused by the load, and L0 is the original unloaded length. An important notation convention will be observed throughout this book. The Greek letter sigma denotes normal stress, which is a function of the applied loads S. Designated strength properties of the materials, for example, figure 3.1 that shows that even with sigma 39 ksi, the material begins to yield, hence Sy equals 39 ksi. Similarly, the greatest ultimate load that the test specimen can withstand corresponds to the engineering stress of 66 ksi, hence SU 66 ksi, where S is used for all strength values, including those for torsion or shear. The letter sigma is used for normal stresses only, that is, stresses caused by tensile, compressive, or bending loads. Shear stresses caused by torsional or transverse shear loads are designated by the Greek letter T. Cool. Returning to figure 3.1, several other mechanical properties are indicated in the stress and strain curve. Point A represents the elastic limit SE. It is the highest stress the material can withstand and still return exactly to its original length when unloaded. When loaded beyond point A, the material exhibits a partially plastic response. For most engineering materials, point A also approximates the proportional unit, defined as a stress where the stress-strain curve first deviates from a straight line. Below the proportional limit, Hooke's law applies. The constant of proportionality between stress and strain is the modulus of elasticity, or Young's modulus E, and for some materials. A slight deviation from linearity occurs between the origin and a point such as A, which the deviation become more apparent. Such a material has no proportion limit, nor is modulus of elasticity definitely defined. The computed value depends on the portion of the curve used for measuring the slope. Point B in figure 3.1 represents the yield strength Sy. It is value of stress at which significant plastic yielding first occurs. In some ductile materials, notably soft steel, marked yielding occurs suddenly at clearly defined value of stress. In other materials, the onset of appreciable yielding occurs gradually, and the yield strength for these materials is determined by using the offset method. This is illustrated in figure 3.1. It shows a line offset an arbitrary amount of 0.2% strain drawn parallel to the straight line portion of the original stress strain diagram. Point B is the yield point of the material at 0.2% offset. If the load is removed after yielding to point B, the specimen exhibits a 0.2% permanent elongation. Yield strength corresponding to a specified offset is standard laboratory determination, whereas elastic limit and proportional limit are not. Yield strength corresponding to a specified offset is a standard laboratory determination, whereas elastic limit and proportional limit or not. Yield strength. Other materials, the onset of appreciable yielding and the yield strength of these materials is determined. The offset method. Oh, okay. Implications of the engineering stress strain curve. Problems. Whenever a material is elongated too many times, its maximal elastic strain, the calculated engineering stress becomes somewhat fictitious because it is based on an area significantly different than that which actually exists. In such cases, this limitation can be avoided by computing the true stress. Man, that's a lot of words, bro. Penetration hardness tests provide a convenient and non-destructive means of estimating the strength properties of materials. Basically, penetration hardness testers measure the resistance to permanent deformation of a material when subjected to particular combinations of triaxial compressive stress and steep stress gradient. Use of handbook data for material strength properties. Ideally, an engineer would always base strength calculations on actual test data for the exact material used in the part involved. This would require the use of test specimens that correspond to the material in the fabricative part, not only in chemical composition, but also in all details of mechanical and thermal history. Because data from such specimens are seldom available, the standard test data reported in handbooks and other sources, Appendix C of this book, is frequently used. Okay. Machinability, Chapter 3.8. The cost of producing a machine part is obviously influenced by the cost of the material and the ease of which it can be machined. Empirically determined ratings of machinability are published for various materials. Although often useful, these data are sometimes unreliable and even contradictory. In an effort to relate machinability to material parameters on a rational basis, Daxko showed that machinability is a secondary material property that is a function of three primary material physical properties, where V, cutting speed, K equals thermal conductivity, HB equals Brinell's hardness number, and AR is the area reduction at fracture. The value of K is the same for all metals. The machinability of metal is essentially a function of hardness and ductility. Cast iron. Cast iron is a 4-element alloy containing iron, carbon, silicon, and manganese. Additional alloying elements are sometimes added. The physical properties of an iron casting are strongly influenced by the cooling rate during solidification. This in turn depends on the size and shape of casting and on details of foundry practice. Because of this, cast iron is usually specified by its mechanical properties than by chemical analysis. The distinctive properties of cast iron result largely from its carbon content. The high carbon content makes molten iron very fluid so that it can be poured into intricate shapes. The precipitation of carbon during solidification counteracts normal shrinkage to give sound sections. The presence of graphite in metal provides excellent machinability even at wear resistance hardness levels. Damps vibrations and aids boundary lubrication at wearing surfaces. When chilled, that is, when the heat is removed rapidly from the surface during solidification, virtually all the carbon near the surface remains combined as iron carbides, giving an extremely hard wear resistant surface. Mechanical properties of several cast irons are given in Appendix C3. That is so cool. Okay. Gray iron. The appearance of gray iron. Okay, I'm gonna take a break. Jeez. I'll be back. Gray iron. The appearance of gray iron comes from the carbon that is precipitated in the form of graphite flakes. Even the softer grades have good wear resistance. Increased hardness are obtainable by using special foundry techniques, heat treatment, or additional alloying elements. Because the graphite flakes markedly weaken cast iron in tension, the compressive strength is 3 to 5 times as high. Advantage is often taken of the strength differential, such as incorporating ribs on the compression side of a member loaded in bending. Typical applications of gray iron include gasoline and diesel engine blocks, machine bases, and frames, gears, flywheels, and brake discs, and drums. Ductile iron. Ductile iron is alloyed with magnesium, which causes the excess carbon to precipitate in the form of small spheres or nodules. These nodules disrupt the structure less than do the graphite flakes of gray iron, thereby giving substantial ductility along with improvised tensile strength, stiffness, and impact resistance. Ductile iron is specified by 3 numbers as 60, 40, 18, which denote tensile strength 60 ksi, yield strength 40 ksi, and elongation 18%. Typical applications include engine crankshafts, heavy-duty gears, and hardware items such as automobile door hinges. White iron. White iron is produced in outer portions of gray and ductile iron castings by chilling selected surfaces of the mold, thereby denying time for carbon precipitation. The resulting structure is extremely hard, wear resistant, and brittle. Typical applications are found in ball mills, extrusion dies, cement mixer liners, railroad brake shoes, rolling mill rolls, crushers, and pulverizers. Malleable iron. Typical uses are for heavy-duty parts having bearing surfaces, which are needed in trucks, railroad equipment, construction machinery, and farm equipment. Chapter 3.10 Steel. Steel is the most extensively used material for machine components. By suitably varying the composition, thermal treatment, and mechanical treatment, manufacturers can obtain a tremendous range of mechanical properties. Three basic relationships are fundamental to the appropriate selection of steel composition. All steels have essentially the same moduli of elasticity. Thus, if rigidity is the critical requirement of the part, all steels perform equally and at the least costly should be selected. Carbon content, almost done, determines the maximum hardness that can be developed in steel. Maximum potential hardness increases with carbon content up to about 0.7%. This means that relatively small, regularly shaped parts can be heat treated to give essentially the same hardness and strength with plain carbon steel as with more costly alloy steels. Alloying elements, manganese, molybdenum, chromium, nickel, and others improve the ease with which steel can be hardened. Thus, the potential hardness and strength, which is controlled by carbon content, can be realized with less drastic heat treatments when these alloying elements are used. This means that with an alloy steel, parts with large sections can achieve higher hardness in the center or core of the section, and irregularly shaped parts subject to warpage during a drastic quench can achieve the desired hardness from a more moderate heat treatment. Mechanical properties of a few more commonly used steels are given in appendixes C4 through C8. Plain carbon steels contain only carbon as a significant alloying element. Low carbon steels have less than 0.3% carbon. Medium carbon steels have 0.3 to 0.5%, and high carbon steels have above 0.5%. Appendixes C4b gives the typical uses for steels having various levels of carbon content. Alloying steels. As already indicated, the basic purpose of adding alloying elements to steel is to increase hardenability. Hardenability is commonly measured by the Jominy and quench test. Parentheses ASTM, abbreviated A-255, and abbreviation SAEJ406B, originated by the late Walter Jominy of the Chrysler Corporation. In this test, a 1-inch diameter by 4-inch long bar is suspended, heated above its critical temperature, and then the bottom end is quenched with water while the top end air cools. Hardness is then measured at 1 16th increments from the quenched end. The distance to which the hardening action extends is a measure of hardenability imparted by alloying elements. Table 3.1 represents the result of a study by Datsko of the relative effectiveness of various alloying elements in imparting hardening ability to steel. The elements are listed in order of decreasing effectiveness. The equations give a relatively hardenability factor F as a function of the concentration of the element used. For example, manganese is the second most effective element, and the equation is valid for concentrations of up to 1.2%. If 1% of manganese is used, the hardenability factor is 4.46. Similarly, a 2% concentration of chromium is a little more effective, giving a factor of 5.36. Table 3.1 is not complete. A notable omission being vanadium, and alloying elements may also have significant secondary influences. Nevertheless, the equations of Table 3.1 provide a useful guide to the selection of the most economical means of obtaining a required level of hardenability. Most alloy steels can be classified as either through hardening or carburizing with a U. The latter being used where a tough core and a relatively shallow hard surface layer are desired. Nitriding and other surface hardening processes are also used. HSLA steels, high strength, low alloy steels, were first developed around the 1940s as a class of relatively low cost steels, providing much of the advantage of more costly regular alloy steels. In many applications, their greater strength compared to the plain carbon steel permits a weight reduction with little, if any, increase of the total cost of the part. In recent years, the use of HSLA steels in automobiles has been substantial. Picture of HSLA steel. Picture of N-quenching and method of hardness testing, and N-quench hardenability specimen. Okay. Case hardening steels. Case hardening is a hardening of only the surface material. It is usually accomplished by carburizing, cyaniding, nitriding, induction hardening, or flame hardening. Carburizing introduces additional carbon into the surface of an otherwise low carbon steel and then heat treats it to give a high surface hardness. Some specific materials and hardness are listed in Appendix C7. Cyaniding is a similar process that adds nitrogen as well as carbon to the surfaces of low and medium carbon steels. Nitriding adds nitrogen to an already machined and heat-treated part. The temperature of the process is 1,000 Fahrenheit or less, or 538 Celsius. And no quenching is involved. This feature eliminates the possible distortion problems. For maximum case hardness, special nitra-alloy steels containing aluminum as an alloy are often used. Medium carbon alloy steels are also nitrided. Induction hardening and flame hardening heat only the surfaces of parts made of medium carbon and alloy steels, then quenching and tempering. Stainless steels. Stainless steels contain, by definition, a minimum of 10.5 chromium. Wrought stainless steels are austenitic, ferritic, martensitic, or precipitation hardening. Mechanical properties of some wrought stainless steels are given in Appendix C8. Cast stainless steels are usually classed as heat-resistant or corrosion-resistant. Iron-based superalloys. Iron-based superalloys are primarily used for elevated temperature applications, such as in turbines. Properties of typical iron-based superalloys listed in Appendix C9. Some authorities consider only austenitic materials to be true superalloys. In general, they are used at temperatures above 1,000 Fahrenheit, and the martensitic materials are used at lower temperatures. Significant properties of superalloys include at high temperatures, strength and resistance to creep, oxidation, corrosion, and wear. Typical uses are for parts, including bolts of gas turbines, jet engines, heat exchangers, and furnaces. Non-ferrous alloys. Aluminum alloys are of such. Literally, hundreds of aluminum alloys are available in both raw and cast forms. Properties of the few more common ones are listed in C10 and C11. The chemical composition of aluminium alloys is designated by 4 digits for raw forms, by 3 digits for cast alloys. Thermal treatment, mechanical treatment, or both are indicated by a temper designation that follows the alloy identification number. Temper designations are given in C12. The heat treatment of aluminum alloys to increase hardness and strength is quite different from the heat treatment of steel. Aluminum alloys are first held at elevated temperature long enough to bring the hardening constituents such as Cu, magnesium, manganese, silicon, nitrogen into solution, then quenched, and finally age hardened. The latter causes some of the hardening elements to precipitate throughout the structure. Some alloys precipitate at room temperature, others require an elevated temperature. Artificial aging. Aluminum is a readily castable metal serving a host of useful applications. Casting problems do exist. Shrinkage during casting is relatively large, and there is no mechanism analogous to the beneficial carbon precipitation in cast iron to counteract shrinkage. Hot shortness and gas absorption can be problems unless details of appropriate foundry practice are specified and controlled. Copper alloys include a variety of brasses, alloys made principally of copper and zinc, and bronzes, alloys made principally of copper and tin. As a class, copper alloys have a good electrical conductivity, thermal conductivity, and resistance to corrosion, but relatively low ratios of strength to weight. They can be hot or cold worked, but they strain harden the process. Ductility can be restored by annealing or by heat associated with welding or brazing. Specific desired properties such as greater strength, resistance to heat softening, and machinability can often be markedly improved by adding small amounts of additional alloying agents. Properties of several common copper alloys are given in C13. Magnesium alloys are the lightest engineering materials. They are designated by a system established by the American Society of Testing and Materials, ASTM abbreviation, which covers both chemical composition and tempers. The designation begins with 2 letters representing the alloying elements of the greatest and second greatest concentration. The letter designations are A. Aluminum, E. Rare earths, H. Thorium, K. Zirconium, L. Lithium, M. Manganese, Q. Silver, S. Silicon, Z. Zinc. Next are 2 digits that represent the respective percentages of these 2 elements, routed off to whole numbers. Following these digits is a serial letter that indicates some variation in the composition or minor alloying constituents or impurities. The temperature designations are at the end are identical with those used in aluminum. For example, alloy AZ31BH24 contains 3% aluminum, the 1% zinc, and is strain hardened. Mechanical properties of few common magnesium alloys are given in Appendix C14. Nickel alloys, including nickel-based superalloys. Nickel alloys are used in a variety of structural applications that usually require specific corrosion resistance and strength and toughness at temperature extremes as great as 2000 Fahrenheit and 400 Fahrenheit. Typical physical properties are given in C15. The nickel and duranickel alloys contain over 94% nickel. Mono represents a series of nickel copper alloys based on the mutual solubility of the two elements in all proportions. They are strong and tough at sub-zero temperatures and especially resistant to stress corrosion cracking. Hastel alloy designates a series of nickel mono and nickel monochromium superalloys. Several Hastel alloys resist oxidation and maintain the useful strength and creep properties in range 2000 Fahrenheit. The Inconel, Incolloy Rene, and Udiment alloys listed in C15 are nickel chromium and nickel chromium alloys. Fe alloys. I don't know what Fe is. Okay. Titanium alloys. Titanium alloys are non-magnetic and extremely corrosion resistant, have low thermal conductivity, and have outstanding strength-weight ratios. On the negative side, they are expensive and difficult to machine. Mechanical properties of some of the more common alloys are given in C16. Zinc alloys. Zinc is a relatively inexpensive metal with moderate strength. It has a low melting point and so is readily and economically die-cast. Typical zinc die casting include automotive parts, building hardware, office machine components, and toys. Limited use is made of the metal in other forms. Mechanical properties of common zinc die cast alloys are listed in C17. Also included is a relatively new alloy, ZA12, that can be cast using various methods. Chapter 3.12. Okay. Plastics and composites. The information contained in this section is a brief overview of the extensive and complex field, and additional technical information related to engineering polymers is available at dewpoint.com and sapicip.com. Volumes of information concerning composite materials are given in MIL-HDBK 17 Composite Materials Handbook. Plastics constitute a large and varied group of synthetic organic materials. The basic chemical units of plastic materials are monomers. Under appropriate conditions, usually by applying heat, pressure, or both, polymerization takes place, combining monomers into polymers. Typical monomers and the corresponding repeating polymer units are shown in figure 3.9. The addition of more monomers to form longer and longer polymer chains increases molecular weight and vastly alters physical properties. For example, figure 3.10 shows CH4, which is methane gas. Adding one CH2 unit gives heavier ethane gas, C2H6. Continued addition of CH2 gives pentane, a liquid, C5H12, and paraffin wax, C18H38. At approximately C100H2O2. Holy crap, that is a high number. Okay, the material is tough enough to be a useful plastic known as low molecular weight polyethylene. The toughest polyethylene, called high molecular weight polyethylene, contains nearly 500,000 CH2 units in a single polymer chain. I did not realize it was that much. My god. This is why you don't use plastic, guys. Okay. As I use a plastic bottle. Okay. Polymer chain structures can incorporate side branching. Also shown in figure 3.10, the degree of branching influences the closeness of which chains fit together. This, in turn, big ass head. Okay. Take that back. Okay. Extensive branching produces a more flexible and amorphous material with less mold shrinkage and distortion. Physical properties of the finished plastic can be altered by copolymerization, the building of polymer chains with two monomers, and by alloying, a strictly mechanical mixing or blending of constituents that does not involve chemical bonds. Plastics have traditionally been designed as thermoplastic, softening with heat, thermosetting, not softening with heat. A preferred designation is linear and cross-linked. The polymer chains in linear plastics remain linear and separate after molding. The chains in cross-linked plastics are initially linear but become joined irreversibly during molding into an interconnected molecular network. Cross-linking can be initiated by heat, chemical agent, radiation, or a combination of these. Some plastics can be either cross-linked or linear. The cross-linked form is more resistant to heat, chemical attack, and creep. On the other hand, the linear form is less brittle, more easily processed, and better adapted to the complex shape. Glass fiber reinforcement improves the strength of plastics by a factor of 2 or more, at substantially increased cost. A further improvement is obtainable by carbon fiber reinforcement. These relatively new materials have tensile strengths as high as 40 ksi. Compared to the glass reinforced resins, they have less mold shrinkage, low coefficients of expansion, and improved creep resistance, wear resistance, and toughness. The new fiber reinforced plastics are being increasingly used for manufacturing machines and structural components requiring lightweight and high strength to weight ratios. Oh my god. Properties of a few common plastics are given in Appendix C 18A. A comparison of these properties in thermoplastics with and without glass reinforcement is given. The thermal-setting plastics benefit similarly from glass reinforcement, the most commercially important being polyester and epoxy resins. And using the tables giving properties of plastics, the reader should recall which gives pitfalls in the use of such handbook data and on the properties of materials. The pitfalls given in this section are particularly true for the data on plastics. Published values reflect the obtained from standardized molding conditions that are simple, economical, and readily produced. Strength values corresponding to actual molding conditions may differ significantly. Furthermore, temperature and rate of loading influence the strength of plastics to a greater extent than they do strength of metals, thus requiring additional effort to the proper selection of plastic. C18C gives a listing of typical applications that more common plastics. Comments relating to each of these follows. Recall the thermoplastics are generally impact resistance. Thermosets are generally heat resistant. Comments on different plastics. Cool. Composites. I'm not going over 100,000 of these. I don't see I mean, it's here. You can read it. It's a very useful. I'll read like a few of them. Acetone, very strong, stiff engineering plastic with exceptional dimensional stability and resistance to creep and vibration fatigue, low coefficient of friction, high resistance to abrasion, and chemicals retain most properties when immersed in hot water, little tendency, stress to crack. Okay, I'm just gonna go down to composites. A composite is composed or formed from two or more constituent materials, each dissimilar and having different properties. With the composite, the material remain distinct and separate on the macroscopic level. Composite materials are not uniform throughout the matrix and not macroscopically homogeneous. The composite materials therefore are not isotropic, or nor do they possess uniform directional properties like metals, since a composite is made from combinations of materials that can be designed to improve thermal and mechanical properties. One major advantage of some composites is their high strength to weight ratio, which can be 4 times of that high strength metals. The stiffness to weight ratios can be 7 times of that high strength metal. As common examples, engineering composites are combinations of strong fibers such as glass, carbon, and boron bonded together in material like nylon, epoxy, or polyester. The constituents of composite materials are comprised of matrix materials, reinforcement materials, various plastic resins, and sometimes even metals are used as matrix materials. Common reinforcement materials are glass, carbon, SiC, and Kevlar, which can be formed of short fibers, long fibers, continuous fibers, randomly oriented fibers, woven fibers, or particulates. Particulates can act as reinforcement, although they are usually added to a matrix to reduce costs or achieve specific material properties. Examples would be glass beads added to the thermoplastic matrix to reduce cost, or mica added to the phenolic matrix to improve electrical properties and or material processing. As the name suggests, reinforcement materials provide improved physical and mechanical properties, strength and stiffness, and the matrix material supports, surrounds, and maintains the position of and transferred load to the reinforcement material. Because the reinforcement material is often made from the fibers of larger pieces of the material, the composite benefits of the size effect. The fibers of smaller diameter have higher tensile strength than parent material. Glass, for example, has a relatively low tensile strength, yet the glass fiber has much higher strength than glass in sheet form. The directionality and orientation of the composite material determines its properties and behavior. The orientation of reinforcement fibers within the composite, such as parallel, woven, random, wound, and angled, can be used to take best advantage of the directional properties of the material. Where a ply single layer has a strong directionality properties, structures of multiple piles or laminates are employed, where each ply is arranged to provide improved strength and stiffness. In general, because of the influence of directionality of the composite material, a minimum of at least 2 Young moduli in a shear modulus and a Poisson ratio are needed for the analysis of stiffness. Wow. A lot of stiffness. Okay. Material selection charts. The information contained in this section is a brief overview of granted design and Ashby material selection charts of graphically present information concisely assist in selecting types of materials based on properties such as stiffness, strength, and density. The information contained in these charts is for rough calculations, not for final design analysis. Actual properties of the material selected should be used in the final design, followed by experimental verification and testing. Strength stiffness chart. Various materials are plotted in strength versus Young modulus. The plotted values of strength are yield strength for metals and polymers, modulus and rupture for ceramics and glasses, tensile failure strength for composites, and tensile tear strength for elastomers. Design requirements for Values of strength or Young's modulus suggest materials to select. For design requirements that are bounded by elastic design or ratio of strength versus Young's modulus, the proper materials can be selected and are compared by energy storage per volume as in springs, radius of bending as in elastic hinges, or deflection under the load as in diaphragm design. For example, we want to maximize the energy storage per volume before failure. We want to maximize the value of S squared divided by E equals C without other design limitations. Inspection of the chart shows that the engineering ceramics have the highest allowable S squared divided by E, followed by elastomers, engineering alloys, steels, engineering composites, engineering polymers, woods, and polymer foams having decreased values. Strength density chart. For a wide variety of materials, strength ranges from 0.01 MPa to 10,000 MPa, while density ranges from 10 to 50,000 kg divided by m to the cubed power. Engineering material selection process introduction. As stated in the introduction to this chapter, the selection of materials and processes used in fabrication are integral parts of the design of a machine component. The goal of the selection is to give the engineering student an introduction to the process of making intelligent choice when selecting materials of the machine components. Although material selection is based on experience and know-how, the section presents a rational method for selection of materials. Table 3.2 presents a list of general performance characteristics for a machine component application. Once the characteristics of the application and the functional component are understood, the material selection is based on availability of the material in the form and shape desired, total cost of the material including initial and future costs, material properties as they relate to service performance requirements, and the processing of material into a finished part. Section 3.14.2 gives material information sources that can be used to identify other materials. Other factors to be considered in the selection of material include the limits of material properties, pressures to reduce costs, increase product/machine energy efficiency through weight reduction, material shortages, ease of recovery and recycling disposal, and legal and health issues. In this design process, machine performance specifications are established, then components are identified, and specifications for their performance are developed from the overall design concept of the machine. The specification of selection of materials typically takes place when the detailed drawings of the components are prepared. Figure 3.13 illustrates the material selection and evaluation process for a component. Identify characteristics of the application, identify component specifications, identify required material properties, select potential material candidates, fabrication of components, verification / evaluation, specify best material. So it's pick and choose after calculations. The material selection process typically involves satisfying more than one service performance requirement, that is, more than one specific characteristic of the application. This can be accomplished by weighing the various performance requirements with respect to the significant material properties that control performance. The specifications are then transformed into the material properties, and materials that have the desired properties and can meet the performance specifications are identified. Performance, cost, and availability are considered to arrive at a single or small set of materials for the component. The smaller group of materials become the candidate materials to further evaluation and possible testing in detailed design phase. Tests may be conducted to eliminate or rank the materials. Extensive testing may be required to establish the integrity and variability of the materials, the effect of manufacturing processes, and the effect of mating parts, etc. Indeed, the entire machine, sub-assemblies, product, or component may be evaluated in simulated or actual service condition tests. Also, it is not uncommon that components placed into service are monitored as operational experience begins to accumulate. And if service failures occur, material selection and / or design corrections are implemented and replacement parts are readied for schedule, maintenance, and replacement. Material selection is an iterative decision-making process of synthesis requiring experience, training, and engineering know-how combined with art to select material that will be suitable to the task. Past experience with material selection yields an understanding of material systems, familiarity with specific engineering materials, and an understanding of the properties of a small repertoire of materials, a few metals, plastics, ceramics, tool steels, and so on. This experience is helpful when the prior learning is applicable to a new selection program. Experience allows a design to rely less on the materials engineer and metallurgist. Oh my god. We're going over time. God. Okay. Chapter 3.14.2 Sources of information on material properties. Okay, this is just the appendixes. Okay, chapter 3.14.3 The principal selection factors have a bearing on the selection of materials and fulfill a design requirement are as follows: availability, cost, material properties, mechanical, physical, chemical, dimensional, manufacturing processes, machining, forming, joining, finishing, coating, and 3D printing. Table 3.3 lists subfactors that related to the important selection of parameters. Not using the proper material selection factors and choosing the inappropriate material can comprise function of the material, service life, and cost of component and product. Service performance. Once the general characteristics of the application are known, they can be reduced to service performance requirements. Examples of service performance conditions would be fluctuating high loads, high temperatures, and highly oxidizing atmosphere. The service performance, also called performance specifications or functional requirements for a machine component, needs to be related to the properties of materials. This is because the properties of materials are indicators of service performance. That is, wear is related to hardness, stiffness is related to modulus of elasticity, and weight is related to density. The designer must be able to translate the service performance requirements into select material properties. Another view of this is general service performance characteristics, described generally in table 3.2 and described specifically by stresses, motions, and applied forces, need to be translated into the mechanical properties of the material. That is, the material must have characteristics, properties, cost, and availability suited for the service conditions, loads, and stresses. Availability. Even though the potential material candidates have required material properties, they must be available. Answering the following questions can assist in the designer and whether the material candidates meet the availability of criteria. What is the total time to obtain the material? Is there more than one supplier that can provide the material? Is the material available in the geometry configuration required? What is the limit on the amount of material available? What is the probability of the material being available in the future? Is special processing required? Will special processing limit the availability of the material? It is the designer's responsibility to establish a timeline for the procurement of materials. The time to obtain materials needs to coincide with the time dedicated by the schedule. Economics, total cost. Cost should be used as an initial factor in screening materials, yet true prices of materials for a component can only be obtained through quotes from vendors. Material properties. A knowledge and understanding of the properties. Manufacturing processes. It is important to recognize the links between material properties and uses of materials. Although related material properties in the manufacturing processes will influence the type of material that can be used in the material, will dictate the type of manufacturing process that can be employed. Also, the material may impose limitations to the design, manufacturability, and component. In other words, the methods of manufacturing, forming, joining, and fastening are dictated by the material choice, and likewise, if a certain manufacturing process will be used to fabricate a component, then the material choice may be limited. Oh my god. It's time to begin, isn't it? Formability and joinability. Although formability and joinability are related to the material properties, the ability of forming, joining, and fastening materials is an important consideration in material selection. The material must be formed, joined, or fastened to the desired shape by shearing, blanking, piercing, bending, spinning, drawing, peening, welding, brazing, soldering, threading, riveting, stapling, or adhesive bonding. Finishing and coatings. Although related to material properties, the finishing or coating ability of design material has an influence in the selection of component material. For example, low carbon steel trencher teeth, when hard-faced, results in a wear resistant and lower cost part. Selection procedure problem. Okay, gotta take a break. Cannot. Oh my god. I'm losing my voice. No, I'm not. Okay, I can do this. Formability and joinability. Although formability and joinability are related to material properties, the ability of forming, joining, and fastening materials is an important consideration in material selection. The material must be able to be formed, joined, or fastened in the desired shape by shearing, blanking, piercing, bending, spinning, drawing, painting, welding, brazing, soldering. Finishing and coatings. Selection procedure. Problems in material selection for machine design usually involve the selection of material for a new redesigned component. Although the goals generally involve performance, reliability, and cost, the selection process usually involves making a decision of insufficient or inaccurate property data, subject to multiple constraints, sometimes competing, and usually without a clear-cut known objective. The methodology of material selection is based on the engineering performance consideration for a given application, the relative importance of required materials, and the availability and final cost of a component. The goal is to select the appropriate material to best meet the demands of the design requirement for a given application. The approach is to identify the connection between the functional requirements and the material requirements, and thus reduce the number of candidate materials from which to select. When selecting among candidates, the choice in some cases can be unambiguous, or the reasons for difficulty for choosing may be revealed. Although material selection involves iterative decision making, when we have a description or definition of a part or component, we recognize that steps in selecting a material for a component follows a typical path. Determine the purpose of the component. Establish the service performance requirements for the part. The service performance of operational conditions for the component needed to be well understood, as these conditions influence the material selection. For example, a gear operating under a heavy load and high speed at elevated temperature would probably require a different material than low speed, low torque gear operating at room temperature. This first step may require analysis of material requirements, that is, determination of the conditions of operation and the environment that the product must withstand, so that the service performance conditions can be translated into corresponding critical material properties. Table 3.3 provides a list of material characteristics that can review to recall general areas to examine. Select a material that appears suitable for the purpose. The second step may initially involve the screening and ranking candidate materials before a candidate material is selected. The material selection charts of section 3.13 can be used to make initial choices of materials that will meet performance requirements. C23 lists candidate materials for common machine components. Knowledge of the material groups, plastics, materials, metals, ceramics, and composites, and the type of component in which the material has previously been used allows the designer to compare materials, knowing what heat treatment and other processes to use when specifying the material. Also use experience Appendix C for typical uses of common materials, and do not reinvent the wheel unless it is important to do so. For example, C10 might suggest considering 6063 T6 aluminum for Terra Cruiser light wheel fuel tanks. Availability, cost, and fabrication should be considered in the onset of the material selection process, even though a detailed cost is not possible to attain. Besides experience, a rational method of selecting materials to utilize failure analysis of similar parts that have failed in service. Materials are selected that are unlikely to fail based on knowledge gained from failure analysis for the component. C24 identifies the material properties that are related to the common failure modes. Since service performance conditions are complex, usually more than one material property is required to identify the properties important in mode of failure. When selecting materials, it should be kept in mind that useful life of most machines and components ends with fatigue, failure, or surface deterioration, pitting, spalling, or excessive wear. After listing material considerations, select a few candidates materials that best match the critical material properties, cost, and availability constraints. You consider formability, fabrication, fastening, and joining, availability, and cost of material, as well as the cost to the production process. When screening candidate materials, ask this question: should this material be evaluated further for this application? Decision making needs to be done carefully but quickly. There is no perfect knowledge. The higher value of SI, the better choice. The selection index can be used to rank order materials. Unfortunately, for available materials and processes, in many cases, the best engineering solution and the best economic solution for the given design do not usually match, and the final material will be a compromise that yields optimal selection of that combines a set of requirements. Test. Once a material candidate has met the material properties, availability, and cost criteria, it is recommended that the candidate is selected to be tested. The test should simulate the product operating conditions. If the selected materials satisfy all the requirements, then there is no need to select an alternate candidate. As the final step, the product itself may need to be tested and the materials selection is re-evaluated. Whether or not the extensive testing program is required depends on total costs, service conditions, and experience. The degree of uncertainty of the material selection with respect to the performance and risk needs to be weighted. That is, the consequences of failure, that analysis of the risk be considered in the material selection process. The material selection process can be as challenging as other aspects of the design process because it follows the same direct decision-making approach. The steps in the material selection process, although iterative, are analysis of the requirements, identification of materials, selection of the evaluation of the candidate materials, and testing and verification. The key is needed to establish the properties and service performance of requirements needed for a design. Once needed properties are identified, the designer selects one or two candidate materials and treatments. It is appropriate to compare the candidate materials for availability and economics. Finally, serviceability and risk could be considered. Final selection involves the compromise of availability, properties, processes, and economics. In short, material selection should include consideration of availability, total cost, material properties, and manufacturing processes by using experience, engineering know-how, selection index, and knowledge of possible failure modes to choose the best material. Example problems. Chapter 4.1 Introduction. Once the external loads applied to a member have been determined, the next item of interest is often resulting stresses. This chapter is considered body stresses existing within the member as a whole, as distinguished as from surface or contact stresses in localized regions where external loads are applied. This chapter also is concerned by stresses resulting from essentially static loading, as opposed to stresses caused by impact or fatigue loading. As noted in section 3.2, this book follows the convention of reserving the capital letter S for material strength, using Greek letters sigma and T for normal stress and shear stress, respectively. Figure 4.1 illustrates a case of simple tension. If external loads P are reversed in direction, the bar is loaded in simple compression. In either case, the loading is axial. Small block E represents arbitrarily located infinitesimally small element of material that is shown by itself. Figures 4.1b and c. Just as equilibrium of the bar as a whole requires the two external forces to be equal, equilibrium of the element requires tensile stresses acting on the opposite pair of elemental faces to be equal. Such elements are commonly shown as in figure 4.1c, where it is important to remember that stresses acting on faces perpendicular to paper. This is made clear by isometric view in figure 4.1b. 4.1d illustrates equilibrium of the left portion of the link under action of the external force at the left and the tensile stresses acting on the cutting plane. From this equilibrium, we have perhaps the simplest formula in the all of engineering. Sigma equals P divided by A. Here are the figures. It is important to remember that although this formula is always correct as an expression for the average stress in any cross-section, disastrous errors can be made by naively assuming that it also gives the correct value of maximum stress in the section. Unless several important requirements are fulfilled, the maximum stress will be greater than P divided by A. Perhaps by several 100%. The maximum stress is equal to P divided by A only if the load is uniformly distributed over the cross-section. The section being considered is well removed from the loaded ends. 4.1e shows lines of force flow. To illustrate the general nature of stress distribution in cross-sections at various distances from the ends, a sustainability uniform distribution is reached at points about 3 diameters from the end fitting in most cases. Direct shear loading. Direct shear loading involves the application of equal or opposite forces so nearly collinear that the material between them experiences shear stress with negligible bending. 4.3 shows a bolt serving to restrain relative sliding of two plates subjected by opposing forces P, with plate interference friction neglected by bolt cross section of area A marked experiences direct shear stress of average value. If the nut in 4.3 is tightened to produce initial bolt tension P, the direct shear stresses at the root of the bolt threads and the root of the nut area have average values in accordance with the 4.2. The thread roots involved are cylinders of a height equal to the nut thickness. If the shear stress is excessive, shearing or stripping of the threads occur in the bolt or nut, whichever is weaker. Similar examples of direct shear occurs in rivets, pins, keys, splines, and so on. Moreover, direct shear loading is commonly used for cutting in ordinary household shears or scissors, paper cutters, and industrial metal shears. Figure 4.4 shows a hinge pin loaded on in double shear where the load P is carried on a shear through two areas in parallel. Hence, the area A used in 4.2 is twice the cross-sectional area of the pin. Example pins of loaded in the double shear are common. Cotter pins are used to prevent threaded nuts from rotating. The shear pins used in drive boat propellers. Transverse pins used to hold telescoping tubular members in a fixed position, and many others. Direct shear loading does not produce per shear, and the actual stress distribution is complex. It involves fit between the mating members of the relative stiffness. The maximum shear stress will always be somewhat in excess of the P divided by A value given by 4.2 in the design of a machine and the structural members. However, 4.2 is commonly used in the conjunction with appropriately conservative values of working shear stress. Furthermore, to produce the total shear fracture of ductile member, the load must be simultaneously overcome the shear strength in every element of material of the shear plane. Thus, for total fracture, 4.2 would apply with T being set equal to the ultimate shear strength, SUS. Shear torsional loading of the round bar. Note that the direction of the applied torque determines the left face of the element E is subjected to a downward shear stress and the right face of the upward stress. Together, these stresses exert a counterclockwise couple on the element that must be balanced by a corresponding clockwise couple created by the shear stresses acting on the top and bottom faces. The state of the stress shown in element E is per shear. The sign convention for axial loading distinguishes between two basically different types of loading. Compression can cause buckling, whereas tension cannot. A chain or cable can withstand tension but not compression. Concrete is strong in compression but weak in tension, and so on. The sign of convention is for shear loading serves no similar function. Positive and negative shear are basically the same, and the sign convention is purely arbitrary. Any shear sign convention is satisfactory so long as the same convention is used throughout any one problem. This book uses the convention of positive clockwise, that is, the shear stresses on a top and bottom faces element E tend to rotate the element clockwise, hence are regarded as positive. The vertical faces are subjected to counterclockwise shear, which is negative. For round bar and torsion, the stresses vary linearly from 0 at the axis to a maxima at the outer surface. Strengths of materials text contain formal proofs that the shear stresses intensity of any radius r is T equals TR divided by J. Of particular interest, of course, the stress at the surface where r is equal to the outside radius of the bar and J is the polar moment of the inertia of the cross section, which is equal to pi d to the 4 divided by 32. For a solid round bar of diameter d, simplest substitution of this expression in 4.3 gives the equation of the surface torsional stress in a solid round bar of diameter d. The corresponding equation of torsional stress in a hollow round bar follows a substitution of appropriate equation for polar moment of inertia. The bar must be straight and round, and the torque must be applied to about the longitudinal axis. The material of the homogeneous and perfectly elastic within the stress range involved. The cross-section considered must be sufficiently remote from the points of load application and from the stress razors. For bars of non-round cross-section, the foregoing analysis gives completely erroneous results. This can be demonstrated for the rectangular bars by marking a rubber eraser with a small square elements 1, 2, and 3 as shown in figure 4.6. When the eraser is twisted about its longitudinal axis, 4.3 implies the highest shear stress would be at the corners because these are farthest from neutral axis. Similarly, the lowest surface stress should be at element 1 because it is closest to the axis. Observation of twisted eraser shows exactly the opposite. This does not distort at all, whereas element 1 experiences greatest distortion of any element on the entire surface. A review of the formal derivation of 4.3 reminds us of the basic assumption that what transverse planes before twisting remains planes after twisting. If such a plane is represented by drawing line A on the eraser, it is obvious that a distortion occurs upon twisting. Therefore, the assumption is not valid for a rectangular section. The equilibrium requirement of the corner element 2 makes it clear that this element must have zero shear stress. The free top and front surfaces do not contact anything and could apply shear stresses. This being so, the equilibrium requirement to prevent any of the other four surfaces from having shear, since there is zero shear stress along all edges of the eraser. Cool. Oh my god. 4.7 and 4.8 show beams loaded and only in bending, hence the term per bending. From studies of strength of materials, the resulting stresses are given by the equation sigma equals my divided by I, where I is the moment of inertia of the cross-section with respect to the neutral axis, and y is the distance from the neutral axis. Bending stresses are normal stresses with the same axial stresses. Sometimes the two are distinguished by the appropriate subscripts as sigma for bending stresses and sigma A for axial stresses. For the bending shown in figures 4.7 and 4.8, tensile stresses exist above the neutral axis section and compressive stresses below. Maximum values are on the top and bottom surfaces. Per bending and loading curved beams. When initially curved beams are loaded in the plane of curvature, the bending stresses are only approximately in accordance of 4.6 to 4.8, since the shortest and stiffest path along the length of the curved beam is at the inside surface, a consideration of the relative stiffness. Of redundant load paths suggests that the stresses inside the surface are greater than indicated by the straight beam equations. Figure 4.9 illustrates that this is indeed the case. This figure also shows that equilibrium requirements of a neutral axis shift inwards amount E and the stress distribution to be hyperbolic. These deviations from the straight beam behavior are importantly severely curved beams such as these commonly encountered in C-clamps, punch press and drill press frames, hooks and brackets, and chain links. To understand more clearly about the behavior pattern shown in 4.9, let us develop the basic curved beam stresses equation. With reference to 4.10, let ABCD represent the element bounded by the plane of symmetry AB and plane CD. Moment M causes the plane CD to rotate through an angle D symbol to new position CD prime. C prime D prime. Rotation of the plane is of course about the neutral bending axis displaced at an as yet unknown distance E from the centroidal axis. The strain on the fiber shown at any distance y is the neutral axis equation. So more strain inside. Cool. More equations, more sample problems. 4.7, Chapter 4.7. Although the average transverse shear stress in beams such as the shaft in Chapter 2, Figure 2.11 is equal to V divided by A, the maximum shear stress is substantially higher. We will now review the analysis of distribution of this transverse shear stress, with emphasis on understanding of the basic concepts involved. Figure 4.14 shows the beam of an arbitrary cross-section that is symmetrical about the plane of loading. It is supported at the ends and carries a concentrated load at the center. We wish to investigate the distribution of transverse shear stress in the plane located in distance x from the left support and at a distance y above the neutral axis. A small square element at the location is shown in the upper right. Drawing the right and left faces of the element are subjected to shear stresses, with directions established by the fact that the only external force of the left of the element is directed upwards, but the resultant of external forces on the right is downwards. If only these two vectors acted on the same element, it would tend to rotate counterclockwise. This is prevented by the counterclockwise shear stresses shown on the top and bottom of the element. The reality of these horizontal shear stresses is easy to visualize. If one loads up a book or paper tablet with forces in Figure 4.14, the pages slide on each other. If the plastic playing cards is used in a long and used deck are stuck together, flexing the deck of these 3-point beam loading breaks them loose. Coming back to the small element in the figure, we can determine the magnitude of all 4 shear stresses by evaluating any of them. We now proceed to evaluate the shear stress on the bottom of the element. Imagine 2 transverse saw cuts distance dx apart, starting at the bottom of the beam and continuing down just to include the size of the square element. This serves to isolate the segment of the beam, the bottom surface of which the bottom surface of this element is acted upon by shear stress T. Note that the beam segment envelops the full width of the beam. Its bottom surface acted upon the unknown shear stress has a rectangular area of the dimensions d, x, and b. Dimension b will of course be different for various values y0. The enlarged views figure 4.14 shows the forces acting on the beam segment. A key point is that the bending stresses are slightly greater on the right side, where the bending moment is greater than on the left side by amount d, and the unknown shear stress at the bottom must be sufficiently large to compensate for this inequality, because the sum of horizontal forces must be 0. Let us now make a few important observations concerning this equation. First, the shear stresses is 0 at top and bottom surfaces. This is true because the saw cuts have no depth, so there is no inequality of bending forces on the two sides to be compensated for the stress at the bottom. As the saw cuts acquire increasing depth, larger and larger surfaces are exposed to the inequality of bending stress. Hence, the compensating shear stress must increase correspondingly. Note that the saw cut depth shown in figure 4.14 is a great increase in shear stress that would result in cutting in just a little deeper, because the area over which the compensating shear stresses acts is repeatedly decreasing. Note further, the maximum shear stress is experienced at the neutral axis. This is the most gratifying situation. The maximum shear stress exists precisely where it can best be tolerated, at the neutral axis, where the bending stress is zero. At any of the critical extreme fibers, the bending stress is maximum. The shear stress is zero. It often helps to establish concepts clearly in mind if we visualize them on a physical model. 4.15 shows ordinary rubber eraser ruled with a row of elements that indicate relative shear strains when the eraser is loaded in as a beam. If the eraser is loaded carefully, we can see the top and bottom elements are negligibly distorted, while the greatest distortion in the right angle corners occurs in the center element. Applying 4.2 to the solid, round, rectangular sections, we can find the parabolic shear stresses situations shown in 4.16 with maximum values at the neutral axis for solid round sections of T equals 4 divided by 3, V divided by A. For conventional I-beam section, width B is so much less in the web than the flanges that the shear stresses are much higher in the web. In fact, the shear stresses throughout the web are often approximated by dividing the shear force V by the area of the web only, with the web considered as extending the entire depth of the beam. In foregoing analysis of the tactical assumption that was made in the shear stress uniform across the beam with B in any distance from the neutral axis, although not strictly correct, this assumption seldom leads to errors of engineering significance. The variation of shear stresses across the width when the beam is treated in 8 and 11. Another topic left to advanced text in strength of materials is the loading of beams whose cross sections have no axes. A final point to be noted is that only in very short beams the transverse shear stress is likely to be important in comparison with the bending stresses. The principle behind this generalization is illustrated in 4.17, where the same loads are shown applied long and short beam. Both beams have the same shear load and the same slope of bending moment diagram. As the beam length approaches zero, the bending moment approaches zero, while the shear load and stresses remain unchanged. Simple tensile or compressive loading induces shear stresses on certain planes. Similarly, pure shear loading induces tension and compression. In some cases, the induced stresses can be more damaging to the material than the direct stresses. Figure 4.21a shows an ordinary rubber eraser marked with two large square elements, one oriented in the direction of sides of the eraser and the other at 45 degrees. The figure 4.21b shows the marked surface subject to tension. A shear distortion of the 45-degree square is clearly evident. If the eraser surface is loaded in compression, the shear distortion of 45-degree square is reversed. Figure 4.21c shows a enlarged view of the marked element with vertical and horizontal faces marked X and Y, and with tensile stresses sigma acting on the X faces, and the X and Y faces of the elements are of course perpendicular of the eraser surface, and as is made clear by the oblique view also shown in figure 4.21c, a Mohr circle plot of the stresses on the element is shown in 4.21d. Points X and Y are plotted to represent the normal and shear stresses acting on the X and Y faces. The circle is then drawn by with the line xy as a diameter. XY forces, XY shear forces, XY shear forces. Oh my god, it's getting pulled. Oh my god, shearing. Oh my god. Alright. Proof of the Mohr circle relationships is left to elementary text on strength of materials. The emphasis here is obtaining clear understanding of significance and interpretation of the Mohr plot. First, note that the imaginary cutting plane through the element is rotated, keeping it perpendicular. Why is there so much on shear forces? On goes on the x-plane to a y-plane, and on the x-plane again, only in 180 degrees. The normal and shear stresses along these, I'm pretty sure everyone knows what a shear force is. Okay, right? Like, we have paper, we were paper as kids. Okay. Those angles measured on the circle are twice the corresponding angles on the element itself. For example, x and y are 90 degrees apart from the element and 180 degrees apart on the circle. The second part of the point is that if we adhere to the shear stress sign convention given in 4.4, rotation of the cutting plane is in either direction to the element corresponding rotating twice as far as the circle in the same direction. Point S and S prime on the circle represents planes on maximum positive shear. On the circle, point S is 90% 90 degrees counterclockwise of X. Hence, the element plane S is 45 degrees counterclockwise of vertical plane X. The element drawn in figure, oh, it's teaching us how to read it, I guess, for math problems. More math problems. Huh. More math problems. Combined stresses. Mohr circle representation. More math problems. Got you. I see what they're doing. Okay. Chapter 4.11. Three-dimensional stresses. Since stresses exist only in real bodies that are three-dimensional, it is best always to think of stresses in three-dimensional terms. Uniaxial stress states involve that three principal stresses, but two of them are zero. Biaxial stresses involve one principal stress of zero. Forgetting about the zero principal stress can lead to serious errors, as is illustrated later in the section. Let us extend the analysis of the state of stress at point A in figure 4.24 by treating this as a three-dimensional problem. Figure 4.32 shows 5 views of the stress elements at point A. Oblique view showing the original x and y plane and the stresses on these planes. A principal element obtained by rotating 28 degrees about the z-axis. C, D, E direct or true values of the 1, 2, 1, 3, and 2, 3 planes of the principal element. A complete Mohr circle representation of the state of stress is shown in figure 3.4.33a. The large circle between points 1 and 3 represents stresses on all planes through point A, which contain the 2 or x-axis. The small circle between the 2 and 3 gives stresses on all planes containing the 1 axis, and the circle between 1 and 2 represents the stresses on all planes containing the 3 axis. Although each of these 3 circles represents an infinite number of planes through point A, a higher order of infinity remains that does not contain any of the principal axes. It can be shown that all such planes are subjected to stresses represented by points in the shaded area between the circles. The location of the specific point in this area that corresponds to any given plane is seldom of concern, but the interested reader can find the procedure involved in references such as section 3.7, since the largest of these 3 Mohr circles represents the maximum shear stresses as well as the 2 extreme values of normal stress. Mohr called this principle the principal circle. A common example where the maximal shear stress would be missed if we fail to include the zero principal stress that in the Moore plot is the outer surface of the pressurized cylinder. Here the axial and tangential stresses are tensile principal stresses, and the unloaded outer surface ensures that the third principal stress is zero. Figure 4.33b illustrates both the correct value of the maximum shear stress and the incorrect value obtained from a simple two-dimensional axis analysis. The same situation exists at the inner surfaces of the cylinder, except that the third principal stress is not zero but negative value, numerically equal to the internal fluid pressure. For the rare case in which there is significant shear stresses on all faces of the stress element, the reader is referred to the detailed works of the theoretical stress analysis. Also, this topic can be presented through the use of an example. Break. Oh, how am I only so far in? It's only page 176. My god, I have 800 more, 700 more pages. Fuck. Chapter 4.12. In section 4.2, figure 4.1 indicates lines of force flow through a tensile link. It was noted earlier that a uniform distribution of these lines existed only in regions substantially removed from the ends. Near the ends, the force flow lines indicate a concentration of stress near the outer surface. This same stress concentration effect exists for bending and torsional loading. Now we wish to evaluate the stress concentration associated with various geometric configurations, so that the maximum stresses existing and apart can be determined. The first mathematical treatments of stress concentrations were published shortly after 1900s. In order to handle other very simple cases, experimental methods for measuring highly localized stresses were developed and used. In recent years, computerized finite element studies have also been applied. The results of many of these studies are available in the form of published graphs, such as those in figure 4.35 through 4.41. These give values of theoretical stress concentration factor K1 for use in the equations. For example, the maximal stress of our actual loading would be obtained by multiplying PA by the appropriate value of K. Note that the stress concentration of the plot basis of dimensional ratios indicating for the shapes of the part is not involved. Also note that stress concentration factors of different axial bending and torsional loading. Among the most extensive and authoritative references to stress concentration factors are R. E. Peterson. In many situations, these notch parts of tension or bending. The notch not only increases the primary stress but also causes one or both of the other principal stresses to take on non-zero values. This is referred as the biaxial triaxial effect of stress razors. Although this is a small secondary effect that will not be pursued further in this book. Stress components can arise. Consider, for example, a soft rubber model of the groove shaft and tension illustrated in point 36b. As the tensile load is increased, there will be a tendency for our outer surface to pull into the smooth cylinder. This will involve an increase in the diameter of the circumference of the section on the plane of the notch. The increased circumference gives rise to the tangential stress, which is a maximum at the surface. The increase in diameter is associated with the creation of radial stresses. Stress concentration factor graphs. such as those in 0.35 through 0.41, pertain to the maximum stresses existing in the surface of the stress razor. The lower values of stress elsewhere in the cross section are seldom of interest, but in some simple cases can be determined by analytically from the theory of elasticity, or they can be approximated by finite element techniques or by experimental procedures such as photoelasticity. The variation in stress over the cross section is given for a few cases in Importance of Stress Concentration, chapter 4.13. It should be emphasized that the stress concentration factors given the graphs are theoretical or geometric factors based on theoretical, homogeneous, isotropic, and elastic material. Real materials have microscopic irregularities causing a certain non-uniformity of microscopic stress distributions, even in top and notch-free parts. Hence, the introduction of a stress razor may not cause as much additional damage as indicated by theoretical factor. Moreover, the real parts, even if free of stress razors, have surface irregularities that can be considered in extremely small notches. The extent to which the engineer must take the stress concentration into account depends on the extent to which real material deviates from theoretical and whether the loading is static or involves the impact of fatigue. For materials permeated with internal discontinuities such as gray cast iron, stress razors are usually have little effect regardless of the nature of loading. This is so that the surface or geometric irregularities seldom cause more severe stress concentration than that already associated with the internal irregularities. For fatigue and impact loading of the most engineering materials, stress concentration must be considered, as will be seen in subsequent chapters. For the case of static loading being treated in the chapter, stress concentration is importantly only with the unusual materials that are both brittle and relatively homogeneous. For more normally ductile materials that under special conditions behave in a brittle manner. For the usual engineering materials having some ductility, it is customary to ignore stress concentration for static loads. The basis of this is illustrated in the following discussion. Point 42A and B show that two flat tensile bars having the minimum cross-sectional area of A and each made of ductile material having the idealized stress strain curve then shown in point 42, the load on the notch bar can be increased to a value equal to the product area times yield strength before the failure occurs. This is represented in point 42. C. Since the grooved bar in the figure point 42b has a stress concentration factor of 2, yielding will begin only at half the load, as shown in point 42d. This is repeated in the curve A. As the load is increased, the stress distribution becomes B, C, and finally D. These curves represent a continuous deepening of local yielding, which began at the root of the curve, but gross yielding involving the entire cross-section is not ready to begin until D is reached. Note that the load associated with the curve is identical to the unnotched load capacity. Residual stress is caused by yielding. Axial loading when a part is yielded non-uniformly throughout the cross-section, residual stresses remain in this cross-section after external load is removed. Consider, for example, the 4 levels of loading of the top of a notch flat tensile bar in point 42. Same bar and the 4 levels of loading are represented in the left column, point 43. Note that the only slight yielding is involved, not major yielding, such as often occurs in processing. The middle column in this figure shows that the change in the stress when the load is removed, except for point 43a, where the load was not quite enough to cause yielding in the top at the notch root. The stress change when the load is removed does not exactly cancel the stresses caused by applying the load. Hence, residual stresses remain after the load is removed. These are shown in the right column of point 43. Note that in each case of point 43, the stress change caused by the removing the load is elastic. It is often helpful in visualizing the development of residual stresses, such as those shown in point 43, to imagine a column of small strain gauges mounted from the top of the bottom of the notch section. If these gauges are attached while the load is applied to the bar, they will initially read all zero, although the actual stresses in the cross section are as shown in the left column. As tensile load is released, the gauges will indicate compression, as shown in the middle. The average compressive stresses indicated by the gauges when the load is completely removed will, of course, be PA, but this provision is satisfied in the cases shown, even in figure 4.43d, where the elastic change in stress at the notch root is 2sy. No yielding occurs. Assuming the equal yield strength in tension and compression, the notch root material goes from sy in tension when the load is applied to sy in compression and the load is released. The elastic stress gradient curves associated with the various loads can be estimated graphically, as shown by the dotted lines from the left column of 43. After the dotted lines on the curves are sketched, the center column load release curves are obtained by merely changing the sign. Once the procedure is understood, the center column plots can be dispensed and the residual stress curves obtained by merely subtracting dotted curves from the solid curves in the left column. Without determining the actual shape of the stress distribution curves, the residual stress curves obtained in point 43 are admittedly approximations. They do, however, reflect the correct surface residual stress and general shape of the residual stress distribution curve, and these are usually the matters of primary interest. It must be remembered too that this development of residual stresses curves was based on assuming that the material conforms to the idealized stress strain curve of figure 42. For this reason also, the residual stress curves in 43 can be no better than good approximations. Okay, take a pause. Residual stresses caused by yielding, bending, and torsion loading. 4.44 illustrates residual stresses caused by the bending of unnotched rectangular beam. The figure illustrates the specific use of a 25 by 50 mm beam made of steel having an idealized stress strain curve with SY 300 MPa. Unknown moment M1 produces a stress distribution shown in figure 4.44a with yielding depth of 10 mm. First, let us determine the magnitude of moment M1 if the distributed stress pattern is replaced by concentrated forces F1 and F2 at centroids of the rectangular and triangular portions of the pattern, respectively. M1 is equal to the sum of the couples produced by F1 and F2. The magnitude of F1 is equally to the product of the average stress 300 MPa times the area of which it acts. Similarly, F2 is equal to an average stress of 150 MPa times the area of 15 mm and 25 mm. The moment arms of the couples are 40 and 20 mm respectively. Hence, M1 equals equation. Next, let us determine the residual stresses remaining after moment M1 is removed. Equations. Thermal stresses. Thus far, Only stresses caused by the application of external loads have been considered. Stresses can also be caused by constrained expansion and contraction due to either temperature changes or material phase change. In actual mechanical and structural parts, an accurate quantitative evaluation of these stresses in general beyond the scope of the text is. It is important, however, for the student to become familiar with the basic principles involved. From these, important qualitative information can be gained. When the temperature of an unrestrained, homogeneous, isotropic body is uniformly changed, it expands uniformly in all directions according to the relationship where E is the strain, A is the coefficient of thermal expansion, and delta T is the temperature change. Values of A alpha for several common metals are given in Appendix C1. This uniform unrestrained volume changes produces no shear strain and no axial or shear stresses. If restraints are placed in the member during temperature change, the resulting stresses can be determined by computing the dimensional changes that would take place in the absence of constraints, determine the straining loads necessary to enforce the restrained dimensional changes, and 3. Computing the stresses associated with these restraining loads. This procedure is illustrated by this following sample problem. In general, residual stresses are important in situations in which stress concentration is important. These include brittle materials involving all load types and the fatigue and impact loading of ductile as well as brittle materials. For the static loading of ductile materials, hardness, local yielding can usually occur to relative high stresses resulting from either stress concentration or superimposed residual stress. It is easy to overlook residual stresses because they involve nothing that ordinarily brings them to attention to the senses. When one holds the unloaded machine part, for example, there is normally no way of knowing whether the stresses are all zero or whether large residual stresses are present. Usually there are no readily available means for determining residual stresses. However, a reasonable qualitative estimate can often be made by considering thermal and mechanical loading history of the part during and after manufacture. Ellman and Black cite an interesting example showing that the residual stresses remain as a part as long as heat or external loading does not remove them by yielding. The Liberty Bell cast in 1753 has residual tensile stresses in the outer surface because the casting cooled most rapidly from the inside surface. After 75 years of satisfactory service, the bell cracked, probably as a result of fatigue of superimposed vibratory stresses caused by ringing the bell. Holes were drilled at the ends to keep track of the growling, but crack subsequently extended itself. Ellman and Black cite this proof that residual stress was present in the bell. Chapter 5: Elastic Train Deflection and Stability. Figure 5. Chapter 5.2 Strain Definition, Measurement, and Mohr Circle Representation. Figure 5.2 shows strains experienced by an element subject to uniaxial tension. Equations? Chapter 5.2 Strain Definition, Measurement, and Mohr Circle Representation. Figure 5.2 shows strains experienced by an element subjected to uniaxial tension. Equations defining the three linear components of strain are given on the figure. The loaded element experiences no change in the initial right angles. Shear strains yxy, yxz, and yyz are therefore zero, and the element shown is a principal element. Because of this, e, x, y, and ez are also e1, e2, and e3, where subscripts 1, 2, and 3 denote the principal directions. The negative values shown for ey and ez result from the material having a positive Poisson's ratio. 5.3 shows a similar element subjected to per shear. The resulting shear strains are defined on the figure. The double subscript notation corresponds to a convention mentioned briefly in 4.9 in connection with 4.26. As was true in the case of shear stresses, there is no need here to be concerned with a distinction between yxy, yx. 5.4 illustrates how Mohr strain circle can be plotted from a knowledge of ex, ey, and yxy. The procedure is identical to that used with the Mohr stress circle, except that the care must be taken to plot ordinates. Only half of the shear strain. Analytical stress equations have direct counterparts for strain, with E being substituted for sigma and Y divided by 2 substituted for T. When experimentally determining stresses at critical points on machine and structural parts, we begin by measuring strains and then compute the corresponding stresses for the materials of known elastic constants. If the directions of the principal axis are known, principal strains E1 and E2 can be measured directly by using electrical resistance strain gauges of single element type or 2-element rosettes. If principal directions are not known, we could theoretically determine E1 and E2 by measuring arbitrarily oriented strains EX, EY, and YXY, and then determining E1 and E2 for more circle plot, as in 5.4. Unfortunately, direct experimental measurement of shear strain is not normally practical. Hence, use is made of 3-element strain gauge rosettes illustrated in 5.5c and d. The rationale associated with this is as follows. Single element gauges oriented to sense horizontal strain. 2-element rosettes oriented to measure horizontal and vertical strain. 3-element equiangular rosettes and 3-element rectangular rosettes. First, note that the conventional Mohr circle construction, either for stress as shown in figure 4.27 or for strain as shown in figure 5.4, provides a convenient graphical solution of 3 equations and 3 unknowns. The unknowns are 2 principal stress values and the angle between the principal planes and the reference planes. A solution requires 3 known values. These are sigma x, sigma y, and txy, or ex, ey, and yxy, all linear strains. No simple graphical Mohr circle type solution is available, so an analytical solution is used. Such a solution is available when 3 linear strains in any direction, but only 2 commonly used arrangements will be considered here. Equiangular angular rosettes and rectangular rosettes. Information regarding strain gauge technology is online. The website contains technical literature in strain gauges, instrumentation, and photoelastic products, as well as calculators for strain gauge theory. Chapter 5.3 Analysis of Strain. Equiangular rosettes. All equiangular rosettes can be represented diagrammatically by figure 5.6a, which shows individual gauges at 0 degrees, 120 degrees, and 240 degrees in a counterclockwise progression. Oh yeah, I got wine. Fuck. Okay. Angle A alpha is measured from 0 degrees gauge to the as yet unknown principal axis. Figures 5.6b and c show other combinations of gauges orientation that are equivalent. Using the preceding notation, we have for principal strain magnitude in the direction of the equations. Oh god. Cool equations. There's a square root. You add something, you add the other, you do plus and minus, and then you have a tan. Okay. A positive value of A alpha means that we measure clockwise from the E0 gauge orientation to each of the two principal axis orientations given by 5.2. To determine which direction goes with which principal axis, use the rule that higher principal strain will always lies within 30 degrees of algebraically highest E0, E120, and E240. The use and interpretation of EQS 5.1 and 5.2 are illustrated by the following table. Cool gauge rosettes. 5.5 Elastic stress strain relationships in 3-dimensional Mohr circle. Elastic, or more precisely linearly elastic stress strain relationships for the general case of triaxial stress are given in various references. Triaxial. So there's 3 axes. Okay. More math equations. The basic deflection of the spring rate formulas are given 5 point deflection and spring rate simple cases. In the case of torsion, derivations are not included because we have presumably covered these in previous courses. No effort should be made to memorize these equations. Okay, but instead we should be sure to understand the rationale and pattern behind them. Then most of the equations will be memorized automatically. You couldn't tell me the rationale and pattern? Buddy. Okay. Note that the first 3 cases involve the deflection at the point load application and in the direction of the load application. In each of these cases, the equation merely states that deflection varies linearly with load. Okay. So it's random. For angular deflections, the symbol K is used. In case 4, note that the length must be squared. This must be so because the linear deflection increases both the length and the wide end scope, the latter being self-function length. In case 5, the length is cubed because the bending moment is an additional factor increasing with length. Incidentally, in case 5, the equation given for deflection results only from bending stresses, the contribution to deflection made by transverse shear being considered negligible. Castigliano's method treated in section 5.8 enables us to evaluate in the shear contribution. For now, let us merely note that the shear contribution to deflection follows exactly the pattern of cases 1, 2, and 3. The shear deflection varies linearly with shear load and length, and inversely with shear modulus of elasticity with a geometric shear rigidity property of the cross section, and the geometric shear rigidity property is roughly equal to the area for most sections. Beam deflection. Chapter 5.7. Beams are structural members subjugated to transverse loads. Examples include machinery shafts, building floor joist, fleece, leaf springs, automobile frame members, and numerous other machine and structural components. A beam often requires a larger cross-section to limit deflection than it does to limit stress. Hence, many steel beams are made of low-cost alloys because they have the same modulus of elasticity as stronger high-cost steels. You get it? Okay. The reader has undoubtedly studied previously one or more of the many methods for computing beam deflection. Appendix D contains a summary of the equations for deflection pertaining to beams of uniform section with commonly encountered loads. More complete tables are given in the many handbooks, such as for when more than one point on the beam is the sum of the individual deflections produced at that point by each of the loads acting singly. This method of superposition often provides the easiest and quickest solution to beam deflection problems involving several loads. For various reasons, many beams do not have the uniform cross-section. For example, machinery rotating shafts are usually stepped in figure 5.14 in order to accommodate the bearings and other parts assembled on the shaft. Okay. The calculations of deflections in such beams is tedious using the conventional methods. Fortunately, these problems can be solved by numerical integration of the M divided by EI curve with available software. Wow. Software. Math. Learning. Now, because of computers, it is unusual for engineers to solve the stepped shaft deflection problems by longhand methods. The following sample problem is included primarily to help the student to understand fundamental mathematical manipulations involved. Okay, so if you know math, then you can probably skip that. Okay, skip. It's just a math problem. I'm not reading a math problem. There's no point. Okay. Chapter 5.8. Determining elastic deflections by Castigliano's method. Castigliano's method. Situations frequently develop that make it necessary to compute elastic deflections not covered by the simple cases given in 5.1 and involving more than the bending loading treated in the previous section. Castigliano's method is selected here for dealing with these situations because of its versatility in handling a wide range of deflection problems, and because it is so useful in determining redundant reactions. The theorem underlying the method was published as part of a thesis written by Alberto Castigliano while a student in Turin, Italy, Polytechnical Institute in the mid-19th century. 5.15 shows the elastic load deflection curve of the completely general case. The load can be any force or moment with the displacement being the corresponding linear or angular displacement. The light blue area under the curve is equal to the stored elastic energy. The darker blue area, U prime, is known as the complementary energy by simple geometry. That is, stored elastic energy is equal to deflection times average force. The additional energy associated with the incremental load dq is du prime equals du equals delta dq. The theorem can be used to find the deflection at any point in any direction, even if there is no load at the point in direction. It is only necessary to apply an imaginary load, commonly designated as q, at the point in the direction desired, and to solve for the deflection as a function of q. After this expression is obtained, q is equated to 0 to obtain the final answer. Cool. Chapter 5.10 Euler's column buckling. Elastic instability. We normally think of deflections within the elastic range as varying linearly with load. Several notable exceptions occur, all of which involve subjecting relatively long thin portions of material to compressive strength. Perhaps the most common of these are long, slender columns loaded in compression. Examples include columns in buildings, structural compression links, piston connecting rods, coil springs in compression, and jack screws. These correspond to the general case treated by Leonhard Euler in 1744 when he published the first known treatise on elastic stability. Treatise. Okay, yeah. Euler's analysis pertains to 5.24, which shows a long, slender column such as an ordinary yardstick loaded in compression. Euler assumed the ideal case of a perfectly straight column with the load precisely axial, the material perfectly homogeneous, and the stresses within the linear elastic range. If such a column is loaded below a certain value, PCR, any slight lateral displacement given to the column results in the internal elastic restoring moment of more than adequate to restore straightness to the column when the lateral displacing force is removed. The column is then elastically stable. When PCR is exceeded, the slightest lateral displacement results in the eccentric bending moment PE greater than the internal elastic restoring moment, and the column collapses. Thus, loads in excess of PCR render the column elastically unstable. Euler's classical equation for PCR is derived in almost all texts in strength of materials. We give it here without repeating the derivation. Take a break here. I'll get to it. Page 237 out of maybe 900. Out of 900. Maybe. I don't know. But we'll get there. Chapter 5.11 Equivalent column length for various end conditions. Euler's analysis indicates that the theoretical shape of the deflection curve in figure 5.24 is 1/2 sine wave. In order to use the single Euler equation as 5.10 and 5.11 for all end conditions, it is customary to work with equivalent column length defined as the length of an equivalent column pinned at both ends. most common types of column end conditions, the theoretical values of equivalent length correspond to absolute rigidity of all fixed ends. In actual practice, this can be approached, hence columns having one or both ends fixed always have equivalent lengths longer than the theoretical. The minimum AISC recommendation is tabulated in figure 5.27 applied to the end constructions where ideal conditions are approximated. When fixed end attachments are less rigid, judgmental must be used. If rigidity is questionable, it is sometimes prudent to make the conservative assumption that bending rigidity of the fixed support is negligible and therefore equivalent to a pinned end. Cool. Column design equations. J.B. Johnson parabola. Because of inevitable deviations from ideal situation represented in the curves ACE and BDF, in 5.26, column failures occur at smaller loads than predicted by theory, particularly in the vicinity of points C and D. Many empirical modifications have been proposed to deal with this. Some of these embodied in codes that pertain to the design of specific equipment involving columns. Perhaps the most widely used modification in the parabola proposed by J.B. Johnson around the turn of the 20th century. This is shown for two cases in figure 5.28. The equation of the parabola is this. You guys can look at it on the screen. I don't think even if I read that out loud, anyone would understand it. I mean, I'll give it a shot. SCR equals PCR divided by A equals SY minus S squared Y divided by Y pi squared E capital E parentheses L E divided by P squared divided by P parentheses squared is what I meant. Although there is much scatter in the test data, Johnson parabola has been found to agree reasonably well with experimental results. As illustrated in 5.28, the parabola is always tangent to the Euler curve at point SCRLE where SC equals SY divided by 2. Cool. Math problems. If the line of action of the resultant column load P does not pass through the centroidal axis of the cross-section, the column is loaded eccentrically. The distance between the load axis and the column axis with eccentricity E, one eccentric moment PE is taken into account. The following an analytical equation known as secant formula can be derived, where C is the distance of neutral bending plane of the extreme fiber and where EC divided by P squared is known as the eccentricity ratio. It is important to note that 5.14 pertains to the buckling in the plane of the bending moment PE. Hence, the radius of the gyration P must be taken with respect to the corresponding bending axis. If this is not the least radius of the gyration, then we must also check for buckling of the axis of at least P, using procedures of concentric column loading described in the preceding sections. To illustrate this point, suppose the column shown in figure 5.24 is loaded with the force whose line of action is displaced a small distance along the x-axis. Although this eccentricity increases any tendencies to buckle about the y-axis, it has no effect on buckling about the x-axis. If the column section shown were more narrowly square, it is easy to visualize buckling about the y-axis for eccentricities greater than some critical value, and the buckling around the x-axis for smaller eccentricities. The secant formula is inconvenient to use for design purposes because of the involved way the various column dimensions appear in the equation. Curves such as those in 5.31 can be prepared for eccentrically loaded column design analysis involving a material with specific values of E and SY. The secant formula can be used with centrally loaded columns if we assume that some estimated small eccentricity would be inevitably be present in any realistic situation. An assumed eccentricity equal to LE divided by 400 is sometimes suggested for centrally loaded structural columns, and assumed eccentricity ratio EC divided by P squared of 0.025 is often used. As a result, an extensive study in 1933 by a committee of American Society of Civil Engineers. Chapter 5.14 Equivalent column stresses. As noted previously, column formulas provide equations for SCR with an applied PA load that can be compared. We can think of SCR as being related to SY by the equation SCR equals SY divided by alpha, where alpha is a factor where the compressive strength is reduced because of the buckling tendencies. For extremely short columns, as LE divided by P is less than 10, alpha is essentially unity. For longer columns, alpha takes on increasing values. It is sometimes convenient to use alpha as a stress multiplier. Then we can compare alpha P divided by A directly with SY. This concept is particularly useful when working with combined stresses. For example, if the direct compressive strength is involved in the calculations of sigma x or sigma y in EQS 4.15 through 4.17, the use of alpha P divided by A to make allowance for the buckling tendency. Other types of buckling. Columns, chapter 5.15. Columns designated for the structures requiring very high strength-weight ratios frequently use non-ferrous materials not having sharply defined yield point. For these materials in particular, the gradual onset of yielding as SCR is approached progressively reduces the slope of the stress-strain curve with resulting reduction in effective elastic modules. E. Methods have been developed based on the tangent modulus concept of dealing more effectively with the situation. The buckling stability of long column and circular cross-section can be greatly increased with no increase in weight by redistributing the same material into a tubular cross-section. There is a limit of how far one can go in this direction because tubing with a very thin wall tends to buckle locally, wrinkling in according fashion, while the axis of the column itself may remain straight. This is illustrated in 5.32a and can be readily demonstrated by using ordinary sheets of paper and a little transparent tape. The proportions are not at all critical, but try rolling an 8 1/2 by 11 inch sheet into the tube 8.5 inch long with either single thickness plus small overlap, or double thickness about 1 1/3 diameter. If the paper is reasonably quality, then the resulting column will easily support the weight of the book, pushing down on the book using care to keep the load concentric. Will cause a wrinkling or accordion type failure. The best failure patterns are usually obtained by pushing the book down quickly. Force equals MA. Okay. If the wall tube is subjected to external pressure, the circumferential compressive stresses can cause local buckling in the form of flute or longitudinal corrugations, as shown in figure 5.32b. When we attempt to bend a thin wall tube into a circular, common experience tells us that local bending occurs on a compression side. The desired bending can sometimes be accomplished by providing lateral support to the compression surface, either externally by a special bending fixture, or internally by filling the stand or other suitable material. A thin plate bent in the form of angle or channel can fail in the local buckling or wrinkling, as shown in 5.32c. A similar failure can occur in the thin I-beam flange, which is bent and subjected to compression. Typical local buckling of an externally pressurized thin wall tube. Okay. Then I-beam whip can wrinkle when high shear stress subjects it to compression. Shear-induced stress causes similar wrinkling in components fabricated by means of stress skin construction such as aircraft panels. Appropriate formulas. Chapter 5.16 Finite Element Analysis. Introduction. For generations, a matter of concern to engineers has been the determination of stress and strains in machines and structures. Although Castigliano's method of sections 5.8 to 5.9 computes elastic deflections and loads for more difficult problems than those simple cases given in Table 5.1. The finite element method will solve problems when the component geometry is complex and cannot be modeled accurately with standard strength of material analysis. In these complex cases, the determination of stresses, strains, deformations, and loads favor the finite element method. An approach to the broad applicability to different types of analysis, as well as different classes of structures, shells, joints, frames and components, gears, bearings, and shafts, for examples. The basic philosophy of the finite element method is discretization and approximation. Simply, the finite element method is a numerical approximation technique that divides a component or structure into discrete regions, and the response is described by a set of functions that represent the displacement or stresses in that region. The finite element method requires formulation, solution processes, and a representation of materials, geometry, boundary conditions, and loadings. To treat adequately the subject of finite element analysis would require a far more lengthy presentation that could possibly be justified in this text, yet the subject is so important that any engineer concerned with the design and development of mechanical and structural components should have at least knowledge of the basic principles. It is with this purpose in mind that the following introductory materials on the finite element method are presented. We hope that the interested student will find an opportunity to continue his or her study in the area. 5.16.2 Steps of a finite element analysis. Machine components can involve complicated geometric parts fabricated from different materials in order to determine stresses, strains, and safety factors. The component is divided into basic elements, each of the simple geometric shape and made of single material. Detailed analysis of each element is then possible. By knowing the physical interrelationships of the elements based on how they are assembled together, the approximate but relative accurate evaluation of the behavior of the component can be determined. Some basic finite element shapes are shown in the figure 5.33. Usually included in the finite method of stress analysis are the following steps. Divide the part into discrete elements, define the property of each element, assemble the elements, stiffness matrices, apply known external loads at nodes, specify part support conditions, solve the system with simultaneous linear algebraic equations, calculate the stresses in each element. Steps 1, 2, 3, 4, 5, 7 typically require input from the user. Finite element analysis program, as stated in the component, is divided into the assemblage of infinite individual finite elements. The material properties of each element is defined. The forces and displacements at each joint are identified for each member. Each element has its nodal forces. When the members are connected, all the nodal forces combined together at the joint equal at the loads applied at the joint. For a stationary component, The forces of each node must be static in equilibrium. Equations are developed to relate in the nodal forces to the nodal displacements, and these equations beside forces and deflections usually involve the modulus of elasticity of the member and its cross-sectional area and length. A stiffness coefficient is used to relate nodal force to nodal displacement. The total force can be written in terms of deflections and the stiffness coefficients. The stiffness matrix Kj of each element is assembled as a structural stiffness matrix that will model the structure. The structural stiffness matrix equation is bracket K squiggly bracket weird ass symbol equals F. We're back? Okay. Where weird symbol is the displacement vector and F is the force vector. From the solution EQA, we obtain the nodal forces and support reactions. From the forces, geometry, and material properties, we can then calculate the stresses in each element. From the forces, geometry, and material properties. Chapter 6: Failure Theories, Safety Factors, and Reliability. Chapter 6.1. Previous chapters have dealt with the determination of loads with the stresses and deflections caused by these loads, and with the ability of representative materials to resist standard test loads. The present chapter is concerned about predicting the capability of materials to withstand infinite combinations of non-standard loads which they are subjected to fabricated machine and structural components, and the selection of appropriate safety factors to provide safety and reliability. As well as with the earlier chapters, the concern of this chapter is primarily with static loads. Reliability is a matter of extreme importance and in the engineering of a product, and this point is becoming increasingly recognized. On the other hand, it is important that components not be over-designed to the point of making them unnecessarily costly, heavy, bulky, or wasteful of resources. The fundamental concept of designing every component of a machine to satisfy a given life and reliability requirement without over-designing a single part was perhaps the never so well phrased as by Oliver Wendell Holmes in 1853 when he wrote One Husshay, the classical bit of a literary heritage is all the more remarkable because Holmes was not an engineering but a physician and professor of anatomy at Harvard Medical School. He was the son of the Congregational minister and father of Oliver Wendell Holmes Jr., the noted Supreme Court Justice. In his remarkable poem reproduced here, Holmes tells the colonial Deccan possessed of such uncanny engineering genius that he was able to design and build one horse carriage so that every single component of the useful life was exactly 100 years, at the end of which time they all failed, causing the little wagon to collapse of heaps of rubble. Oh shit, that is actually pretty cool. Wait, that is such a cool story. Okay. The One Husshay. Have you ever heard of the wonderful One Husshay? That was built in such a logical way. It ran 100 years to a day, and then all of a sudden, but stay. I'll tell you what happened without delay, scaring the parsons into fits, frightening people out of their wits. Have you ever heard of that, I say? 1755. Georgius Secundus was then alive. Snuffy old drone from the German hive. That was the year when Lisbon town saw the earth open and gulp her down. And Braddock's army was done and so brown, left without a scalp to its crown. It was on the terrible earthquake day that the Dagon finished the one hoss shay. Now in buildings of chassis, I tell you what, there is always somewhere a weaker spot. In hub, tire, felloe, in spring or thrill, in panel or crossbar or floor or sill, in screw, bolt, thorough brace, lurking still. Find it somewhere you must and will, above or below or within or without, and that's the reason beyond a doubt. A chassis breaks down but doesn't wear out, but Dacons swear, as Dacons do, with an I do vum or an I tell you. He would build one shay to beat the town and the country and all the country round. It should be built. It should be so built that it couldn't break down. For, said Dacon, this mighty plane, the weakest place must stand the strain, and the way t fix it. You, I maintain, is only just to make the place oot strong oots the rest. So the Dacon inquired the village folk where he could find the strongest oak that couldn't be split nor bent nor broke, that was for spokes and floors and sills. He sent the lancewood to make the thrills. The crossbars were ash from the straightest trees, the panels of white wood that cuts like cheese, but lasts like iron for things like these. The hubs of logs from the settlers' Elam. Last of its timber, they couldn't sell 'em. Never an axe had seen their chips, and the wedges flew from between their lips. Their blunt ends frizzled like celery tips. Step and prop, iron, bolt and screw, spring, tire, axle, and linchpin too. Steel of the finest, bright and blue, thorough braced bison skin, thick and wide. Boot top dasher from tough old hide, found in the pit when Tanner died. That was the way he put her through. There, said the Dacon, now she'll do. Do, I tell you, I rather guess she was a wonder, and nothing less. Colts grew horses, beards turned gray. Dacon and Daconess dropped away. Children and grandchildren were they, but there stood the stout old one hoss shay, as fresh as Lisbon earthquake day. 1800. It came and found the Dacon's masterpiece strong and sound. 1800 increased by 10. Handsome carriage, they called it the land. 1820 came, running as usual, much the same. 30 and 40 at last arrive, and then come 50 and 55. Little of all value here wakes the morn but its 100th year, without both feeling and looking queer. In fact, there's nothing that keeps its youth. So far I know but a tree in truth. Take it, you're welcome, no extra charge. 1st of November, the earthquake day, there are traces of age in the one house shay. A general flavor of mild decay, but nothing local, as one may say. There couldn't be, for the Dacon's art had made it so like in every part. Third, that there wasn't a chance for one to start, for the wheels were just strong as the thrills, and the floor was just strong as the sills, and the panels were just strong as the floor, and the whippletree neither less nor more, and the back crossbar as strong as the fore, and the string and axle and hub and core. And yet, as a whole, it is past a doubt. In another hour it will be worn out. 1st of November 55. This morning the parson takes a drive. Now, small boys, get out of the way. Here comes the wonderful one-horse shay, drawn by the rat-tailed, ewe-necked bay. "Hut up," said the parson. Off went they. The parson was working on his Sunday text. He got filthy and stopped perplexed at what the Mosses was coming next. All at once was the horses stood still, close by the meetin' house on the hill. First a shiver, then a thrill, then something decidedly like a spill, and the parson was sitting on top of a rock at 9:30 by the meetin' house clock. Just the hour of the earthquake shock. What do you think the parson found when he got up and stared around? The poor old chaise in a heap or mound, as if it had been to the mill and ground. You see, of course, you are not a dunce, how it went to pieces all at once, and nothing first, just as bubbles do when they burst. End of the wonderful one-horse shay. Logic is logic, that's all I say. That was nice. Okay. Chapter 6.2. Types of failure. Failure of a loaded member can be regarded as any behavior that renders it unsuitable for its intended function. At this point, we are concerned only with the static loading, saving for later chapters impact, fatigue, and surface wear. Static loading can result in objectionable deflection and elastic instability, as well as plastic distortion and fracture, with which the present chapter is concerned. Distortion or plastic strain is associated with the shear stresses and involves slip along natural slip planes. Failure is defined as having occurred when the plastic deformation reaches an arbitrary limit, such as the 0.2% offset in the standard tensile test. Often appreciably more yielding can occur without harm, as in localized abrasion or stress concentrated, and in some members of subjugated bending or torsion, where yielding is restricted to the outer surface. The definition by a failure distortion is arbitrary and not always easy to apply. Fracture, on the other hand, is clearly defined as the separation or fragmentation of a member into two or more pieces. It is normally constitutes a pulling apart associated with a tensile stress. In general, materials prone to distortion failure are classed as ductile, and those prone to fracture without a significant prior distortion as brittle. Unfortunately, there is an intermediate gray area wherein a given material can fail in either ductile or brittle manner depending on circumstances. It is well known that materials are normally ductile and can fracture in brittle manner at sufficiently lower temperatures. Other factors promoting brittle fracture are sharp notches and impact loading. An important concept of this connection is the transition temperature, that is a fairly narrow temperature range above which the material and the associated geometry loading conditions produce ductile failure, with brittle fracture occurring at lower temperatures. Also, in general, where the yield strength of a material is close to a magnitude of the ultimate strength or elongation of less than 5% of the material will not absorb significant energy in the plastic region, and brittle fracture can occur. For generations, a matter of concern to engineers and metallurgists have been a brittle fracture of structural steels that have that behave in a completely ductile manner during the ordinary laboratory test strengths. Figure 6.1 shows a rather spectacular example of World War II tanker broken in two by brittle fracture. Despite normal ductility associated with the grade of steel used, the mechanisms of brittle fracture are the concern of relatively new discipline, fracture mechanics. To treat adequately, the subject of fracture mechanics would require a far more lively presentation than could possibly be justified in the text. Yet the subject is so important that any engineer concerned with the design and development of mechanical and structural components should have at least a knowledge of basic principles. It is with this purpose in mind that the next two sections are presented. We hope that the interested student will find a opportunity to continue his or her study in the area. Damn, son. Pew. 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 Damn, son. They calculated that shit. Oh my god. Break time. Read one more chapter. Chapter 6.3 Fracture Mechanics Basic Concepts. The fracture mechanics approach begins with the assumption that all real materials contain cracks of some size, even if only submicroscopic. If brittle fracture occurs, it is because of the conditions of loading and environment are such that they cause almost instantaneous propagation to failure of one or more original cracks. If there is fatigue loading, the initial cracks may grow very slowly until one of them reaches critical size, at which time total fracture occurs. Theoretically, the stress concentration factor of the base of a crack approaches infinity because at this radius the crack root approaches zero. This means that if the material has any ductility, yielding will occur within some volume of material at the crack tip. The less stress it will be redistributed. Thus, the effective stress concentration factor is considerably less than infinity T. And furthermore, it varies with the intensity of the applied nominal stress. In the fracture mechanics approach, one does not attempt to evaluate the effective stress concentration per se. Rather, the stress intensity factor K is evaluated. This can be thought of the measure of the effective local stresses at the crack root. Once evaluated, K is then compared with the limiting value that is necessary to crack propagation in the material. This limiting value of the characteristic of the material called fracture toughness or critical stress intensity factor KC, which is determined from standard tests. Failure is defined as whenever the stress intensity factor K exceeds the critical stress intensity factor KC, thus a safety factor. SF for failure by fracture can be defined by Kc divided by K. Most currently available values of K and Kc for tensile loading, which is called mode I. Accordingly, these values are designated K1 and K1C. Modes 2 and 3 pertain to the shear loading. The treatment here will be concerned primarily with mode 1. A set of fracture toughness KIC presented in table 6.1 and more extensive set of K1C values are available in the MIL HDBK-5J book, Appendix F. Most available values of K1C are for relatively thick members, such as the material at the crack root is proximate at the state of plane strain. That is, the material that surrounds the crack and is under low stress resists Poisson's ratio contraction at the crack root, thereby enforcing E similar to 0 in thickness direction. Crack root material in sufficiently thin members is free to contract in the thickness direction, giving sigma 3 similar to 0 or condition of plane stress. The plane strain tensile loading with sigma 3 being tensile offers less opportunity for redistributing high crack root stresses by shear yielding. Because of this, the values KIC for the plane strain are substantially lower than those for the plane stress. Thus, the more readily available plane strain values of KIC are often used for conservative calculations when the value KIC for the actual thickness is not known. Fracture mechanics applications. Thin plates. Figure 6.2a shows a thin plate with central crack of length 2c extending through the full thickness. If the crack length is a small fraction of the plate width and the P divided by A stress figured on the basis of net area, T parentheses 2W minus 2C parentheses is less than the yield strength, then the stress intensity factor at the edges of the crack is approximately K1, similar to KO equals to sigma square root pi c equals to parentheses 1.8 square root c parentheses sigma g. Where sigma equals sigma g is the gross section of the tensile strength P divided by 2 Wt and the K0 stress intensity factor for a short central crack at length 2c and the flat infinite plane of small thickness T. She is subjected to the uniform tensile stress. Rapid fracture occurs when Ki becomes the KIC, the fracture toughness of the value of the material. In this case of thin plate, the plane stress of the value KIC would be preferred. Thus, failure occurs when three basic variables reach the following approximate relationship. For geometries that differ from the central crack in a small fraction of the plate with a configuration factor y is introduced that accounts for the particular geometry and loading. For example, with a crack occurring at the edge of the plate, the preceding equation is applied with only a small increase in the value of the constant. Thus, the failure criterion for the figure 6.2 becomes approximately. So they are just guesstimating with a small constant. Okay. That's not too good, but alright, I'm gonna take a break here. Cracks in thick plates generally begin at the surface, taking a somewhat elliptical form, as shown in figure 6.4a. If 2w divided by t is greater than 6, a divided by 2c about 0.25, w divided by c is greater than 3, a divided by t is less than 0.5, and sigma g and sy is less than 0.8. The stress intensity factor at the edges of the crack is approximately K1 equals to this equation. 6.1 gives typical mechanical properties of a 1-inch thick plates made of various structural materials commonly used in aircraft applications. Note particularly the relatively high fracture toughness of the titanium alloy in comparison to its ultimate strength. The room temperature comparison of KIC for the two steels of nearly equivalent ultimate strengths, and the reduction of KIC with the temperature of the high toughness D6AC steel. Thick plate with a central crack starting at one surface. Okay. Stress intensity factors. We now wish to evaluate stress intensity factors associated with various geometric configurations and loadings so that the maximum stress intensity factor existing in a part can be determined. In the past, in order to handle other than very simple cases, experimental and analytical methods for determining stress intensity factors were developed and used. The results of many of these studies are available in the form of published graphs, such as those in figure 6.5a through 6.5h, for geometries that differ from the central crack in small fraction of the plate with a configuration factor y is introduced that accounts for the particular geometry and loading. The configuration factor y equals ki divided by ko is plotted versus dimensionless ratios, indicating that not only that loading and the shape for the part of influences the configuration factor involved. The figures give values of the stress intensity factor ki at the crack tip. The value of k0 is the stress intensity factor of a short central crack of the length 2c in the infinite sheet subjugated to a uniform uniaxial tensile stress sigma, where ko is sigma square root pi c equals to 1.8 square root c pi g, sigma g. A stress intensity factor ki will reflect the particular geometry and loading, and thus will differ from k0 except for the plate with a small central crack. As mentioned before, the value of ki is compared to the value of kic to determine if failure occurs. Among the most extensive and authoritative compendium of stress intensity factors is that of Rook and Cartwright, which contains the collection of factors gathered from researchers and presented in a convenient form and grouped by categories: flat sheets, stiffened sheets, discs, tubes, bars, shapes with three-dimensional cracks, plates, shells. This compendium presents solutions to a multitude of crack problems in a straightforward graphical form. Some classes of problems are excluded, such as those involving thermal cracks and cracks at surfaces between different materials. We now present 8 figures selected from that can be studied and better understand the effect of proximity of cracks to different geometrical boundaries, such as sheet edges and stress concentrations like holes. Each figure presents curves of stress intensity factor with an inset for the corresponding geometry. 6.5a shows a rectangular sheet of width 2w and height 2h with a central crack of length 2c. A uniform tensile stress acts over the ends of the sheet and is perpendicular to the direction of the crack. 6.5a presents curves of the configuration factor y versus c divided by w for various values of h divided by w. Ko is the stress intensity factor of the central crack in an infinite sheet, and is given by ko equals sigma square root pi c. Here ki equals yko. Figure 6.5b shows the rectangular sheet of width 2w and height 4w, with 2 cracks each of equal length, c minus r. At a central circular hole of radius r, the cracks are diametrically opposite and perpendicular to the direction of the uniform load P, or uniform uniaxial tensile stress sigma. The crack tips are a distance 2c apart. 6.5b presents curves of the configuration factor y versus c divided by w for various values of r divided by w. 6.5b, the height width ratio is 2, and for the case of r divided by w equals 0, the results are correspond and agree for those for a central crack in a rectangular sheet. 6.5c shows that the flat sheet with a width w and 2h, the sheet is loaded with a uniform tensile stress sigma acting perpendicular to the edge crack length c. 6.5c presents curves of configuration factor y versus c divided by w for several values of h divided by w. 2 cases are presented where the ends are free to rotate, bending unrestrained, and 2 where the ends are constrained from rotating, bending restrained. As the previous figures, ki equals yk0 and ko equals sigma square root pi c. 6.5d shows that flat sheet of width w and height 2h. The sheet contains an edge crack in the middle of the perpendicular to one side. A splitting force P acts symmetrically along the side containing the crack of length c. 6.5d presents curves of configuration factor y versus c divided by w for various values of w divided by h. 6.5e shows a flat sheet with thickness t, width w, and an edge crack depth of c for both per bending and 3-point bending for c divided by w. 0.6 is less than or equal to 0.6, curves with configuration factors y versus c divided by w are presented in both cases. Since linear elastic fracture mechanics is being used, stress intensity factors of other types of mode 1 components can be obtained by superposition. For example, for a flat sheet with an edge crack and loaded with uniform stress and pure bending moment, the Ki from figure 6.5c and the Ki from figure 6.5e may be added to obtain the Ki for the combined loading. 6.5f shows the tube with inner radius Ri and the outer radius Ro. The tube contains a circumferential crack of depth c extending radially and inward from the outside surface. Remote from the crack, a uniform tensile stress sigma is applied and acts parallel to the tube axis. Presented are curves of configuration factor y versus c divided by Ro minus Ri for values of Ri divided by Ro for a long tube. Note that in the limiting case of short circumferential crack in a long tube, the results approach those for a short edge crack in a flat sheet that does not bend. 6.5g shows a cross sectional of a tube inside radius I and outer radius Ro. Radius output. The tube contains a radial crack at length c, extending the radial inwards and outside the cylindrical circumference. Cylindrical surface. The tube is subjected to an internal pressure P, presented on the curve's configuration factor y versus c divided by r output minus the initial for various values of, why don't they just use delta? Man, what? I don't get it. Okay, the stress sigma is, in summary, for the design and subsequent operation of machine components, fracture mechanics is becoming increasingly important in understanding cracks and crack growth during their service life. Linear elastic fracture mechanics is used successfully to better understand catastrophic failure, but the procedure requires knowing the stress intensity factor for the configuration and loading being considered. Cool. Chapter 6.5. The theory of static failure theories. Engineers engaged in the design and development of all kinds of structural and machine components are repeatedly confronted with problems like the ones depicted in 6.6, a proposed application of combinations of static loads that produce at a critical location stresses of sigma 80 ksi and sigma 2 negative 40 ksi and sigma 3 equals 0. The material being considered was found to fail on a standard tensile test at a stress of 100 ksi. Will this material fail in the proposed application, since it is impractical to test every material in the combination of stresses sigma 1 and sigma 2 and sigma 3? A failure theory is needed for making predictions on the basis of material's performance on the tensile test of how strong it is. It will be under other conditions of static loading. The theory behind the various classical failure theories is that whatever is responsible for the failure in the standard tensile test will also be responsible for the failure under all conditions of static loading. For example, suppose that theory is that failure occurred during the tensile test represented by 6.6b, simply because the material is unable to withstand a tensile stress above 100 ksi. The theory then predicts that under any conditions of loading, the material will fail if and only if sigma 1 exceeds 100 ksi. Since the proposed application in 6.6a has a maximum tensile stress of only 80 ksi, no failure is predicted. On the other hand, suppose it is postulated that the failure during the tensile test occurred because the material is limited by an inherent capacity to resist shear stress, and that based on the tensile test, the shear stress capacity is 50 ksi. On this basis, failure would be predicted in a figure 6.6a. Thus, reader will probably recognize the preceding examples as illustrating the maximum normal stress and maximal shear stress theories, respectively. Other theories have been advanced that would interpret the information 6.6b as establishing limiting values of other allegedly critical quantities such as normal strain, shear strain, total energy absorbed, and distortion energy absorbed. Sometimes one of these theories is modified empirically to obtain a better agreement with experimental data. It should be emphasized that the failure theories presented in this chapter apply to only situations with which the same type of failure occurs in the application as the standard test. Maximum normal stress theory. The theory concerning maximum normal stress, generally credited to English scientist W.J.M. Rankine, 1872, is perhaps the simplest of all failure theories. It contends merely that failure will always occur whenever the greatest tensile strength tends to exceed the uniaxial tensile strength, or whenever the largest compressive strength tends to exceed the uniaxial compressive strength. With respect to Mohr-Sekel's plot in 6.7a, failure is predicted for any state of stress for which the principal Mohr circle extends beyond either the dotted vertical boundaries on the sigma 1 minus sigma 2 plot for the biaxial stresses shown in 6.7b. Failure is predicted for all combinations of sigma 1 and sigma 2 falling outside of the shaded area. This theory has been found to correlate reasonably well with test data for brittle fractures. As might be expected, it is not suitable for predicting ductile failures. For this reason, the test points in 6.7 have been marked as SUT and SUC, ultimate strengths in tension and compression, respectively, of an assumed brittle material. Chapter 6.7 Maximum shear stress theory. The theory of maximum shear stress is thought to be the oldest failure theory, being originally proposed in the great French scientist C.A. Coulomb, who made a major contributions to the field of mechanical for electricity. Coulomb's law. Cool. Regardless of the name, we love Coulomb. Okay. Okay, cool. Regardless of the name, this theory is generalized forms states that a material subjected to any combination of loads will fail whenever maximum shear stress exceeds the shear strength of the material. The shear strength, in turn, is usually assumed to be determined by the standard uniaxial tension test. This theory is represented graphically in 6.8. Note carefully in 6.8b that in the first and third quadrants of zero principal stress is involved in the principal Mohr circle, whereas it is not in the second and fourth quadrants. The single test point is marked SYT, yield strength and tension of assumed ductile material. A data point in compression and torsion could serve as well, but the tensile test is the most common and the most accurate, hence it is normally used. Of course, if the material truly behaves in accordance with the maximum shear stress theory, all test data would agree on the level of shear stress associated with failure. This theory correlates reasonably well with the yielding ductile materials. However, the maximum distortion energy theory, discussed in the next section, is recommended because it correlates better with the actual test data for the yielding of ductile materials. Chapter 6.8 Maximum distortion energy theory. A remarkable thing about the theory of maximum distortion energy is that two equations can be derived from at least 5 different hypotheses. The two most important pertain to the names given in the theory in section 6.7. Credit for the theory is often given to M.T. Huber, R. von Mises, Germany and the United States, H. Henke, Germany and the United States, who contributed to it in 1904, 1913, and 1925 respectively. More recently, Timoshenko has brought light to the fact that it was proposed by 1856 by James Clerk Maxwell of England, who, like Coulomb, is better remembered for its contributions to electrical engineering than for his important contributions to field of mechanics. Briefly, the contention of the maximum distortion energy theory is that any elastically stressed material undergoes a slight change in shape, volume, or both. The energy required to produce this change is stored in the material as elastic energy. It was recognized that the engineering materials could withstand enormous hydrostatic pressures without damage. It was therefore postulated that a given material has a definite limited capacity to absorb the energy distortion, and that attempts to subject the matter to greater amounts of distortion energy result in yielding. It is convenient when using this theory to work on an equivalent stress, sigma, defined as the value of uniaxial tensile stress that would produce the same level of distortion energy as the actual stresses involved. In terms of the existing principal stresses, the equation for equivalent stresses is once the equivalent stress is obtained, this is compared with the yield strength of the standard tensile stress. If sigma exceeds SYT, yielding is predicted. These same equations can be readily derived on the basis of shear stress on the octahedral plane. Figure 6.9 illustrates the relationship of the octahedral plane and the faces of a principal element. There are 8 octahedral planes, all of which have the same intensity of normal and shear stress. Then the sigma E can be defined as the value of a uniaxial tensile stress that produces the same level of shear stress on the octahedral planes as do the actual stresses involved. Point 10, 6.10 shows that sigma 1 minus sigma 2 plot for the maximum distortion energy theory is an ellipse. This is shown in the comparison with the corresponding plots for the maximum shear stress and maximum normal stress theories for a ductile material having SYT equals SYC equals 100 KSI. The distortion energy and the shear stress theories agree fairly well with the distortion energy theory, given the material credit 0 to 15% more strength depending on the ratio sigma 1 to sigma 2. Also shown in the figure is the shear diagonal, or locus of all points, corresponding to per shear. It is interesting to note that the wide variation of the shear strengths predicted in various theories. As previously noted, actual shear tests of ductile materials usually agree quite well with the distortion energy theory, which predicts that the shear yield strength SY is 0.58 SY. The complete derivation of the equations for the equivalent stress from both the distortion and octahedral shear stress points of view is contained in several references such as chapters such as 2. The Moore's theory and modified Moore's theory. Over the years, various empirical modifications to basic failure theories have been proposed, one of which is the Moore's theory, represented in 6.11. This theory suggested for the brittle materials for which the compressive strength far exceeds the tensile strength. A modification of the Moore's theory, illustrated in 6.12, is recommended for predicting the failure of the brittle materials. It correlates better with the experimental data than do the Moore or maximum normal stress theories, which are also used. It is well to remember that at best a failure theory is substitute for good test data pertaining to the actual material and the combination of stresses involved. Any additional good test data can be used to improve theoretical failure theory curve for a given material. For example, suppose that the material involved in 6.10 was known to have an experimentally determined torsional strength of 60 KSI. We might then conclude that the material did not appear to behave in accordance of the distortion energy theory, but not exactly. By empirically modifying the ellipse just enough so it passes through the experimental point, we would have presumably better failure theory for making predictions in the second and fourth quadrants. Okay. Problems. Pause. Chapter 6.11 Safety Factors Concept Definition. A safety factor was originally a number by which ultimate tensile strength of a material was divided in order to obtain a value of working stress or design stress. These design stresses, in turn, were often used in highly simplified calculations that made no allowance for such factors as stress concentration, impact, fatigue, differences between properties and material in the standard test specimen, and in the manufactured part, and so on. As a result, one can still find in handbooks safety factor recommendations as high as 20 to 30. Modern engineering design gives rational accounting for all factors possible, leaving relatively few items of uncertainty to be covered by a safety factor, which is commonly in the range of 1.25 to 4. Modern engineering practice also bases the safety factor on significant strength of the material, not necessarily the static tensile strength. For example, if failure involves static yielding, the safety factor relates the static stress caused by the anticipated load, called the significant stress, to the static yield strength of the material, called significant strength, exactly as illustrated in the sample problem 6.3. If the significant stresses involve fatigue, then the safety factor is based on the fatigue strength. If brittle fracture is expected mode of failure, then the factor is based on tensile strength and so forth. Thus, the safety factor SF can be defined as a significant strength of the material divided by corresponding significant stress from normally expected loads, where the design overload is, and safety factor can also be defined in terms of design overload divided by normal expected load, where the design overload is defined as being just sufficient to cause failure. In most situations, the two definitions of safety factor are equivalent. For example, if the material has significant strength of 200 MPa and the significant stress is 100 MPa, the safety factor is 2. Looking at it either way, looking at it the other way, the design overload needed to bring the stress up to the limiting value of 200 MPa is twice the expected normal load, thus giving a safety factor of 2. Although the distinction between EQS 6.9 and 6.10 may seem trivial, it is recommended that the design overload concept 6.10 be used. These are always valid, whereas there are instances where EQ 6.9 cannot be properly applied. For example, consider the design of a slender column for a safety factor 2. Figure 6.15 shows how load and stress increase to buckling failure and where operation and safety factor of 2 would be calculated both ways. The discrepancy is due to non-linearity of the load stress curve. It is clear which interpretation is most conducive to the engineer's peace of mind. Another example in support of the design overload concept concerns the general case of fatigue loading, which consists of a combination of mean and alternating loads. The kind of overload most likely to occur may involve increasing either or both of these load components. The design overload concept permits of the safety factor to be computed with respect to whatever kind of overload is of interest. A word of caution: it follows from the preceding comments that there are instances in which the safety factor is ambiguous. It is therefore necessary to be sure that it is clearly defined in all cases for which there could be ambiguity. Chapter 6.12 Safety Factors Selection of Numerical Value. After going as far as is practical in determining the significant strength of the actual fabricated part of the part and the details of loading to which it will be subjected, there always remains some margin of uncertainty that must be covered by a safety factor. The part must be designed to withstand a design overload somewhat larger than the normally expected load. In the last analysis, selection of the safety factor comes down to engineering judgment based on experience. Sometimes these selections are formalized into design codes covering specific situations. For example, the ASME pressure vessel codes, the various building codes, and the stipulated safety factors or values in legal contracts covering the design and development of special machines. Safety factors are often embodied into computer programs or software for the design of specific components. Then the responsibility for making the engineering judgment falls upon the engineer responsible for the code or computer software, but only partly so because the engineer using the code or software must be satisfied that this detail of the code or software is indeed appropriate for the particular application. Chapter 6.12.1 Factors in the Selection of a Safety Factor. The selection of an appropriate value of the safety factor is based primarily on the following 5 factors. Degree of uncertainty about loading. In some situations, loads can be determined with virtual certainty. The centrifugal forces in the rotor of an alternating current motor cannot exceed those calculated for synchronous speed. The loads acting on the engine valve spring are definitely established by the valve open and valve closed positions. But what loads should be used for the design of an automotive suspension component whose loads can vary tremendously depending on the severity of use and abuse? And what about a comparable situation in a completely new kind of machine for which there are no previous experience to serve as a guide? The greater the uncertainty, the more conservative the engineer must be in selecting an appropriate design overload or safety factor. 2. Degree of uncertainty about material strength. Ideally, the engineer would have available or extensive data pertaining to the strength of the material as fabricated into the actual parts and tested at temperatures and environments similar to those actually encountered. But this is seldom the case. More often, the available material strength data pertain to the sample smaller than the actual part, which have not experienced any cold working in part fabrication, and which have been tested at room temperature in ordinary air. Moreover, there is bound to be some variation in strength from one test specimen to another. Sometimes the engineer must work with material test data for which such information as specimen size and degree of data scatter, and the relationship between the reported single value and the total range of scatter are unknown. Furthermore, the material properties may sometimes change significantly over the service life of the part. The greater the uncertainty about all these factors, the larger the safety factor must be used. Uncertainties in relating applied loads to material strength via stress analysis. At this point, the reader is already familiar with the number of possible uncertainties, such as validity of the assumptions involved in the standard equations for calculating nominal stresses, accurately in determining the effective stress concentration factors, accurately in estimating residual stresses, if any, introduced in fabricating the part, and suitability of any failure theories and other relationships used to estimate significant strength from available laboratory strength test data. Consequences of failure, human safety and economics. If the consequences of failure are catastrophic and relatively large, safety factors must of course be used. In addition, if the failure of some relatively inexpensive part could cause extensive shutdown of a major assembly line, simple economics dictates increasing the cost of this part several-fold in order to virtually eliminate the possibility of its failure. An important item is the nature of a failure. If a failure is caused by ductile yielding, the consequences are likely to be less severe than if caused by brittle fracture. Accordingly, safety factors recommended in handbooks are invariably larger for brittle materials. Cost of providing a large safety factor. This cost involves a monetary consideration and may involve important consumption of resources. In some cases, a safety factor larger than needed may have serious consequences. A dramatic example is a hypothetical aircraft with excessive safety factors making it too heavy to fly. With respect to the design of an automobile, it would be impossible to increase safety factors in structural components to the point that a maniac driver could hardly cause a failure even when trying. But to do so would penalize sane drivers by requiring them to pay for stronger components than they can use. More likely, of course, It would motivate them to buy competitors' cars. Consider the situation. Should an automotive engineer increase the cost per car by $10 in order to avoid 100 failures in a production run of 1,000,000 cars, where the failures would not involve safety but would entail a $100 repair? That is, should be 10 million to be spent to save 10,000 plus some customer inconvenience. A key point in safety factor is balance. All parts of the machine or system should have consistent safety factors. Components that might possibly cause human injury or entail major costs should have the greatest safety factors. Components that are comparable in these respects should generally have about the same safety factor, and so on. In fact, balance is perhaps the key to proper safety factor selection. Balance based on good engineering judgment, which is in turn based on all available information and experience. Chapter 6.12.2 Recommended values for a safety factor. Man, I hate reading numbers. Oh my god, couldn't they just do like ABC, like, why switch from the numerical system to the English system? It's like, throws me off. I would have stopped reading, but it's okay. We continue. Having read through this much philosophy of safety factor selection, the reader is entitled to have at least a guide, some suggestions for ballpark values of safety factor that has been found useful. For this purpose, the following recommendations of Joseph Vidosic are suggested. These safety factors are based on yield strength. SF equals 1.25 to 1.5 for exceptionally reliable materials and under controllable conditions, and subjected to loads and stresses that can be determined with certainty, used almost invariably where low weight is particularly important consideration. SF equals 1.2 to 2 for well-known materials under reasonably constant environmental conditions, subjected to loads and stresses that can be determined readily. SF2 to 2.5 for average materials operated in ordinary environments. S2.5 to 3 for less tried materials or for brittle materials under average conditions of environment, load, and stress. 3 to 4 for untried materials under average conditions of environment, load, and stress. 3 to 4 should also be used when better known materials that are used in uncertain environments are subjected to uncertain stresses. Repeated loads. The factors established in 1 to 6 are acceptable but must be applied to endurance limit rather than yield strength of the material. Impact forces. The factors given in terms 3 to 6 are acceptable, but an impact factor should be included. Brittle materials, where the ultimate strength is used as theoretical maximum, the factors presented in items 1 to 6 should be approximately doubled, where higher factors might appear desirable. A more thorough analysis of the problem should be undertaken before deciding their use. Chapter 6.13 Reliability. A concept closely related to safety factor is reliability. If 100 identical parts are put into a service and 2 fail, then the parts prove to be 98% reliable. Although the reliability concepts find considerably more application with parts subjected to wear and fatigue loading, we introduce it here in simpler context of the static loading. The usefulness of the reliability approach depends on having adequate information on the statistical distribution of loading applied to parts in service, from which can be calculated the significant stress and the significant strength of the production runs of manufactured parts. Figure 6.16 shows hypothetical distribution curves for significant stress and for the corresponding significant strength. The mean value of strength is 70 and the mean value of stress is 40. This means that if an average part of the production run were to put into service under average conditions of loading, there would be a margin of safety of 30. However, the unshaded area of the curve indicates that there are some possibility of a weak part being installed in a particular severe application, in which case failure would occur. Thus, even the margin of safety is on average 30. In a few instances, the margin of safety will be negative and failure expected. 6.17 shows corresponding plot of the distribution of margin of safety. In some instances, interest would be focused on the size of the unshaded area in the left indicating failures. In order to obtain quantitative estimates of the percentage of anticipated failures from a study like the preceding, we must look into the nature of distribution curves for significant stress and strength. We will consider here only the case involving normal or Gaussian distributions. Although this is only one of the mathematical models sometimes found best suited to the actual cases, it is probably the most common. The normal distribution function is commonly credited to Gauss, but was also discovered independent by two 18th century mathematicians, Laplace and De Moivre. Several normal distribution curves are plotted in figure 6.18. They have the equation where px De Moivre, such a uncanny valley name. I'm not used to it. Okay, it's the probability density function mu is the mean value of the quantity, and sigma the standard deviation. One limitation of this mathematical model for many applications is the fact that the curve extends asymptotically all the way to plus and minus infinity. Since the probability that any individual value of x will fall between plus and minus infinity is 1, the area under each of the curves 6.18 is unity. Likewise, the probability between the value of x would be between any specific values x1 and x2 is equal to the area under the curve between x1 and x2 as shown in figures 6.18. Varying mu with constant sigma merely shifts the curve to the right or left. Varying sigma with constant mu changes the shape of the curve, as shown in 6.18. Standard deviation sigma can be thought of the standard index dispersion or scatter of the particular quantity. Mathematically, mu and sigma is defined by mu equals mean equals 1 divided by n summation n I equals 1 xi. Normal distribution curves having a common mu and various sigma. Figure 6.19 illustrates a particularly useful property of all normal distribution curves. 68% of the population represented fall within the band mu plus minus 1 sigma. 95% fall within the band mu plus minus 2 sigma, and so on. Percentages of the population corresponding to any portion of the distribution can be determined from figure 6.20. Alternately, the reader may use the normal distribution table in Appendix H. 6.15 Interference theory of reliability prediction. The interference theory of reliability prediction has already been illustrated by interference or shaded area of the overlap in figure 6.16 and by figure 6.17. The margin of safety z is given by z equals x minus y. It can be shown that mu z equals mu x minus mu y. And by definition, the probability of failure is p parentheses z is less than 0. If the strength x and y are normally distributed, then it can be shown that the margin of safety z also has a normal distribution. Cool. Chapter 7.1 impact. Introduction. The previous chapters have dealt with almost exclusively with static loading. We now turn to the more commonly encountered case of dynamic loading. Dynamic loading includes both impact and the subject of this chapter, and fatigue, which will be introduced in chapter 8. Impact loading is also called shock, sudden, or impulsive loading. The reader has inevitably experienced and observed many examples of impact loading: driving a nail or stake with a hammer, breaking up a concrete with an air hammer, automobile collisions, dropping of cartons by freight handlers, raising of buildings with an impact ball, automotive wheels dropping onto potholes, and so on. The impact loads may be divided into 3 categories in order of increasing severity. 1. Rapid moving loads of essentially constant magnitude as produced by a vehicle crossing a bridge. Suddenly applied loads such as an explosion or from combustion of an engine cylinder. And 3. Direct impact loads as produced by a pile driver, drop force, or vehicle crash. These are illustrated schematically in figure 7.1. In 7.1a, mass M is held so that it just touches the top of spring K and it is suddenly released. Dash pot C adds a frictional supporting force that prevents the full gravitational force mg from being applied to the spring immediately. In figure 7.1b, there is no dash pot, so the release of mass m results in an instantaneous application of full force mg. 7.1c, not only is the force applied instantaneously, but the mass acquires kinetic energy before it strikes the spring. The significant thing about the dash pot action in 7.1a is the result of the gradual application of load mg. If the load is applied slowly enough, it can be considered as static. The usual way of distinguishing between impact and static loading in this situation is to compare the time required for applying the load with natural period vibration of the undampened mass on the spring. If time required to apply the load is greater than the 3 times the natural period, dynamic effects are negligible and static loading may be assumed. If the time of loading is less than half the natural period, there is definitely an impact. Of course, there is gray area between. See Table 7.1. Impact loads can be compressive, tensile, bending, torsional, or a combination of these. The sudden application of a clutch or striking of an obstruction by the bit of an electrical drill are examples of torsional impact. An important difference between static and impact loading is that the statically loaded parts must be designed to carry loads, whereas the parts subjected to impact must be designed to absorb energy. Material strength properties usually vary with speed of load application. In general, this works out favorably because both the yield and ultimate strength tends to increase with speed of loading. One of the problems in applying a theoretical analysis of impact to actual engineering problems is often the times rates of load application and train development can only be approximated. This sometimes leads to empirically determined stress and impact factors together with the static strength properties of the material. The practice works out well when good empirical data are available and applied closely to the part being designed. An example of use of stress impact factor for designing automobile suspension parts, even when the use of these empirical factors is justified, is important for an engineer to have a good understanding of basic fundamentals of impact loading. Chapter 7.2. Stress and deflection caused by linear and bending impact. Figure 7.3 shows an idealized version of freely falling mass with impacting a structure. To derive from 7.3 the simplified equation for stress and deflection, the same assumptions are made when deriving the equation for natural frequency of a simple spring mass system. The mass of a structure is negligible. Deflections within the mass itself are negligible, and dampening is negligible. These assumptions have some important implications. The first assumption implies that dynamic deflection curve is identical to that caused by the static application of the same load multiplied by impact factor. In reality, the dynamic deflection curve inevitably involves points of higher than local strain than does the static curve. Some deflection must inevitably occur within the impacting mass itself. To the extent that it does, a portion of the energy is absorbed within the mass, thereby causing the stresses and deflections in the structure to be little lower than the calculated values. Any calculated case involves some friction happening in the form of windage, rubbing of mass on the guide rod and spring end of the spring, and internal friction within the body of deflecting structure. This dampening can cause the actual stresses and deflections to be significantly less than those calculated from the idealized case. Keeping the above limitations in mind, the following analysis of the idealized case provides an understanding of basic impact phenomena, together with equations that are very helpful as a guide in dealing with linear impact. In figure 7.3, the following mass such that it has a weight W, the structure is assumed to respond to impact elastically with a spring constant of K. The maximum value of deflection is due to impact squiggly. F is defined as the equivalent static force that would produce the same deflection squiggly, that is Fe equals K times squiggly. The static deflection exists after the energy is damped out, the weight comes to rest. The structure is designated by squiggly St, where squiggly St is weight divided by K, spring constant. Cool. Chapter 7.2.1 Linear impact of straight bar in tension or compression. An important special case of linear impact is the straight rod or bar impacted in compression or in tension. The tensile case is illustrated schematically in 7.4a. The tensile rod sometimes takes the form of a bolt. If the impact load is applied concentrically, and if stress concentration can be neglected, then we can substitute into 7.4b the elementary expressions, and where A and L are the rod cross-sectional area and length respectively. The resulting equation is where V is the volume of the material rod. Note the important implication of 7.5 in the stress developed in the rod is a function of its volume irrespective of whether the volume is made up of a long rod of small area or a short rod of large area. This shows the impact energy capacity of straight rod to be a remarkably simple function of its volume, its modulus of elasticity, and the square of the allowable stress. Despite the importance of this basic relationship, it should be emphasized that 7.5 and 7.5a may in practice give results that are considerably optimistic, that is, give a calculated stress lower than the actual peak stress and correspondingly a calculated energy capacity greater than what actually exists. The main reasons of this are the stresses are not uniform throughout the member. The impacted member has mass. The inertial resulting from the rod mass causes the impacted end of the rod to have a greater local deflection, hence stress, than it would if inertia effects did not prevent the instantaneous distribution of deflection throughout the length of the rod. The effect of stress razors is considered in section 7.4. The quantitative effect of the mass of the struck member is left for more advanced works. Interesting. Chapter 7.3 Stress and deflection caused by torsional impact. Hour 5. Take a 5-minute break. I forgot the time, 5 minutes. Let's do 4 minutes for now. Fuck it. I gotta follow it. Gotta wait 1 more minute. Fix my hair. Okay, chapter 7.3 Stress and deflection caused by torsional impact. The analysis of preceding section can be repeated for the case of torsional systems and a corresponding set of equations developed. Instead, advantage will be taken of the direct analogy between linear and torsional systems to write the final equations directly. The analogous quantities involved are linear and torsional variables. Cool. Figure 7.8 shows the tensile impact bar as 7.4a. Except the recognition is given to the fact that stress concentration exists at the end of the bar. As with static loading, it is possible that the local yielding would redistribute the stresses so as virtually nullify the effect of stress razor. But under impact loading, the time available for plastic action is likely to be so short that brittle fracture will sometimes occur even in a material that exhibits ductile behavior in the tensile test. In terms of discussion, in 6.2, adding a stress razor and applying an impact load are both factors tending to raise the transition temperature, that is, cause brittle fracture without dropping to as low a temperature. Because of the difficulty in predicting impact notches affect their theoretical considerations, standard notch impacts are used, such as the Charpy and IZOD. These two have their limitations, where notched impact strength varies markedly with size, shape, and nature of impact. Because of this, the special laboratory tests are more closely simulate actual conditions are sometimes used. Chapter 8, Fatigue. Tell me about it. Chapter 8.1. Until the middle of the 19th century, engineers treated fluctuating or repeated loading the same as static loading, except for the use of larger safety factors. The use of term fatigue in these situations appears to have been introduced by Poncelet of France in the book published in 1839. Modern authorities suggest that the term progressive fracture would perhaps have been more appropriate. Fatigue fractures begin with a minute crack at a critical area of high local stress. This almost always at geometric stress razor. Additionally, minute material flaws or pre-existing cracks are commonly involved. An inspection of the surfaces after final fracture often reveals where the crack has gradually enlarged from one beach mark to the next until the section is sufficiently weakened that final fracture occurs on one final load application. This can happen when the stress exceeds the ultimate strength, with fracture occurring as a static tensile test. Usually, however, the final fracture is largely brittle and takes place in accordance with the fracture mechanics concepts treated in section 6.3 and 6.4. In figure 8.1, the curvature of the beach marks serves to indicate where the failure originates. By repeatedly pressing together and separating of the mating crack surfaces, this contrasts with the relatively rough final fracture. A distinguishing characteristic of the fatigue fracture of a ductile material is that little, if any, macroscopic distortion occurs during the entire process, whereas failure is caused by a static overload produces gross distortion. Chapter 8.2 Basic Concepts. Extensive research over the last century has given us a partial understanding of the basic mechanisms associated with fatigue failures. Reference 3 contains a summary of much current knowledge as it applies to engineering practices. Fatigue failures results from repeated plastic deformation, such as breaking a wire by bending it back and forth repeatedly without repeated plastic yielding. Fatigue failures cannot occur, whereas a wire can be broken in a few cycles of gross plastic yielding. Fatigue failures typically occur after 1,000 or even a million cycles of minute yielding that often exists. Cool. Cause. Origin and only on a microscopic level, fatigue failure can occur at stress levels far below the conventionally determined yield point or elastic limit. Because highly localized plastic yielding can be the beginning of fatigue failure, it behooves the engineer to focus attention on all potentially vulnerable locations such as holes, sharp corners, threads, keyways, surface scratches, and corrosion. Such a location is shown at the root of a notch. If the local yielding is sufficiently minute, the material may strain strength, causing the yielding to cease. The part will then have actually benefited from this mild overload. But if the local yielding is any more than this, the repeated load cycling will cause a loss of local ductility until the cyclic strain imposed at the vulnerable spot in question can no longer be withstood without fracture. The initial fatigue crack usually results in increasing local stress concentration. As the crack progresses, the material at the crack root at any particular time subjected to destructive localized reverse yielding. As the crack deepens, thereby reducing the section and increased stresses, the rate of crack propagation increases until the remaining section is no longer able to support a single load of application, and final fracture occurs, usually in accordance with the principles of fracture mechanics. Present engineering practices relies heavily on the wealth of empirical data and that has accumulated from fatigue tests of numerous materials in various forms and subjected to various kinds of loading. The remainder of this chapter is based largely on these data. The next section describes the standardized R&R Morg fatigue test, which is used to determine the fatigue strength characteristics of materials under a standardized and highly restricted set of conditions. After the pattern of results obtained from this test has been reviewed, the succeeding section deals with effects of deviating from the standard test in various ways, thus working towards the completely general case of fatigue in orderly fashion. The generalizations or patterns of fatigue behavior developed in the remainder of this chapter enable the engineer to estimate the fatigue behavior of combinations of materials, geometry, and loading for what test data are not available. This estimating of fatigue behavior is an extremely important step in modern engineering. The preliminary design of crucial parts normally encompasses this procedure. The prototypes of preliminary design are built and fatigue tested. The results provide a basis refining of the preliminary design to arrive at the final design suitable for production. Chapter 8.3 Standard fatigue strengths for rotating bending. Figure 8.3 represents a standard R&R rotating beam fatigue testing machine. The reader should verify the loading is imposed by four symmetrically located bearings that cause the center portion of the specimen to be loaded per bending, and that the stress at any point goes through a cycle of tension to compression to tension with each shaft rotation. The highest level of stress is at the center, where the diameter is a standard 0.300 inch. The large radius of the curvature prevents a stress concentration. Various weights are chosen to give it the desired stress levels. The motor speed is usually 1,750 RPM. When the specimen fails, the weight drops. Opening contact point C. which stops the motor, and the number of cycles to failure is indicated by the revolution counter. Cool. I don't want to read this, but I'll read it. This is not that cool. Afterwards, a series of tests made in various weights and using test specimens carefully made as nearly identical as possible gives results are plotted as SN curves, as illustrated in 8.4. SN curves are plotted either on a semi-log or log-log coordinates. Note that the intensity of the reverse stress causing failure of a given number cycle is called the fatigue strength, corresponding to the number of load cycles. Numerous tests have established various materials that have endurance limit defined at the highest level as alternating stress that can withstood indefinitely without failure. The usual symbol of this endurance limit is Sn, designated as Sn S prime n, as in 8.4, where the prime indicates a special case of standard tests illustrated in 8.3. Log-log coordinates are particularly convenient for plotting various Sn curves because of the straight line relationship shown. 8.4c illustrates the knee of SN curves for the material type, clearly defines the endurance limit. This knee normally occurs between 10 to the 6 to the 10 to the 7 cycles. It is customary to make the conservative assumption that the various materials must not be stressed above the endurance limit if life of 10 to the 6 or more cycles is required. This assumption is illustrated in the generalized S to the N curve, where steel is shown in Figure 8.5. Because the fatigue failures originate at local points of the relative weakness, the results of fatigue tests have considerably more scattered than do all of these static tests. For this reason, the statistical approach to defining strength takes on greater importance. The standard deviations of endurance limit values are commonly in the range of 4 to 9% of the nominal value. Ideally, the standard deviation is determined by experimentally from a test corresponding to the specific application. Often 8% of the nominal endurance limit is used to conservative estimate of standard deviation when more specific information is not available. The static scatter illustrated in Figure 8.4 is typically for carefully controlled tests. The scatter band marked on 8.4 illustrates the interesting point. The scatter in the fatigue strength corresponding to a given life is small. The scatter and fatigue life corresponding to a given stress level is large. Even in carefully controlled tests, these life values can vary over a range of 5 or 10 to 1. A multitude of standard fatigue tests have been conducted over the last few decades, with results tending to conform to the certain generalized patterns. The most commonly used of these is shown in 8.5. With knowledge of the ultimate tensile strength, a good approximation of the compute SN curved steel can be quickly made. Furthermore, tensile strength can be estimated on non-destructive hardness tests. For steels, the tensile strength PSI is 500 times the Brinell hardness. Hence, the conservative estimate of endurance limit is about 250 HB. The latter relationship can be counted only up in Brinell hardness values about 400. The endurance limit may or may not continue to increase for greater hardness depending on the composition of steel. Although the 10 to the 3 cycle fatigue strength in Figure 8.5 is computed as being 90% of the ultimate strength, the actual stress is not that high. The computed reasons that fatigue strength values corresponding to test points in 8.4 are computed according to the elastic formula sigma mc divided by I. Large loads enough to cause failure in 1,000 cycles usually cause significant yielding, resulting in actual stresses that are lower than calculated values. The point is illustrated in 8.7. The fatigue strength characteristics of cast iron are similar to those of steel. The assumption that endurance limits corresponds about 0.4 times the ultimate strength. Representative SN curves for various aluminum alloys are shown in Figure 8.8. Note that the absence of sharply defined knee and true endurance limit. This is typical of non-ferrous metals. In absence of endurance limit, the fatigue strength of 10 to the 8 or 5 times 10 to the 8 cycles is used. For typical raw aluminum alloys, 0.5 times 10 to the 8 cycle fatigue strength is related to the static tensile strength indicated in figure 8.9. Typical S to the N curves for magnesium alloys are shown in 8.10. The 10 to the 8 cycle fatigue strength is about 0.35 times the tensile strength for most wrought and cast alloys. For most copper alloys, the ratio of 10 to the 8 cycle fatigue strength to static tensile strength ranges between 0.25 and 0.5. For nickel alloys, the ratio of these strengths usually between 0.35 and 0.5. Titanium and nickel alloys behave like steel, and like they tend to exhibit a true endurance limit in the range of 10 to the 6 and 10 to the 7 cycles, with endurance limit between 0.45 and 0.65 times the tensile strength. Chapter 8.4 Fatigue strength for reverse bending and reverse axial loading. If a test specimen similar to the one used in R.R. Moore's testing machine is not rotated but mounted horizontally with one fixed end and the other pushed alternatively up and down, reverse bending stresses are produced. These differ from stresses caused by rotating bending that only the maximum stresses are limited to the top and bottom, whereas rotating bending produces maximum stress all around the circumference. In rotating bending, a fatigue failure will originate from the weakest points of surface. In reverse bending, there is excellent statistical probability that the weakest point will not be at exactly top or bottom. This means that the fatigue strength of the reverse bending is usually greater than rotating bending. The difference is small and usually neglected. Thus, for problems involving the reverse bending, the small error on the conservative side is deliberately introduced. Similar reasoning indicates that the reverse axial loading, which subjects the entire cross-section, should give lower fatigue strength than rotating and bending. This is indeed the case, and the difference should be taken into account. Axial or push-pull tests give endurance limits about 10% lower than the rotating bending. Furthermore, if the supposedly axial load is just a little bit off-center, slight bending is introduced, which causes the stresses in one side to be a little higher than P/A. Ideally, one would determine the load eccentricity and calculate the peak alternating stress as P divided by A, MC divided by I, but the magnitude of the unwanted eccentricity is often not known. In such cases, it is customary to make this into account by using only the P divided by A stress and reducing the rotating bending endurance limit by more than 10%. Since the reduction of 10% or more endurance limit for rotating bending is associated with differences in stress gradient, we will take this into account by multiplying the basic endurance limit S prime n by gradient factor and a gradient constant, where CG 0.9 for pure axial loading of precision parts and CG ranges from perhaps 0.7 or 0.9 of axial loading non-precision parts. Stress gradient is also responsible for the 10 to the 3 cycle fatigue strength being lower for the axial loading than bending materials. Recall from figure 8.7 that the 0.9 SU strength where rotating bending was in most cases artificially calculated but value neglected but affect yielding at the surface. Yielding cannot reduce the surface stress. In the case of axial loading, accordingly, tests indicate that the 10-3 cycle strength for this loading is about 0.75 S mu. The preceding points are illustrated in figure 8.11. The top two curves in figure 8.11 show comparative estimates of the S-N curves for bending axial loading. The bottom curve in figure 8.11 shows the comparative estimated S-N curve for torsion loading. For axial fatigue, another possible approach is to rely on data MIL HDBK5J. Among the data MIL HDBK5J are S-N data points, and the associated curve fits from many different metals including steel, aluminum, and titanium. The loading consists of both fully reverse axial fatigue and axial fatigue with non-zero mean stress. In some cases, the stress concentrations are also included. It should be noted that MILHDBK5J only presents axial fatigue data, and other types of fatigue testing, such as bending and torsion, are seldom used for aerospace applications. Chapter 8.5 Fatigue Strength for Reversed Torsional Loading. Since fatigue failures are associated with highly localized yielding, and since yielding of ductile materials have been found to correlate well with distortion and energy theory, it's perhaps not surprising that theory has been found useful in predicting the endurance limit of ductile materials under various combinations of reverse biaxial loading, including torsion. This is illustrated in Figure 8.12. Thus, for ductile materials, metals, the endurance limit in reverse torsion is about 58% of the endurance limit in reverse bending. This is taken into account by multiplying the basic endurance limit S prime n by a load factor of CL of 0.58. Since torsional stresses involve stress gradients similar to bending, it is not surprising that as in bending, the 10 to the 3 cycle fatigue strength is generally about 0.9 times the appropriate ultimate strength. Thus, for reverse torsion, the 10 to the 3 cycle strength is approximately 0.9 times the ultimate shear strength. The experimental values for ultimate torsional shear strength should only be used if they are available. If not, they may be roughly approximated as the bottom SUS 0.8 SU for steel. The bottom curve of Figure 8.11 shows the estimated torsional SN curve for the steel based on the preceding relationships. There are fewer data available to support a generalized procedure for estimating the torsional S to N curves for brittle materials, and this makes it all the more desirable to obtain the actual experimental fatigue data for specific material and loading condition in the problem at hand. In the absence of such data, torsional SN curves for brittle materials are sometimes estimated on the basis of assuming the endurance limit of 10 to the 6 cycles and 0.8 times the standard reverse bending endurance limit, and assuming a 10 to the 3 cycle strength of 0.9 SUS, the same for ductile materials. Alright. 527. Chapter 8.6 Fatigue Strength for Reverse Biaxial Loading. Figure 8.12 illustrates the good general agreement of the distortion energy theory with the endurance limit of ductile material subjected to all combinations of reversed biaxial loading for shorter life fatigue strengths in ductile materials, and for brittle materials we are not only in a good position to make fatigue strength predictions without the benefit of directly applicable experimental data. With this reservation in mind, the following procedure is tentatively recommended. For ductile materials use distortion energy theory to convert from the actual load stresses to an equivalent stress that is regarded as a reversed bending stress. Then proceed to relate the stress to the fatigue properties of the material. In reversed bending, for brittle materials, use Moore theory to obtain an equivalent reverse stress that is regarded as a reverse bending stress, and relate this to the bending fatigue properties of the material. A convenient graphical procedure for determining the equivalent bending stress is to draw sigma 1 minus sigma 2 plot like in 6.11b for a material, and then plot the point corresponding to actual reverse stresses. Next, draw a line through the point in a parallel to the failure line. The intersection of the line sigma 1 Chapter 8.7 Influence of surface and size on fatigue strength. Surface factor. Up to this point, all discussions of fatigue strength have assumed the surface to have special mirror polish finish. This requires a costly laboratory procedure but serves to minimize surface scratches and other geometric irregularities acting as a point of stress concentration. Any differences in metallurgical character of the surface layer and material in the interior, and any residual stresses produced by the surface finishing procedure. Normal commercial surface finishes usually have localized points of greater fatigue vulnerability. Hence, the commercially finished parts have lower fatigue strengths. The amount of surface damage caused by the commercial processes depends not only on the process but the susceptibility of material to damage. Figure 8.13 gives estimated values of surface factor (CS) for various finishes applied to steels of various hardnesses. In all cases, the endurance limit for the laboratory polished surface is multiplied by CS to obtain the corresponding endurance limit for commercial finish. It is standard practice not to make any surface correction for the 10 to the 3 cycle strength. The reason being that this is to the strength for static loads, and static strength of ductile parts is not significantly influenced by surface finished. The surface factor for ordinary grade cast iron is approximately 1. The reason for this is that even the mirror polish samples have surface discontinuities because of the graphite flakes in the cast iron matrix, and that adding even rather severe surface scratches does not make the situation much worse, if any. Unfortunately, there is little published information on the surface factors for other materials. For critical parts, actual fatigue tests of the material and surface in question must be conducted. Chapter 8.7.2 In section 8.4, it was pointed out the endurance limit for reverse axial load is about 10% lower for reverse bending because of stress gradient. For the 0.3 inch diameter bending specimen, the rapid drop in stress level below the surface is somehow beneficial. The 0.3 inch diameter axial specimen does not enjoy this benefit. A comparison of how stress gradients in 8.14a and b show that large specimens in bending or torsion do not have the same favorable gradients as the standard 0.3 inch specimen. Experiments show that if the diameter is increased to much more than 0.4 inch, most of the beneficial gradient effect is lost. Hence, parts that are more than 0.4 inch in diameter and that are subjected to reverse bending or torsion should carry a gradient factor Cg of 0.9, the same as parts subjected to axial loading. 8.14c shows that very small parts have even more favorable gradient than the standard RR more specimen. Thus, we might expect the endurance limit for such parts to be greater than for 0.3 inch diameter parts. Sometimes this has been found to be the case, but unless specific data are available to substantiate this increase, it is best to use a gradient factor of unity for these small parts. Consider the question of what gradient factor to use when the bending of a rectangular section, say 6 mm by 12 mm. If the bending is about the neutral axis that places tension and compression surfaces 6 mm apart, use Cg equals 1. If the tension and compression surfaces are 12 mm apart, use Cg equals 0.9. Thus, the gradient factor is determined to be the basis of an equivalent round section having the same stress gradient as the actual part. Recall that a gradient factor 0.9 was specified for all axially loaded parts because the stress gradient is unfavorable, regardless of size. Parts with sections larger than about 50 mm equivalent diameter are usually found to have lower endurance limits than those computed using the gradient factors recommended previously. This is due in part to metallurgical factors such as hardenability, for the interior of large section parts is usually metallurgically different from the surface metal. The extent to which the endurance limit of very large parts is reduced varies substantially. The generalizations are hardly warranted. If the part in question is critical, there is no substitute for pertinent test data. A very rough guide for the value sometimes used in Table 8.1. The foregoing recommended consideration of specimen size focused on the effect of size on stress gradient. It should be noted that more extensive treatment of the subject would consider other facets. For example, the larger the specimen, the greater the statistical probability that a flaw of given severity will exist somewhere near the surface or somewhere within the entire body of material. In addition, the effects of processing on metallurgical factors is often more favorable for smaller parts, even in the size range below 50 mm equivalent diameter. Chapter 8.8 Summary of estimated fatigue strengths for completely reversed loading. The foregoing sections have emphasized the desirability of obtaining actual fatigue test data that pertain as closely as possible to the application. Generalized empirical factors were given for use when such data are not available. These factors can be applied with greatest confidence to steel parts because most of the data they were based came from testing steel specimens. 5 of these factors are involved in the estimate for the endurance limit, as n equals s prime n, cl, cg, cs, ct, cr. The temperature factor Ct accounts for the fact that the strength of a material decreases with increased temperature, and the reliability factor Cr acknowledges that a more reliable estimate of the endurance limit requires using a lower value of endurance limit. Table 8.1 gives a summary of all factors using the estimate of the fatigue strength of ductile materials. It serves as a convenient reference for solving problems. Chapter 8.9 Effect of mean stress on the fatigue strength. Machine and structural parts seldom encounter completely reversed stresses. Rather, they typically encounter fluctuating stresses that is a combination of static plus completely reversed stress. A fluctuating stress is usually characterized by its mean and altering components. However, the terms maximum stress and minimum stress are also used. All 4 of these quantities are defined in figure 8.15. Note that any two of them are known. The others are readily computed. This text uses primarily mean and alternating stress components. As in figure 8.16, the same information can be portrayed graphically with any combination of 2 stress components shown in figure 8.15. For example, sigma m and sigma max coordinates are often found in the literature. For convenience, some graphs use all 4 quantities. Figures 8.17 through 8.19. The existence of static tensile stress reduces the amplitude of reverse stress that can be superimposed. 8.20 illustrates this concept. Fluctuation A is completely reverse stress corresponding to the endurance limit. The mean stress is 0 and alternating stress Sn. Fluctuation fatigue. Fluctuation B involves a tensile mean stress. In order to have an equal fatigue life, the alternating stress must be less than Sn in going from B, C, D, E, F. The mean stress continually increases. Hence, the alternating stress must be correspondingly decreased. Note that in each case, the stress fluctuation is shown as starting from 0, and the stresses are computed P divided by A. Values. Microscopic yielding occurs even at A, as has previously been noted. Upon reaching D, macroscopic yielding begins. Although load fluctuations E and F give infinite life, the part is yielded at the first load application. Figure 8.16 gives convenient graphical representation of various combinations of mean and alternating stress in relation to criteria for both for yielding and various fatigue lives. It is often called a constant life fatigue diagram because it has lines corresponding to a constant 10 to the 6 cycle life, constant 10 to the 5 cycle life, and so forth. To begin the construction of this diagram, put on it first the information that is already known. The horizontal axis corresponds to static loading. Oh god. Okay. Yield and ultimate strengths are plotted at points A and B. For ductile materials, the compressive yield strength is negative Sy, and this is plotted at point A prime. If the mean stress is 0 and the alternating stress is equal to Sy, the stress fluctuates between plus Sy and minus Sy. All points along the line AA double prime correspond to fluctuations in having tensile peak of Sy. All points of A prime, A double prime correspond to compressive peaks equal to negative Sy. All combinations of sigma M and sigma A causing no yielding are contained within triangle A prime, A double prime. All Sn curves considered in the chapter corresponding to sigma M equals 0. Hence, we can read from these curves points like C, D, E, and F for any fatigue life of interest. Connecting these points with B gives an estimated line of constant life. This empirical procedure for obtaining constant life lines is credited to Goodman. Hence, the lines are commonly called Goodman lines. Laboratory tests have consistently indicated that compressive mean stresses do not reduce the amplitude of allowable alternating stress. If anything, they slightly increase it. Figure 8.16 is thus conservative in showing the constant life lines as horizontal to the left of points C, D, and so on. These lines apparently extend indefinitely as far as fatigue is concerned. The limitation is being only static compression failure. Detailed modifications of diagrams for various types of loading are given in figure 8.16. Let us observe the significance of various areas on the diagram. If a life of at least 6 to the 6 cycles is required and no yielding is permitted, we must stay inside the area A prime H times G times GA. If no yielding but less than 10 to the 6 cycles of life are required, we can also work within some or all of the area HCGA double prime H. If 10 to the 6 cycles of life are required but yielding is acceptable, area AGB may be used in addition to the area A prime HCGA. area above A double prime GB corresponds to yielding the first application load in fatigue fracture prior to the 10 to the 6 cycles of loading. The procedure for general biaxial loads given in 8.16 should be recognized as a substantial simplification of a very complex situation. It applies best to situations involving long life where the loads are all in phase, where the principal axes for mean and alternating stresses are the same, and where these axes are fixed with time. For illustration in which these conditions will be fulfilled, consider the example in 4.25 with the shaft stationary and with the 2,000 pound static load changed to a load that fluctuates between 1,500 and 2,500 pounds. The static stresses on element A would have been unchanged, but alternating stresses would be added. The alternating bending and alternating torsion would obviously be in phase. The principal planes for mean and alternating stresses would be the same, and these planes would remain the same as the load fluctuated. Chapter 8.10 Effects of Stress Concentration with Completely Reversed Fatigue Loading. 8.23 shows that SN curves, such as unnotched specimens and otherwise identical specimens, except for a stress razor. Unlike SN curves we will use, the stresses plotted are nominal stresses, that is, stress concentration is not taken into account. The specimen dimensions in the section where fatigue fractures occur are the same for both figures. 8.23a and b. Hence, any given load that causes the same calculated amount of stress in both cases, as shown in the figure, the ratio of a notch to notch endurance limit is fatigue stress concentration factor, designated as KF. Theoretically, we might expect KF to be equal to theoretical or geometric factor KT discussed in section 4.12. Fortunately, tests show that KF is often less than KT. This is apparently due to internal irregularities for the structure of the material. An ideal material would have internal stresses in the exact accordance of elastic theory. Actual material have internal irregularities causing local points to have higher stresses. Thus, even a notch sample suffer from these internal notches. Adding an external geometric notch to this material may not do as much additional damage as it would were the material itself perfect. An extreme case on point was ordinary gray cast iron. The internal stress razors caused by graphite flakes in the matrix are such that addition of a geometric stress razor has little or no effect. This means that in the material in 8.23 were one of the lower grades of gray cast iron, the two SN curves would nearly coincide. A material with uniform fine-grained matrix is highly sensitive to notches. Cast iron is insensitive to notches. The preceding situation is commonly dealt with a notch sensitivity factor Q, defined by the equation Kf equals 1 plus Kt minus 1 times Q, where Q ranges between 0 and unity. Thus, to determine the fatigue stress concentration factors from corresponding theoretical factors, we need to know the notch sensitivity of the material. The situation is a little more complicated than it appears because notch sensitivity depends not only on the material, but the relative radius of the geometric notch and dimensions of characteristic internal imperfections. Notch radii, so small that they approach the imperfection size, give zero notch sensitivity. That is indeed fortunate. Otherwise, even minute scratches on what would generally be called a smooth polished surface would disastrously weaken the fatigue strength. 8.24 is the plot of notch sensitivity versus notch radius for some common materials. Note that in all cases notch sensitivity approaches 0 as the notch radius approaches 0. Also note that the data for for steels illustrate the fundamental tendency for the harder and stronger materials to be more notch sensitive. That means that changing from a soft to a harder to and stronger steel normally increases part fatigue strength, but increases all not as great as it might be expected because of this increased notch sensitivity. 8.24 shows that a given steel is a little more notch sensitive for torsional loading than for bending and axial loading. For example, 0.04-inch radius notch in a 160 BHN steel part has a notch sensitivity of 0.71 if the loading is bending or axial, and about 0.76 if the load is torsional. Figure 8.23 shows that influence that the notch at 10 to the 3 cycles is considerably less than 10 to the 6 cycles. Some references advise neglecting and influence the stress razor at 10 to 3 cycles. Although the certain data supports this recommendation, a closer study indicates this is valid only for relatively soft metal. But for relatively hard and strong alloys, these same metals, the effect of the notch at 10 to the 3 cycles can be nearly as great as 10 to the 6. There is a fundamentally difficulty in analyzing notch effects at the low cycle end of curves like that in figure 8.23c. This is because the calculated nominal stress used on the plot does not relate very closely with the actual loading conditions imposed upon the local region and at the root of the notch where the fatigue correct starts. 8.2 shows an enlarged view of the notch region of a notch specimen. In figure 8.23b, the reverse loading is sufficient to cause fatigue failure after, say, 10 to the 3 cycles. Plastic yielding will occur through some small region at the base of the notch. This region contributes to the rigidity of the total part. Thus, the strengths within the zone are determined entirely by stable elastic resistance of the great bulk of material outside the zone. This means that during a fatigue test with constant maximum load, the maximal strain within a vulnerable zone will stay constant from cycle to cycle. The actual stress within a zone may vary widely with time, depending on the strain hardening or strain softening characteristics of the material. Hence, a meaningful study of the low cycle fatigue must deal with actual local strain rather than calculated nominal stress. This strain cycling approach is beyond our scope of this book. For our purposes, it is recommended that the full fatigue stress concentration factor KF be used in all cases. For relatively short situations, this may be overly conservative. Another question should be considered here. Is it better to treat KF as a stress concentration factor or as a stress reduction factor? Authorities differ on this point, but in this book, KF will be regarded as a stress concentration factor. Looking at 8.23, we could easily regard KF as a strength reduction factor and calculated a notch endurance limit as equal to S prime N CL CG CS CT CR divided by KJ. This would be correct, but it has the disadvantage of implying that the material itself is weakened by the notch. It is not, of course. The notch has merely caused higher local stresses. In addition, when we use the KF as a stress multiplier, SN curves and constant life fatigue strength curves are independent of notch geometry, and the same curves can be used repeatedly for members of various stress razors. Finally, for considering residual stresses caused by peak loads, it is necessary that KF be regarded as a stress concentration factor. Chapter 8.11 Effect of stress concentration with mean plus alternating loads. It was shown in section 8.4.14 In 4.15, that peak loads caused elastic stresses to yield strength, producing yielding and resultant residual stresses. Furthermore, the residual stresses always serve to lower the actual stresses when the same peak is applied again. To illustrate the effect of residual stresses on fatigue life, where mean and as well as alternating stresses are involved. Consider the examples developed in figure 4.43. Suppose the notch tensile bar is made of steel with SU equals 450 MPa, SY equals 300 MPa, and that its size and surface are such that the estimated constant life fatigue curves are shown at the bottom of 8.25. The top of 8.25 shows a fluctuation of notch stress calculated without taking yielding into account. The first 3 cycles correspond to the loading and unloading involved in 4.43a. The next 2 cycles represent progressively increasing the load to that involved in 4.43b. Note that these dotted cycles show an elastically computed stress at about the notch root of about 7 over 6 SY. Correspondingly, the 3 cycles drawn with solid lines at B. In figure 8.25 showed calculated stresses fluctuating between 0 and 400 MPa, which is 4 divided by 3 SY. This procedure continues along the top of figure 8.25 until the condition is shown in figure 4.43d is reached. Here the calculated stress is 0 when the load is off and 2 SY when it is on. Just below this figure 8.25 is a corresponding plot of actual stresses at the notch root. It is based on the assumption that the ductile material can be approximated by a flat top, idealized stress strain curve like the one drawn in 4.42e. No yielding occurs during the first 3 cycles at A, but yielding does occur at the notch root when the calculated stress exceeds 300 MPa during the first dotted cycle. A little more yielding takes place during each cycle and the load goes higher than it has previously. When the load is on during one of the cycles at B, the stress distribution corresponds to the solid line in the left drawing of 4.43. When the load is off, the stresses are 0, but correspond to the residual stress pattern in the right-hand drawing of 4.43. At the notch, these stresses range from SY when the load is on the residual strength minus SY divided by 3 when the load is off. This procedure continues on the actual notch stress figure of 8.25 until the condition shown in 8.43d is reached. Here, the actual notch of the root stress in SY and when the load is applied, and residual stress of minus SY when the load is off. At the bottom of figure 8.25, stresses resulting from on and off application of the figure 4.43 loads are represented in a comparison to the fatigue strength characteristics of the material. Points A, B, C, and D correspond to the calculated notch root stresses. Points A prime, B prime, C prime, D prime correspond to actual stresses and are fairly realistic. Note that in every case, yielding has reduced the mean stress and it does not change the alternating stress. On the basis of the plot in figure 8.25, the estimated fatigue libs corresponding to repeated application of various levels of tensile loading would be 10 to the 5 cycles for loading point A, perhaps 1.5 or 2 times 10 to the 4 cycles for loading B, about 6 to the times 10 to the 3 cycles for C, and about 2.5 times 10 to the 3 cycles for D. These estimates represent rough visual interpolations between adjacent constant life lines. The dotted line through point C prime illustrates a better procedure. This line is the Goodman line corresponding to some unknown life. All points on the line correspond to the same life. In particular, point C prime corresponds to the same life as completely reverse stress of 280 MPa. Now we can go to the SN curve and take from it the life corresponding to 280 MPa. To keep the matter of life predictions in proper perspective, remember that such predictions are inherently very rough, except on a statistical basis, as was illustrated by the scatter band of SN curve in figure 8.4c. Also, do not forget the previously mentioned limitations of procedure for making predictions is in the same low cycle range. In this example, stress concentration of the factor 2 originally used in 4.43 was taken as a fatigue stress concentration factor in figure 8.25. Assuming that the material has a notch sensitivity of Q of something less than unity, the theoretical stress concentration factor KT would be greater than 2. Such life predictions can be made conveniently from fatigue strength diagrams in the form of 8.17 through 8.19. On these diagrams, point A, B, C, and D would lie on the vertical axis, and points B prime, C prime, and D prime would lie on the horizontal axis line. Sigma max equals Sy. At first, we might be inclined to become a little alarmed with the appearance of points like B, C, and D on the sigma m minus sigma a plot. Even point C, let alone point D, shows a peak stress in excess of the ultimate strength. We must consider that these fictitious calculated stresses and of the extent that of yielding they represent is usually very small. With the tensile bar in this example, there is no way that very much yielding can occur at the top-notch root without yielding the entire cross section, and this is only the verge of happening at point D. In summary, the procedure recommended here for fatigue life prediction of notch parts subjected to combinations of mean and alternating stresses all stresses are multiplied by the fatigue stress concentration of factor Kf, and correction is made for yielding and resultant residual stresses if the calculated peak stress extends the material yield strength. This procedure is sometimes called the residual stress method because of the recognition it gives to the development of residual stresses. An alternative procedure sometimes used to apply to the stress concentration factor of the alternating stress only and not to take residual stress into account. We can see that in some cases this reduction in mean stress from not multiplying by Kf might be the same about the reduction in mean stress is achieved with the residual stress method by yielding and residual stress into account. Because the mean stress is not multiplied by a stress concentration factor, this alternate procedure is sometimes called the nominal mean stress method. Only the residual stress method is recommended here for fatigue life prediction. Chapter 8.12 Fatigue Life Prediction with Randomly Varying Loads. Predicting the life of parts stressed above the Nernst limit is a best rough procedure. This point is illustrated by the typical scatter band of 7 to 1 life ratio of figure 8.4c. For the large percentage of mechanical and structural parts subjected to randomly varying stress cycle intensity, the prediction of fatigue life is further complicated. The procedure given here for dealing with this situation was proposed by Palmgren of Sweden in 1924, and independently by Miner of the United States in 1945. The procedure is often called the linear cumulative damage rule, with the names of Miner, Palmgren, or both attached. Palmgren and Miner are very logically proposed to the simple concept that if a part is cyclically loaded at the stress level causing the failure in 10 to the 5 cycles, each cycle of this loading consumes one part in 10 to the 5 cycles life of the part. If other stress cycles are interposed corresponding to life of 10 to the 5 cycles, each of these consume one part in the 10 to the 4 of the life, and so on. When on this basis 100% of the life has been consumed, fatigue failure is predicted. The Palmgren or Miner rule is expressed by the following equation, which N1, N2, Nk represent the number of cycles at specific overstress levels. N1, N2, and Nk represent the life in these overstress levels as taken as the appropriate S to the N curve. The fatigue failure is predicted when N1 divided by N a bigger capitalized N1 plus N2 divided by N2 capitalized plus Nk divided by Nk capitalized equals to 1, or summation Nj divided by Nj capitalized equals to 1. Chapter 8.13 Effect of surface treatment on the fatigue strength of a part. Since fatigue failures originate from localized areas of relative weakness and that are usually used on the surface, the local condition of the surface is of particular importance. We have already dealt with the surface constant Cs for various categories of finishing operations, and this and the following two sections are concerned with the various surface treatments, given the specific regard to the influence on surface strength in comparison with the strength of subsurface material, the surface residual stress, all three surface considerations, geometry, smoothness, strength, and residual stress, are somewhat interrelated. For example, the low values of C5 shown in figure 8.13 for hot rolled and as forged subsurfaces are due partly to surface geometry and partly to decarburization of the surface layer. The influence of the surface strengthening and the creation of a favorable residual surface stress are illustrated in 8.31, which shows a notched bar that is symmetrically about the load axis. The notched bar is subjected to the external tensile force, which varies between 0 and P max. Curve A shows the stress gradient in the vicinity of a notch owing to a tensile load. Curve B shows the desirable residual stress gradient having the compression of the groove surface. Curve C shows total stress, the sum of curves A and B. Curve D shows the desirable strength gradient resulting from treatment causing the surface strengthening. Note that the surface strengthening and compressive residual stresses have substantially increased to the load that can be carried, and the point of potential failure origin has been moved under the surface point to point T, where curves C and D are tangent. This means that the surface of the groove could deteriorate in somewhat in service without reducing the load carrying capacity of the part. Further benefit to the fatigue strength is not evident in figure 8.31 is that compressive residual stresses shift the operating point on the mean stress alternating stress diagram to the left, which increases fatigue life. The concept of comparing strength gradients with total stress gradients provides ready explanation of the fact that parts have steep load stress gradients and poor surfaces. Benefit from surface treatment. Unnotched parts with axial loading benefit little. unless they have poor initial surface finishes. Severely notched parts loaded in bending or torsion benefit most, since practically all parts have critical areas of stress concentration. Surface strengthening treatments are usually quite effective. For example, 8.31 illustrates about a 60% increase in allowable load stress caused by the combination of surface strengthening plus residual stress. For applications involving bending or torsional loads, it is not uncommon for the fatigue load capacity to be more than doubled. The next two sections discuss processes for strengthening surfaces. It is also important to be aware of processes causing surface to weaken. Grinding, for example, is, if not performed carefully and with slow or moderate feel rates, could cause harmful subsurface residual tensile stresses and even minute surface cracks. Chrome and nickel plating, even though good for the surface in providing corrosion protection, can substantially reduce the endurance limit of steel parts by causing hydrogen gas to be absorbed. This is known as hydrogen embrittlement. This damage can be minimized by taking special care as in the low plating current densities and baking the parts after plating. Properly performed electroplating steel parts with soft metals like copper, cadmium, zinc, lead, and tin causes little, if any, fatigue weakening. Relatively, the little information available on the effect of electroplating and anodizing and various materials, both beneficial and harmful effects, have been reported in specific instances. Welding and flame cutting operations tend to provide harmful subsurface residual tensile stresses unless special precautions are taken, such as subsequent thermal stress relieving. The following list of few basic principles may help to place the subject of fatigue strengthening for surface treatments in proper perspective. The engineer concerned with the design and development of machine and structural components subjected to dynamic loads should seek to identify local areas of stress concentration where fatigue failures could conceivably start, review the possibilities for modifying the design to reduce stress concentration. For example, move the stress razor to an area of lower nominal stress. 3. Pay particular attention to the surface finish CS in these areas. 4. Consider what can be done in the manufacture of the part to strengthen the surface layer and provide a compressive residual stress at potentially critical stress razors. Chapter 8.14 Mechanical Surface Treatments, Shot Peening, and Others. Mechanical surface treatments cold work on the surface material using compressive residual stresses and depending on the properties of the material, often strengthening in the surface against strain. The geometry of the surface, its smoothness, is altered usually for the better unless the surface was initially polished or fine ground. The most common and versatile of the cold working treatments is shot peening. It is widely used with springs, gears, shafts, connecting rods, and other machine and structural components. In shot peening, the surface is bombarded with high velocity steel or iron shot discharged from a rotating wheel or pneumatic nozzle. The resulting lightly hammered or peened effect tends to reduce the thickness and therefore increase the area of exposed skin. Since the area is resisted by subsurface material, the skin is placed in a residual compression. The thickness of the compressive layer is usually less than the millimeter. The highest compressive stresses occur slightly below the surface and are commonly of order of half the yield strength. Sometimes greater compressive residual stresses are obtained by the loading part in tension while it is peened. This is called strain peening. With steel parts, shot peening is more effective with harder steel because the yield strength is a greater percentage of the ultimate strength. This means that the resulting residual stresses are less easily wiped out by subsequent load stresses that cause the total stress to exceed the yield strength. With a reference to the relationship illustrated in figure 8.6, endurance strength increases with hardness up to substantially higher values with shot peening. Machine parts made from very high strength steels are particularly benefited. A related mechanical surface treatment is cold rolling. The part is usually rotated while suitable contoured rollers are pressed against the surface to be strengthened, such as the shaft fillet or groove. This can create compressive residual stresses to a depth of the centimeter or more. Cold rolling has been applied to parts of all sizes, including large railway crank pins and axles of diameters up to 400 mm. Cold rolling is particularly effective for fatigue strengthening shafts used with pressed fit hubs. The fatigue strengthening advantages of cold rolling are sometimes obtained by product of a roll forming operation. Under enough pressure with suitable materials, screw threads, shaft lines, and other even fine gear teeth can be formed by cold rolling. The properties of the material then reflect the severe cold working. In addition, the residual compressive stresses are usually created. Coining is another cold forming operation that increases fatigue strength. An example is the pressing of a cone or oversized ball into the surface at the end of a hole, leaving a residual compressive stress at the vulnerable intersection of the hole and surface. Another example of cold pressing round grooves onto the shaft on both sides of a transverse hole. Chapter 8.15 Thermal and Chemical Surface Hardening Treatments. The purpose of thermal and chemical surface hardening treatments is usually to provide surface with increased resistance to wear. However, they also serve to increase fatigue strength, and for this reason are considered here. The strictly thermal process of flame induction hardening of steel parts containing sufficient carbon to produce surface residual compressive stresses as well as surface hardening as expected. Maximum benefits are obtained with notched parts having steep applied stress gradients. In such situations, fatigue strengths can often be more than doubled. Carburizing and nitriding are examples of chemical and thermal processes that add carbon or nitrogen to the surface layer together with appropriate heat treatment. The resulting hardened skin together with the surface residual compressive stresses can be very effective in increasing fatigue strength. In fact, nitriding has been found capable of rendering parts nearly immune to weakening by ordinary stress razors. This is illustrated by the following table given in the flow. Six hours. We've been at this for 6 hours. Oh my god. Chapter 8.16 Fatigue Crack Growth. In Chapter 6, we introduce basic concepts of fracture mechanics and defined fracture failure as whenever the stress intensity factor K exceeds the critical stress intensity factor Kc. We will now consider the fatigue process where the crack grows under alternating loads. Figure 8.32 plots the progress of the crack growth from initial crack length to C1 to critical crack length of CCR. We know that as the crack grows with increased number of cycles, and the tendency for failure increases. For a small identifiable crack, a typical crack growth history for cyclical tensile load of constant amplitude would begin with growth in a stable, controlled manner until a critical crack size was reached, that is, where the crack growth rate increases in an uncontrolled manner and catastrophe looms. Figure 8.33a and 8.33b shows the proportional relationship between the range of stress intensity delta K equals K max minus K min and the range of stress delta sigma equals sigma max minus sigma min respectively. Here K min and sigma min y square root pi c K, K max equals pi max y square root pi c and delta K equals delta sigma y square root pi times c. Period. Recall that fatigue life is largely dependent on the mean alternating component of stress, that is, for a range of magnitude of the stress which is proportional to the range of stress intensity for an initial existing crack of size c, and for a given material, the slope dc divided by dn depends upon the range of stress intensity factor. Delta K equals delta max equals K max minus K min. Again, K1 equals to sigma times y square root pi c. Figure 8.3 shows a plot of crack propagation versus delta K. The crack propagation rate or crack growth rate increases with cycles of alternating load and denoted by the dc divided by dn, where n is the number of cycles and c is the crack size. For a particular material, the stress intensity range delta K is related to dc divided by dn as shown as a sigmoidal curve comprised of 3 stages. Stage 1, initiation, shows that the growth of a crack requires a stress intensity range exceed a threshold value. One mechanism for initial growth relates to the cleavage around One mechanism for initial growth relates to cleavage along grain boundaries. Stage 2, stable propagation, shows that crack growth rate versus intensity range is approximately cleavage, okay. Okay, log linear. This important stage is for cracks that grow in a stable manner. The curve for stage 2 can be described by the Paris equation, where dc divided by dn is the crack growth rate and c in the index n are constant material properties values, of which appear in literature. In stage 2, for a certain crack growth rate dc divided by dn, there is a corresponding stress intensity delta K such that the constant c equals dc divided by dn divided by delta K 0 to the power of K. Stage 3, instability begins as the critical crack size is approached and exists for a small portion of the component's life. The instability is catastrophic and takes place suddenly after the start of stage 3. Stages 2 and 3 can be both represented by empirical modification of equation 8.4, that is dc divided by dn equals c times delta k to the power of n divided by beautiful bracket 1 minus k max divided by kc parentheses to the power of n beautiful bracket. Okay. 8.5, that if k max is less than kc, then the term 1 beautiful bracket 1 minus k max divided by kc parentheses to the power of n beautiful bracket approaches 1, and equation 8.5 represents stage 2. If k max approaches kc, then dc divided by dn tends to infinity and represents stage 3. Integration of 8.5 yields the component life delta n 12 cycles that elapses during crack growth from C1 to C2. In normalized form, where A equals C divided by W, we have a longer equation with a derivative where CR is normalized critical crack size corresponds to KC, and A2 is less than or equal to ACR for the plane strain conditions. KC equals KLC. 8.6 can be integrated and then solved for the component's life that elapsed during the crack growth. The configuration factor is required as a function of crack size, that is y equals y parentheses alpha. With normalized crack size limits of A1 and A2, the integral of 8.6 may be evaluated numerically, noting the value of W is required that each term is dimensionless. In practice, closed form integration is usually impossible and graphical methods may be used. Chapter 8.17 General Approach for Fatigue Design. Brief overview of failure criterion for simpler cases. Why do I need the brief version of it when you just gave me the full version of it? What are you doing? Okay. Chapter 9.1 Introduction. Previous chapters have dealt with the damage occurring within the body of a part. In addition, various kinds of damage can occur to the surface of a part, which render it unfit for use. To begin the list, the surface may corrode, either in a normal atmosphere or in other, usually more corrosive environments, such as saltwater. Surface corrosion may combine with static or fatigue stresses to produce more destructive action than would be expected. By considering the actions of corrosion and stress separately, high relative velocities begin solid parts, and liquid particles can use cavitation with the liquid, which may be destructive to the surface of the part. When two solid members are pressed together, contact stresses are produced and require special consideration. When the members are in sliding contact, several types of deterioration coming under the general heading of wear can occur. The severity of the wear can be reduced by using a lubricant such as oil, grease, or solid film between the rubbing surfaces. Experience indicates that more machine parts fail through surface deterioration than by breakage. In an automobile, for example, consider the range of surface damage represented by corroded exhaust systems, rusted body panels, and worn piston rings, suspension joints, and other rubbing parts. The epidemic cost of the surface damage underscores its importance. The National Bureau of Standards reported to Congress that the estimated total annual cost of corrosion and wear in the United States were $70 billion and $20 billion respectively in 1978 dollars. Chapter 9.2 Corrosion Fundamentals. Corrosion is degradation of a material by chemical or electrochemical reaction with its environment. Most corrosion results from electrochemical or galvanic action. This complex phenomenon giving rise to the special discipline of the corrosion engineering. 9.1 shows the electrode of chemically pure iron and homogeneous electrolyte. Positively charged iron 2 plus ions go into solution, leaving excess of electrons. When equilibrium electrode potential is reached, no further electrochemical action takes place. 9.2 figure 9.2. The iron electrode is completely plated, leaving exposed iron as shown. If the plating is thin, for example, the plating tends to lose positively charged ions with a corresponding negative charge for remaining in the tin coating. At the same time, the exposed iron surface tends to lose positive iron ions, leaving negative charge in the body of the iron. Table 9.1 shows that. Ooh, okay. So we got the two charts here. I remember this from school. God. Oh my god, I still remember my chemistry teacher. Oh my god. I wonder how he is. Never talked to that dude. But then again, I don't talk to any of my teachers that often. But anyways, let's is more active than tin. In the galvanic series, this means that iron has the greater tendency to ionize and develops in the greater negative charge. It's okay. You guys can know that. Oh my god. That's still there? A flow of ions going through the electrolyte completes a circuit. This process involves a continuous discharge of iron ions, hence the iron corrodes. The current is direction to prevent a discharge of tin ion, thus the tin cathode does not corrode. This phenomenon is commonly observed in rusted tin cans, where breaks in the tin can caused by exposed steel to corrode. The iron ions discharged in the electrolyte commonly combines with hydroxyl and oxygen ions to precipitate out as ferric hydroxide and ferric oxide or rust. Although the relative order of metals in the galvanic series is generally similar to commonly encountered electrolytes, exceptions do occur. An interesting case in point is that same tin can. The various acids, alkalides, and organic substances in canned foods provide electrolytes in the inner steel surface of the can is cathodic with respect to the tin and is therefore protected. Furthermore, tin salts, which may be present in an extremely low concentration owing to corrosion of the tin, are non-toxic. Hence, tin plates is considered ideal for handling beverages and foods. Suppose in figure 9.2 that the plating is not tin but zinc. Reference table 9.1 indicates that the extraordinary environment the zinc will go into solution, and the direction of the current through the electrode will oppose the discharge of positively charged iron ions. Thus, the iron becomes a cathode and does not corrode. Zinc coating represents the common practice of galvanizing ferrous materials to protect them against corrosion. Most corrosion phenomena include two metal electrodes in contact as iron and zinc or iron and tin. In figure 9.2, closely related electrochemical phenomena can be illustrated with where the two electrodes A and B are not in direct contact. Suppose these electrodes are zinc and carbon. Table 9.1 indicates that the greater concentration of electrons would be on the zinc. Zinc has the greater tendency to lose positive ions, thereby leaving it with a negative charge with respect to the carbon. If terminals A and B are connected by a wire, electrons will flow through the wire. This is what happens in an ordinary carbon-zinc dry cell. Then again, referencing to figure 9.3, suppose that electrode is iron and B is copper, and that the two terminals are connected by a battery that forces a flow of positive charges from the copper through the electrode and to the iron. This is accomplished by copper ions going to the solution, corroding the copper away, and then migrating to the iron electrode where they are deposited. This process is electroplating. Figures 9.4 and 9.5 illustrate the practical applications of the principles just given in suppressing corrosion. In 9.4, the natural flow of galvanic current is such that the equipment to be protected in this cathode, and the zinc and magnesium plates are sacrificial anodes. In the source, in an external direct voltage source forces a flow of electrons to the equipment to be protected, making it a cathode. Chapter 9.3 Corrosion, Electrode and Electrolyte Heterogeneity. In the previous section, it was assumed that electrodes and electrolytes were homogeneous. Many corrosion situations deviate from substantially from this ideal condition, and these deviations affect the nature of extent of resulting corrosion. For example, aluminum and titanium exposed to ordinary atmosphere from protective oxide films Al2O3 and TiO2 on their surfaces, that electrically insulate the body of the material. The corrosion current density is therefore almost nil. This explains why the aluminum can be used for boats despite its position in galvanic series. Iron, chromium, nickel, titanium, and many of their important alloys exhibit the phenomenon of passivation, which means insulating oxide films are maintained in certain environments. When the metal is active condition, corrosion and current densities are frequently 10 to the 4 and 10 to the 6 times of those passive states. Another important form of electrode heterogeneity is the microstructure of the metal. For example, when perlite is etched with a mild acid, the microstructure can be seen because the ferrite and carbide constituents become anodes and cathodes in the multitude of minute galvanic cells. Whichever is the anode corrodes, thus enabling it to be visually distinguished. Ferrite and carbide have very close electrode potentials, and their relative position in the galvanic series depends on the electrolyte used. Another important cause of the local galvanic action is heterogeneity of the electrolyte. A common example is a variation in composition of the salt mud water deposit under car bodies in the northern United States, which sets up vigorous local galvanic action. Another example is the corrosion of buried pipe that passes through the strata of soil of varying salt content. 9.6 illustrates two instances where a drop of electrolyte, usually water, creates electrolyte heterogeneity by sealing off the atmospheric oxygen from the outer center of the drop compared to the oxygen-rich electrolyte near the edge. Corrosion occurs at the oxygen-starved interior. Figure 9.6b illustrates the commonly called crevice corrosion. A related observation that the reader may have made is the smooth surfaces tend to corrode less rapidly than rough surfaces. Chapter 9.4. First, consider material selection. Materials toward the inactive or noble end of the galvanic series for the electrolyte developed lower electrical potentials, tending to send their ions into solution and thus corrode more slowly. This is not the whole story though, because as noted previously, the rate of which metal ions go into solution can be dramatically reduced by the oxide film. Thus, aluminum corrodes extremely slowly in salt water, despite its position in the galvanic series. The same thing is true for stainless steels when, in most environments, these films change the metal's action from active to passive. Alright. Differences in microstructure caused by heat treating and welding can influence the intensity of galvanic action when low. Multitude of surfaces, galvanic cells, certain low alloy steels have been developed that effectively resist atmospheric corrosion by forming protective rust films. These steels are primarily used for architectural construction. After initial weathering, they have a uniform reddish-brown color, and galvanic action nearly stops. Because the weathering steels need not to be painted, their use often results in substantial cost saving over the life of the structure. Chemical treatment of metal surfaces may produce surface films that offer some degree of insulation to the base metal from the environment. Common examples are phosphate coatings on steel. The oxide coatings on steel, brown, black, or blue in color. The effectiveness of these films are usually minimal unless they are combined with rubbing with oils or waxes. Phosphate coatings on steel help provide a good adherence of paint and decrease the tendency of corrosion to undercut the paint film at scratches or other discontinuities. And anodizing of aluminum alloys produces a stable aluminum oxide film that has excellent corrosion resistance that can be dyed in a variety of colors. Common experience indicates the protective oxide film and unanodized aluminum rubs off to produce a black stain. Metal surfaces can be sealed from the possible contact of electrolyte by non-porous coatings such as porcelain enamel applied to the bathroom fixtures and rubber coatings vulcanized to steel plates. Ordinary paints provide a good barrier of the diffusion of water and oxygen to a metal surface, but are permeable to some extent. Because of this, and because paint films can be scratched and otherwise damaged, it is important to be effective primer. The pigments in the prime cost applied to bare metal should be effective corrosion inhibitors. Any water reaching the metal surface then dissolves in a small amount of primer pigment, making the water less corrosive. Where appearance and weight considerations are not stringent, it is sometimes more economical to make part with larger dimensions to allow for anticipated future corrosion than it is to provide effective corrosion protection. In addition, the impact of corrosion damage can be often reduced by designing equipment so that parts vulnerable to corrosion can be easily replaced. The preceding discussion assumed that only a single metal was involved. When the corrosion of two or more metals connected by electrode is to be minimized, the metals should be as close together as possible in the galvanic series. For example, cadmium is very close to the aluminum in most environments. Hence, cadmium plated screws can be used in direct contact with aluminum parts. But if a copper washer is introduced, aluminum normally corrodes rapidly. In fact, aluminum has been found to corrode rapidly in rainwater that had previously contacted copper flashings or gutters. Other common examples of galvanic corrosion include the corroding of aluminum car door stills in contact with steel body structure when exposed to the road salt in northern areas or salt near the coast. Steel pipe connected to aluminum plumbing, steel screws and brass marine hardware, and the lead tin solder on copper wire. 9.1 shows the compatibility with respect to galvanic corrosion of commonly used metals and alloys when placed together in atmospheric environments. Anodized aluminum is capable with all other metals. Oh my god. It's bright, guys. The screen is so bright. Oh my god. Where was I? When it is necessary to use dissimilar metals together, the corroding galvanic circuits can often be broken by using an electrical insulator. Sometimes the galvanic cells are deliberately designed to a component system or by providing a sacrificial anode to protect the metal cathode, which was illustrated by the zinc coating of steel in connection of 9.2 and other examples in 9.4. In the United States alone, thousands of tons of magnesium are used annually as sacrificial electrodes. Figure 9.5 shows the alternative method of cathodically protecting underground tanks or pipe. The cost of external electrical energy consumed was the obvious factor limiting the application of this method. An important factor of the design of the metal parts to resist the corrosion is the area effect. To minimize corrosion of the anode, its exposed surface area should be large in comparison to cathode surface area. This results in low current density at the anode, hence a low corrosion rate. The area effect is clearly illustrated by the examples depicted in 9.2, where the plating was zinc, as in galvanized steel. The large zinc surface results in low current density and a low rate of corrosion. Where the plating was thin, small areas of exposed ferrous material results in rapid corrosion, as observed in the discarded and used rust tin cans. Design for corrosion control also requires a careful attention to factors relating to the electrolyte. The electrolyte may be a liquid in which metal electrodes are totally immersed, or its function may be provided by exposure to spray or mist, by alternate wetting and drying, as by rain, by contact with moist earth, or merely from humidity in the atmosphere. It is important to eliminate or minimize crevices which corrosion can completely occur. Parts should be designed so that moisture can drain completely without leaving residual liquid to encourage corrosion. This means that smooth but welded joints tend to corrode more slowly than bolted or riveted lap joints. Surfaces that are smooth tend to corrode less than rough surfaces. for they have less tendency to retain liquid electrolyte. Unavoidable crevices should be sealed, ideally with vulcanized rubber or the equivalent. Surfaces subject to retaining deposits of mud and salt should be designed to facilitate cleaning. For heterogeneous mixtures of soil and salt in contact with a metal can cause destructive galvanic action. Electrolytes tend to cause the least galvanic action where they are stagnant. Agitation and temperature gradients tend to remove ion concentration near the electrode surfaces, thus increasing galvanic currents. Hence, temperature gradients and fluid velocities should be minimized. Atmospheric corrosion tends to be the greatest at high temperatures and high humidity. For example, corrosion rates of structural steel in tropical climates are reportedly at least twice than that encountered in temperature climates. In recirculating cooling systems, inhibitors are used to make the liquid a less effective electrolyte. These inhibitors act to encourage passivation of the metal subject to corrosion and otherwise impede the movement of ions in the region of the electrodes. The inhibitors must be appropriate to the liquid and the metals involved. When static tensile stresses exist on a metal surface subjected to certain corrosive environments, the combined action can cause a brittle cracking fracture that would not be predicted on the basis of considering these two factors separately. Such cracks are called stress corrosion cracks and have been known to engineers since at least 1895, when it was noted that the surface cracks developed on iron tires of wagons wheels after a period of exposure to humid atmosphere. These tires were subjected to the residual tensile stress because they had been forced onto the wheels with an interference fit. Although the vulnerability in engineering metals to stress corrosion cracking varies greatly, nearly all are susceptible to some degree in some environments. Stress corrosion cracking is a complex phenomenon not yet fully understood. Environments causing galvanic corrosion of a metal are not necessarily the same as associated with serious stress corrosion cracking of the metal. The relative resistance of the materials to ordinary galvanic corrosion in a specific environment is not usually the same as the relative resistance of these materials to stress corrosion cracking. For example, stress corrosion cracking has been observed in certain stainless steels that are completely corrosion resistant when unstressed. The stress associated with stress corrosion cracking is always tensile, and is the sum of the residual and operating stresses existing on the local site where the cracks initiate and propagate. The total stress necessarily for stress corrosion cracking is most often in the order to 50 to 75% of the tensile yield strength. Residual stresses alone can be easily this high. Stress corrosion cracks may occur after a period of time, relative few minutes to several years, depending on the corrosive environment and tensile. Attempts to determine stress levels during where stress corrosion cracks would never occur have not been successful. However, engineers are gaining a better understanding of stress corrosion cracking failures through studies applying fracture mechanics. When stress corrosion cracking occurs, there are usually multiple cracks originating at the surface, with fracture resulting from a single crack propagating normal to the resultant tensile stress. The appearance of a local failure is shown in 9.8. An early reported example of stress corrosion cracking was riveted steam boilers. Alkaline boiler water in crevices around the rivets contacted boiler plate surfaces that were in tension, with these stresses being accentuated by stress concentration. Some boilers exploded. Mild steel boiler tubes operating with water containing sodium hydroxide have also failed because of stress corrosion cracking. Other examples of this type of failure include stainless steel aircraft parts exposed to the salt environment of the seacoast. Then hubs or rims are passed into an inner member of a heavy interference fit. Bridge cables whose steel is inappropriate for the chemicals in the local atmosphere. Steel brackets that support heavy static weights and season cracking of brass cartridge cases. These are deep drawn cylindrical cases that have residual tensile stresses in the sharp bottom corner. Cracking occurs after storage before the loads have been applied. Peening is of particular importance. It serves to overcome previous surface residual tension and impart helpful residual compressive stresses. In summary of the stress corrosion, performance of several metals and alloys is given in 5a. Corrosion plus cyclic stress. The combination of action of corrosion and fatigue loading usually causes earlier failure than would be expected from a consideration of the two effects separately. This phenomenon is called corrosion fatigue. It occurs when most metals, but most markedly with those having little corrosion resistance. Corrosion fatigue is a complex action not yet fully understood. A simplification explanation with the initial corrosion pits with serve as points of stress and concentration. Protected films formed by resolved corrosion are usually weak and brittle, hence they are ruptured by the imposed cyclic strain. The rupture exposes unprotected metal, which quickly corrodes, forming another film which is also ruptured by cyclic strain, and so on. Thus, the initial corrosion pit becomes a fatigue crack and propagates more rapidly than it be explained by considering corrosion and the cyclic loading separately. As would be expected, corrosion fatigue failures show the discoloration of the crack propagation surfaces, whereas ordinary fatigue crack surfaces are corrosion-free. The fatigue strength of the corroding parts depends on the lapse time, as well as cyclic stress in the corroding environment. The fatigue strength for a given number of stress cycles is obviously greater if those cycles are imposed quickly without allowing much time for corrosion to occur. Test results tend to support the following generalizations. 1. Corrosion fatigue strengths do not correlate with tensile strengths. This is likely in part because of the stronger metals have greater sensitivity to corrosion pits. 2. Medium alloy steels have slightly higher corrosion fatigue strengths than carbon steels, and in neither case this is corrosion fatigue strength improved by heat treatment. 3. Corrosion resistant steels such as those containing chromium have a higher corrosion fatigue strength than other steels. Good corrosion resistance is more important than high tensile strength. 4. Residual tensile stresses are harmful. Residual compressive stress, such as those caused by the shop painting, are beneficial. Remedial measures for corrosion fatigue are similar to those for stress corrosion cracking. Use a more corrosion resistant material to reduce corrosive action by protective coatings, inhibitors, or cathode protection, and minimize steel tensile stresses and introduce the residual compressive stresses. Much of the experimental data on corrosion fatigue strengths of various metals that are still referred to were reported by D.J. McAdam, the investigator who originally coined the term corrosion fatigue. Some of McAdam's results are summarized in 6 and 14. Note that 8.15 gives the surface factors for test specimens which previously corroded surfaces. These factors serve only as a rough guide and do not apply to all situations in the part subjected to corrosion while the cyclic stress is applied. Jeez. Let's take a break. 5-minute break. Chapter 9.7 Cavitation damage. Cavitation is the formation of gas bubbles or cavities in a liquid that is moving with respect to a nearby solid surface. Bubbles are formed when the liquid pressure drops below its vapor pressure. When these bubbles subsequently collapse at or near the solid surface, pressure waves impinge upon the surface, causing local stresses that can be great enough to cause plastic deformation of many metals. Often metal damage evident only after repeated bombardment by these pressure waves, much in the case of damage caused by ordinary metal fatigue. Cavitation commonly occurs on ship propellers, centrifugal pumps, turbine blades, and other surfaces that encounter high local liquid velocities and large liquid static pressure gradients. The resulting damage to metal surfaces is essentially mechanical. In corrosive environments, however, cavitation can repeatedly damage or remove protective oxide films, thereby increasing galvanic action. A surface area damaged by cavitation appears roughened, with closely spaced pits. In severe cases, enough material is removed to give the surface a spongy texture. If not feasible to eliminate or reduce cavitation by modifying the liquid composition, velocity, flow pattern, or static pressure, then the most effective means of dealing with cavitation damage is to usually increase surface hardness. Stainless steel is often the most effective material available at reasonable cost. The following materials are listed in decreasing order of resistance to cavitation damage: stellite, 18-8 cast stainless steel, cast magnesium bronze, cast steel, bronze, cast iron, and aluminum. This list is extracted from 4 and 8, which also list other materials. Chapter 9.8 Types of wear. The previous sections in this chapter dealt with surface damage resulting from contact with fluids. The remaining sections discuss contact with another solid. In many instances, the resulting surface damage is classed as wear. The most common types of wear are adhesive wear and abrasive wear. These are treated in the next 3 sections. A third type is corrosion film wear, wherein the corroded surface film is alternately removed by sliding and then reformed. A typical example is the wear that may occur on the cylinder walls and piston rings of a diesel engines burning high sulfur fuels. An important type of surface deterioration, sometimes incorrectly classed as wear, is surface fatigue, discussed in 9.14. All forms of wear are strongly influenced by the presence of lubricant. The information in section 13.1 on types of lubricant and section 13.14 on boundary lubrication is relevant here. The wear rate for an unlubricated bearing can be 10 to the 5 times that for a bearing with a boundary lubrication. In a typical well-designed machine component, the initial wear rate on rubbing surfaces during the run-in may be relatively high, as the more pronounced surface peaks are worn off, causing the actual area of contact to increase. The wear rate decreases a small constant value. After a period of time, the wear rate may again increase because the lubricant is contaminated or surface temperatures are higher. Reference 10 contains 33 articles dealing with the various aspects of wear, and it is an excellent reference for further study. Chapter 9.9 Adhesive wear. On a microscopic scale, sliding metal surfaces are never smooth. Although surface roughness may be a few micro-inches, inevitable peaks and valleys occur. As shown in figure 9.9, since the contact pressure and the frictional heat of sliding are concentrated on small local areas of contact indicated by the arrows, local temperatures and pressures are extremely high, and conditions are favorable for welding at these points. If melting and welding of surface asperities at the arrows in figure 9.9 do occur either the weld or one of the two metals near the weld must fail to shear permit the relative motion of the surfaces to continue. New welds, adhesions, and corresponding fractures continue to occur, resulting in what is approximately called adhesive wear. Since adhesive wear is basically a welding phenomenon, metals that weld together easily are more susceptible. Loose particles of metal and metal oxide resulting from adhesive wear cause further surface wear because of abrasion. If the surface asperity, welding, and tearing cause a transfer of metal from one surface to the other, the resulting wear or surface damage is called scoring. If the local welding of asperities becomes so extensive that the surfaces will no longer slide on each other, the resulting failure is called seizure. Figure 9.10 shows severe scoring and seizure of different pinion gears on their shafts. Perhaps the best known examples of seizure occurs in engines that continue to operate after losing their liquid coolant or oil supply. Pistons may seize to the cylinder walls, the crankshaft may seize to its bearings, or both may happen. Severe adhesive wear is also called galling. Mild adhesive wear between piston rings and cylinder walls is often called scuffing. When like metals are rubbed together with suitable pressure and velocity, conditions are ideal for asperity welding because both surfaces have the same melting temperature. In addition, the cohesive bonds thus formed are normally stronger than adhesive bonds between dissimilar welded asperities. For these reasons, or metallurgically similar metals do not normally be used together under conditions likely to cause wear problems. Metallurgically similar metals are referred to compatible. Compatible metals are defined as having complete liquid miscibility and at least 1% solid solubility of the one metal and another at room temperature. Figure 9.11 shows the degree of compatibility of various combinations of the metals. In general, the harder the surface, the greater the resistance to adhesive wear. Chapter 9.10 Abrasive wear. The term wear most often refers to abrasive wear, which is due to the rubbing of abrasive particles on a surface. These particles are typically small and hard and have sharp edges like grains of sand or particles of metal or metal oxide that rub off a wearing metal surface. Common examples include the wearing down wood or metal with sand or emery paper with grinding wheel, the wearing of shoe leather by scuffing against cement sidewalks, the wearing of a plow blade or earth auger during use, and the removal of metal from the journal surface of a rotating shaft by foreign abrasive particles in the lubricant. Usually, the harder the surface, the more resistant it is to abrasive wear. Hard metal surfaces are produced by heat treatment, flame or induction hardening, carburizing, nitriding, electroplating, flame plating, and other means. Not all these methods are applicable to severe applications because the hardened surfaces must sometimes be at least 3 mm thick to give adequate service life. In machinery design, it is extremely important to use appropriate oil filters, air cleaners, dust covers, shaft seals, and so on to keep foreign particles away from rubbing metal surfaces. Sometimes one pair of rubbing members is made relatively soft and is designed to be easily and economically replaced. For example, hard surfaces on rotating shafts are protected by the use of softer, easily replaced bearings and bushings. It is sometimes desirable for the bearing to be sufficiently soft to permit hard abrasive particles to embed completely so that they do not protrude above the surface and act like abrasive particles on sandpaper. This is the one reason why soft Babbitt bearings are used with the automotive engine crankshafts. Chapter 9.11 Fretting. Fretting, also known as fretting corrosion, is classed as a form of adhesive wear but usually embraces the elements of abrasive wear and corrosion film wear as well. Fretting occurs when the surfaces pressed together experience a slight relative motion. Examples of press fits include press fits and bolted riveted connections. where fluctuating loads produce slight elusive movement. Other examples of leaf spring interfaces and stacks of sheet metal transported long distance by rail or truck. The relative motion is typically in the order of 0.01 to 0.25 mm. The resulting damage can be the discoloration of mating surfaces, the formation of surface pits, or the wearing away of a millimeter of material. The roughness and pitting caused by the fretting make the surface more vulnerable to fatigue failure. Reducing fatigue strength is a major consequence of fretting. A widely accepted theory is the oscillatory motion breakdowns down natural protective surface films, exposing bare metal surface peaks that weld together and then torn away by the relative motion. With most engineering materials, the surface debris thus formed oxidizes to form the powdery abrasive particles which build up and cause continuing wear. With ferrous surfaces, the oxide powder is sometimes called cocoa because of its brown color. Magnesium and aluminum oxide particles appear black. Resistance to frettage varies widely in different materials. Cobalt-based hard-facing alloys are among the best. In general, steel on steel and cast iron on cast iron are good. Interfaces in which one metal is stainless steel or titanium are poor. Brass on steel tends to be better than the steel on steel. Combinations of cast iron with aluminum, magnesium, chrome plate, tin plate, or plastics are poor. The creation of surface residual compressive stresses by heat treatment or cold working has proved particularly effective in retarding the propagation of fatigue cracks initiated by fretting. The increased surface hardness resulting from these treatments is probably also beneficial. Low velocity, high tenacity lubricants tend to reduce the intensity of fretting, their main effect apparently being to keep oxygen away from the active interface. Sometimes fretting can be arrested by increasing surface interface pressure so that relative motion ceases. However, if the relative motion continues, fretting damage will usually increase with higher pressure. Additional details considering fretting corrosion are given in references 4, 6, 8, 10, 13. 7. Chapter 9.12 Analytical Approach to Wear. Although the design of machine components from standpoint of resisting wear remains largely empirical, and analytical approaches are now available. The generally recognized wear equation, which emerged in the 1940s, can be written as wear rate squiggly divided by T equals K divided by H P times V, where squiggly equals wear depth, T equals time, K equals wear coefficient, surface hardness in MPa, P equals surface interface pressure, and V equals sliding velocity. For two rubbing surfaces A and B, this equation implies that the rate of wear of surface A is proportional to the wear coefficient, inversely proportional to the surface hardness of A, and assuming a constant coefficient of friction directly proportional to the rate of friction work. For a given total compressive force between the surfaces, the volume of material worn away is independent of the area of contact. Thus, another and more commonly used form of wear equation is W equals K divided by H F times S, where W equals the volume of material worn away, mm3, F equals the compressive force between the surfaces, S equals total rubbing distance, mm. The best way to obtain values of wear coefficient K for a particular design application is from experimental data for some combination of materials operating under essentially the same conditions. For example, obtaining wear constants for the design of a new model from wear data obtained in a similar old model. In addition, the literature contains values of K for many combinations of materials that have been obtained under laboratory conditions. When we use these values, it is important to the approximate interface temperature and the materials and lubrication of expected applications correspond to those used in laboratory tests. For a wide variety of sliding systems, wear coefficients range from 10 to the negative 1 and 10 to the negative 8. Figure 9.12 illustrates ranges values typically obtained with various combinations of material compatibility, lubrication, and wear mode. The values of K pertain to the softer of two rubbing metals. The test data for wear coefficients show considerable scatter, typically over a range of plus or minus factor of 4. For example, if the observed wear coefficient is 100 units, the actual K value will vary from 25 to 400 units. This is perhaps to be expected because adhesive wear tends to be proportional to the fourth or fifth power of the frictional coefficient, which itself has considerable scatter. The following sample problem illustrates the computation of K from experimental data. Chapter 9.13 Curved Surface Contact Stresses. A theoretical contact between curved surfaces is generally a point or a line. When curved elastic bodies are pressed together, finite contact areas are developed because of deflections. These contact areas are so small, however, the corresponding compressive stresses tend to be extremely high. In the case of machine components like ball bearings or roller bearings, gears, and cam and followers, these contact stresses at any specific point on the surface are cyclically applied. Hence, fatigue failures tend to be produced. These failures are caused by minute cracks in them propagate to permit small bits of material to separate from the surface. This surface damage, sometimes referred to as wear, is preferably called surface fatigue. These failures are discussed more fully in the following section. The present section lays a necessary foundation by considering in more detail the stresses caused by pressure plus possible sliding between curved and elastic bodies. Figure 9.14 illustrates contact area and corresponding stress distribution between two spheres and two cylinders loaded with force F. By equating the sum of the pressures over each contact area to the force F, we obtain a expression for the maximum contact pressure. The maximum contact pressure P0 exists on the load axis. The area of contact is defined by dimension A for the spheres B and L for the cylinders. The equations for P0, A, and B can be simplified by introducing the contact modulus delta, which is a function of Young's modulus E and Poisson's ratio for contacting bodies 1 and 2. For a cylinder and flat plate, R2 is infinite. For a cylinder and cylindrical groove, R2 is negative. For other cases, the two surfaces pressed together, C6, 7, 11, and 12. Contact pressure P0 is, of course, also the value of compressive stress at the load axis. The original analysis of elastic contact stresses was published in 1981 by Heinrich Hertz of Germany at age 24. In his honor, the stresses at the mating surfaces of curved bodies in Hertz of Germany in compression are called Hertz contact stresses. Derivation of equations 9.2 to 9.6 assumes that the contact is frictionless. The contacting bodies are elastic, isotropic, homogeneous, and smooth. The radii of curvature R1 and R2 are large in comparison with dimensions of the boundaries of the surface of contact. Figure 9.15 shows how direct compressive strength sigma demonstrates this below the surface. It also shows the corresponding values of sigma x and sigma y. These compressive stresses result from Poisson's ratio and the material along the load axis that is compressed in z directions to expand the x and y directions. But the surrounding material does not have to move away to accommodate this expansion. Hence, the compressive stresses in the x and y directions. Because of symmetry and loading, it can be shown that x, y, and z stresses plotted on 9.15 are principal stresses. In figure 9.16 shows a more circle plot for stresses on the load axis at depth B below the surface for two parallel cylinders. Note the value of the shear stress T max in figure 9.16 agrees to the value plotted in 9.15b. Other values of T max plotted in figures 9.15a and 9.15b can be verified in the same manner. All stresses previously considered in the section exist along the load axis. Figure 9.17 shows the important shear stress existing below the surface and displaced from the load axis. Cylinders are rotating together in the direction indicated. Any point below the surfaces experience stresses at the first at A and then B, and then completely reverse shear stress, believed to be very significant in the connection of subsurface fatigue crack initiation. The stress is greatest at points below the surface, a distance about 0.5 B, as a point at this depth rolls through the contact zone. The maximum values of shear stress are reached at a distance about B on either side of the load axis. Most rolling members mating gear teeth, a cam, and follower, and to some extent the rolling members in a ball and roller bearings are also tend to slide, even if only slightly. The resulting friction forces the tangential normal and shear stresses that are superimposed on the stresses that caused by the normal loading. These tangential stresses are illustrated in figure 9.18. As any given point on the surface rolls through the contact zone, the tangential shear stresses vary from 0 to maximum to 0, while the normal stresses vary from 0 to tension to compression to 0. The presence of surface tensile stresses is undoubtedly important to the propagation of surface fatigue cracks. Let us conclude this section by summarizing more important aspects of stresses associated with contact curved surfaces. First, the maximum contact pressures and the flattened areas of contact are given by the classical equations of Henrik Hertz. Below the surface and the load axis is an important shear stress associated with Poisson's ratio expansion of the compressed material below the surface, and to each of the load axis the shear strength Txy. This is particularly important in the rolling members because it reverses direction as any given point below the surface rolls through the contact zone. Some sliding often accompanies rolling and causes both a tangential surface shear strength and a reverse surface tangential stress. Two other very important factors affecting the stresses in the contact region are highly localized heating and thermal expansion caused by sliding friction, and the hydrodynamic pressure distribution with an oil film that normally exists within the contact region. Because of these many factors, the maximum Hertz contact pressure is not by itself a very good index of contact loading severity. Chapter 9.14 Surface fatigue failures. Surface fatigue failures result from the repeated application of loads that produce stresses in and under contacting surfaces. As described in the previous section, cracks initiated by these stresses propagate until small bits of surface material become separated, producing pitting or spalling. Pitting originates with the surface cracks, and each pit has relatively small surface area. Spalling originates with the subsurface cracks, and the spalls are thin flakes of surface material. These types of failure occur commonly in gear teeth, ball and roller bearings, cams, and followers, and metal wheels rolling on rails. An example of spalling is illustrated in figure 9.20. Figure 9.21 shows a typical S to N curves based on computed elastic Hertz stress. Note that the degree of sliding generally increases from the parallel rollers presented by the top line to spur great teeth corresponding to the bottom line. The tendency for surfaces to fail in fatigue can obviously be reduced by decreasing loads and decreasing sliding. Better lubrication helps in at least three ways. Less friction reduces the surface tangential shear stress and also the tensile stress known in the figure 9.18. Less friction plus improved heat transfer reduce thermal stresses, and the presence of a good lubricating film usually allows a more favorable distribution of pressure over the contact area. In general, increased surface hardness increases resistance to surface fatigue. However, the associated increased strength reduces the ability of minute surface imperfections to adjust by the wear or surface flow, and thereby reduce localized contact pressures. This is part of the rationale behind the common practice of making one of a pair of mating gears very hard and with the other somewhat softer to allow for run-in of the surfaces. Precise accuracy of the surface geometry and extreme surface smoothness are highly beneficial. Exceptions occur when significant sliding is present. Then surface porosity or pattern of minute depressions in one of the mating surfaces may help by providing tiny reservoirs for holding lubricant. Compressive residual stresses in the contacting surfaces increase resistance to surface fatigue failure. This is to be expected and follows the general pattern of each of such stresses, discouraging fatigue failure and surface damage. Pause here. 5-minute break. Alright. Chapter 9.15 Closure. At previously noted, corrosion and wear represent an estimated annual cost in the United States of some $90 billion. Furthermore, more machine parts wear out than break. The reduction of this enormous economic and ecological burden presents one of the greatest challenges to modern engineering. The solution would seem to require designing to reduce surface damage as much as feasible and providing for the easy replacement of machine components that are most vulnerable to surface deterioration. Almost everyone is familiar with instances in which an entire machine was scrapped because it was too costly to replace one or two worn out parts. Let us briefly review three aspects of machine component surfaces. Smoothness is an important fatigue strength. Recall surface factor CS in figure 8.13 to wear resistance and to some extent to corrosion resistance. Hardness acts to improve the strength, to provide resistance to wear and prevent cavitation damage. Surface residual stress is important for compressive residual stresses, increase fatigue strength, and increase resistance to stress corrosion cracking, corrosion fatigue, and surface fatigue, and decrease damage from fretting corrosion. An important concept of the modern design of many machine components is that of choosing different materials for the interior and for the surface. If the material most suitable for the bulk of the part does not meet surface requirements, a second material can often be applied to the surface. For example, steel parts can be coated with zinc, cadmium, chromium, nickel, or other metals to provide desired corrosion resistance. Soft metal parts or even plastic parts can be coated with hard, bright surface metal for abrasion resistance and appearance. For extreme hardness, carbides of tungsten and other metals can be commercially applied by flame spraying and other processes. For applications requiring low friction and wear, coatings incorporating fluoroplastics are commonly applied. Other plastic coatings are used for applications requiring high coefficient of friction. Parts having surfaces subjected to extreme heat can be coated with special high temperature alloys or ceramic materials. Sometimes the desired coating can be incorporated into paint type materials such as corrosion resistant paints having a pigment of powdered zinc, or wear resistant coatings consisting of tiny beads of alumina and ceramic and epoxy resin can be used. Thus, it is becoming increasingly feasible to avoid the serious compromises associated with making parts from a single material. Ecological and health considerations must be taken into account when choosing a coating material and coating process. For example, cadmium in the human body can pose serious danger. Cadmium plating of steel parts has been long extensively used to provide corrosion resistance. Large quantities of spent fluids of high cadmium content are a byproduct of cadmium electroplating. Disposal of this waste without polluting water or soil is a problem. The development of safe processes for cadmium coating thus becomes an important scientific and engineering challenge. Threaded fasteners and power screws. Chapter 10.1 Introduction. A lay person may consider threaded fasteners to be the most mundane and uninteresting of all machine elements. Looking deeper, the engineer finds that these seemingly simple components exist in amazing variety of design details representing remarkable ingenuity. The economic implications of fastener design, both threaded and non-threaded, such as rivets, are tremendous. For example, the airframe of a large jet aircraft has approximately 2.4 to 10 to the 6 fasteners, costing about $750K in 1978 dollars. The safety implications of the fasteners used in many machines, particular vehicles carrying people, are obvious. Corrosion considerations are often critical. For differences in materials used in fasteners and clamped members give rise to potential galvanic cells. Many fasteners must be designed for easy, low-cost assembly. Ease of disassembly is often important too, where servicing and parts replacement must be considered. On the other hand, difficulty of disassembling is also important for resisting vandalism. As a further requirement, ease of disassembly for scrapping and recycling components and materials is becoming increasingly important. It has facetiously suggested that automobile fasteners would withstand safely all operating and safety-related crash loads, but be so designed that upon dropping the car from a height of several feet, all fasteners would fail, permitting the pile of components to be easily sorted for recycling. In summary, the problem of devising bolts that are lighter in weight, cheaper to manufacture and use, less susceptible to corrosion, and more resistant to loosening under vibration presents a never-ending challenge to the engineer working in this field. In addition, nearly all engineers are considered with the selection of fasteners and thus need to be somewhat knowledgeable of the choices available and the factors governing their selection and use. Power screws of various descriptions are also commonly encountered in machine components. Their engineering and design has much in common with the engineering and design of threaded fasteners. Chapter 10.2 Threaded forms, Terminology, and Standards. Figure 10.1 illustrates a basic arrangement of the heli thread wound around a cylinder as used on screw-type fasteners, power screws, and worms. Pitch, lead, angle, and hand of thread are defined by the illustrations. Virtually all bolts and screws have a single thread, but worms and power screws sometimes have double, triple, and even quadruple threads. Unless otherwise noted, all threads are assumed to be right-hand. Figure 10.2 shows the standard geometry of screw threads and used on fasteners. This is basically the same for both unified and inch series and ISO International Standard Organization metric. Threads. Standard size of two systems are given in tables 10.2 and 10.1. Table 10.1 shows the fine thread series. The pitch diameter dp is the diameter of the cylinder on a perfect thread, where the width and the thread and groove are equal. The stress area tabulated is based on the average of the pitch and root diameters. This is the area used for the P divided by A stress calculations. It approximates the smallest possible fracture area considering the presence of the helical thread, the official American national standard from which the information in table 10.1 was taken at ANSI. B1.1, which is published by the American Society of Mechanical Engineers and sponsored jointly by the ASME of the Society of Automotive Engineers. The standard also defines an extra fine thread series and an 8 constant pitch thread series. The great majority of screws and bolts with the inch series threads, however, conform to the standard coarse and fine series listed in 10.1. One of the earliest thread forms to be used was the V thread, which had a profile essentially like the modern profile shown in figure 10.2, except that the 60-degree angled sides extended to sharp points at the crest and root. The sharp crests were vulnerable to damage, and the sharp roots caused severe stress concentration. The previous American standard and the former British standard modified the sharp crest and roots in slightly different ways. Both countries, when agreed on the unified standard illustrated in figure 10.2. More recently, all major nations have agreed on the ISO threads. Different applications require screw threads with different degrees of precision and different amounts of clearance between the mating threaded members. Accordingly, screw threads are manufactured to fit to different classes of fit. For unified threads, 3 classes are standard, with class 1 representing the loosest fit and the greatest tolerances, and class 3 the tightest fit and smallest tolerances. Obviously, class 3 threaded members are also the most expensive. The tolerance zones for nut and screw are illustrated in figure 10.3. Detailed information regarding dimension, fits, and tolerances for the various inch series threads may be found in ANSI B11. Figure 10.4 illustrates most of the standard thread forms used for power screws. Acme threads are the oldest and still in common use. The Acme stub is sometimes used because it is easier to heat treat. The square thread gives slightly greater efficiency but is seldom because of the difficulties in manufacturing the 0-degree thread angle. Furthermore, it lacks availability of Acme thread to be used with a split nut too, the 2 halves of which can be moved together to compensate the thread wear. The 5-degree thread angle of the modified square thread partially overcomes these objections. The buttressed thread is sometimes used for resisting large axial forces in one direction. Standard sizes are given in 10.3. For power screws and multiple threads, it should be noted that the number of thread per inch defined as a reciprocal of the pitch, not the reciprocal of the lead. The threads discussed in this section are all wound around a cylinder, as shown in figure 10.1. Other threads, such as those in the pipe and on wood screws, are wound around a cone. Chapter 10.3 Power screws. Power screws, sometimes called linear actuators or translation screws, are used to convert rotary motion of either the nut or the screw to relatively low linear motion of the mating member along the screw axis. The purpose of many power screws is to obtain great mechanical advantage in lifting weights, as in screw-type jacks, or to exert large forces in the presses and tensile testing machines, home garbage compactors, and C-clamps. The purpose of others, such as the micrometer screws or lead screw of the lathe, is to obtain precise positioning of the axial movement. Figure 10.5 shows a simplified drawing of 3 different screw jacks supporting a weight. Note in each way shaded member connected to the handle rotates and that a ball thrust bearing transfers the axial force from the rotating to the non-rotating member. All 3 jacks are, here's the chart of the screw threads. Here's the weight supported by these screw jacks. In each screw jack, only the shaded member rotates. Basically the same, but let us use figure 10.5c for determining torque. Fa must be applied to the nut in order to lift a given weight. Turning the nut in figure 10.c forces each portion of the nut thread to climb an inclined plane. Let us represent this plane by unwinding a portion of one turn of the screw thread, as shown in the lower left portion of 10.6. And if a full turn was developed, a triangle would be formed, illustrating the relationship. A segment of the nut is represented in 10.6 by the black block acted upon the load W. Force Fn and tangential force Q. Note that force Q times dm divided by 2 represents the torque applied to the nut segment. Summing the tangential forces acting on the block gives, as noted, the torque corresponding to force Q. Since the small block represents a typical segment of nut, integration over the entire thread surface in contact results in the same equations except QWN replaced by QWN, where the latter represent the total tangential, vertical, and normal loads respectively acting on the thread. Thus the equation for the torque to lift the load is T equals QDM divided by 2. Note that the torque T is also equal to Fa in figure 10.5c, since the lead L rather than the lead angle lead angle Greek letter is usually known as the standard value. A more convenient form of the torque equation is obtained by dividing the numerator and denominator by cos. Is that okay? I need to Google this. What kind of Greek letter, and then substituting L divided by pi dm for the tan Greek letter. This gives this equation. Most applications of power screws require a bearing surface or thrust collar between the stationary and rotating members. In figure 10.5, this function is served by the ball thrust bearing of diameter dc. In many cases, a simple thrust washer is used. The coefficient of friction of the collar or washer or bearing is Fc. Then the added torque is required to overcome collar friction is Wfc dc divided by 2, and the total torque required to lift the load W is T equals W dm divided by 2 times this huge equation. For the special case of the squared thread, cos A alpha n equals 1, and 10.4 simplifies to this equation. For Acme thread, cos alpha is so nearly equal to the unity, 10.4a can be used without significant error, particularly when one considers inherent invariability of the coefficient of friction. Several remaining equations in the section will be developed for the general case and for the special case of the squared thread. Acme thread problems can usually be handled with sufficiently accurately using the simpler squared thread equations. In all cases, however, an awareness of more complete general equations provides that additional insight. The preceding analysis pertaining to raising a load or to learning the rotating member against the load. The analysis of lowering a load is exactly the same, that the directions of Q and Fn are reversed. The total torque required to lower the load is this equation for general case and for special case of the squared thread. This equation. Chapter 10.3.1 Values of friction coefficients. When a ball or roller thrust bearing is used, usually low enough, the collar friction can be neglected, thus eliminating the second term from the preceding equations. Wait, what? Really? Okay, that doesn't sound like good engineering. Okay, when a plain thrust collar is used, values of F and Fc vary generally between about 0.08 and 0.20 under conditions of ordinary service and lubrication for common materials of steel against cast iron bronze. This range includes both starting and running friction, with starting friction being about 1/3 higher than running friction. Special surface treatments and coatings can reduce these values by at least half. So what happens when you get to like nanobots, you know? Anyways, values of thread angle in the normal plane. Figure 10.7 shows the thread angle measured in normal plane. It follows from figure 10.7 that for small helix angles, cosine Greek letter is often taken as unity. Chapter 10.3.3 Overhauling and self-locking. A self-locking screw is one that requires a positive torque to the lower load, and an overhauling screw is one that has low enough friction to enable the load to lower itself. That is, a negative external lowering torque that must be maintained to keep the load from lowering if collar friction can be neglected. 10.5 where T is greater than equal to 0 shows that the screw is self-locking. For a square thread, this simplifies to F is greater than L divided by pi dm. A word of caution is appropriate at this point. Even though the screw is self-locking under static conditions, it may overhaul when exposed to vibration. This is particularly important for screw fasteners and tend to loosen because of vibration. Chapter 10.3.4 Efficiency. The work output of a power screw for one revolution of the rotating member is the product of force times distance, or WL. Corresponding work input is 2 pi t. The ratio of WL divided by 2 pi t is equal to efficiency. Substituting the expression for t in equation 10.4 with collar friction neglected gives efficiency E, or for the equals to the equation. For the case of squared thread, efficiency, new equation, equals. It is always reassuring to approach the analysis from two different points of view and arrive at the same answer. Accordingly, equation 10.8 can be derived by defining efficiency as the ratio of torque required to raise the load with F0 divided by the actual torque required. This simple exercise is left to the reader. Substitution of 10.1 into equation 10.8 gives a routine simplification. equation for squared thread, new equation. Figure 10.8 gives a plot efficiency as a function of coefficient of friction and lead angle. That it is worth taking time to note the plots come out as expected. In the higher coefficient friction, the lower the efficiency. Efficiency approaches 0 as lead angle approaches 0, because this represents a condition corresponding to a case where a large amount of friction work is required when moving the block in figure 10.6 around and around the thread without lifting the load very much. Efficiency again approaches 0 as lead angle approaches 90 degrees, and efficiency also slightly decreases slightly as the thread angle A alpha is increased to 0 to 14.5. Furthermore, the efficiency would also approach 0 if the thread angle were to approach 90 degrees. This is so the greater the angle that the thread surface makes with a particular plane perpendicular to screw axis, the greater it must be the normal force in order to provide a given load force. Increasing the normal force increases the friction force correspondingly, because the relationship between them is simply the coefficient of friction. To illustrate this, imagine pushing down on a flat washer and rotating back and forth against the flat surface. Now change the flat washer into a conical washer and put it down in the same force you maintain against the mating conical surface. It will be more difficult to turn back and forth because the wedging action increases the normal force and therefore the friction force. Finally, imagine cone angle steepened. Now the wedging action may be so great it becomes almost impossible to turn the washer. Chapter 10.3.5 Rolling contact. Figure 10.9 shows a ball bearing screw. The sliding friction between the screw and the nut threads have been replaced with approximately rolling contact between the balls and the grooves in the screw and nut. This decreases friction drastically with efficiencies commonly 90% or higher. Because of the low friction, ball bearing screws are usually overhauling. This means that the brake must be used to hold the load in place. On the other hand, it means that the screw is reversible in that linear motion can be converted to relatively rapid rotary motion, and applications for which this look at this, looks pretty cool, is desirable. Operation is smooth without the slipstick action commonly observed in regular power screws. The load carrying capacity of ball bearing screws is normally greater than that of regular power screws of the same diameter. The smaller size and lighter weight are often an advantage. On the other hand, buckling problems and critical speed problems can be more severe. Cleanliness and thin film of lubricant are important to ball bearing screws, where dry operation is unavoidable. Load capacity should be reduced as much as 90%. Ball bearing screws are commonly used in aircraft landing gear retractors, large jet aircraft engine thrust reversers, actuators, automatic door closers, antenna drives, hospital bed adjusters, machine tool controls, and numerous other applications. For design information, see ThompsonBSA.com. Power screws are also available with patented arrangements for positioning rollers in the nut that contact the screw thread surface with the line contact rather than a point contact as with the ball bearing screw. These roller equipped nuts provide low friction together with very high load carrying capacity. Hence they are used in offshore oil rig elevators, heavy construction jacks, and mining machinery. Chapter 10.4 Static Screw Stresses. This section applies equally to power screws covered in previous section and to thread fasteners as discussed in following sections. Let us consider separately the various stresses of which these members are subjected. Chapter 10.4.1 Torsion. Power screws in operation and thread fasteners during tightening are subjected to torsional stresses. Where this equation, where D is the thread root diameter, dr obtained from figure 10.4 or other tables 10.1 and 10.2. If the screw or bolt is hollow, then joules should be substituted for this new joules equation in the stress equation, where di represents the inside diameter. Where the collar friction is negligible, the torque transmitted through a power screw is the fully applied torque. With threaded fasteners, an equivalent of substantial collar friction is normally present, in which case it is customary to assume that the torque transmitted through the threaded section is approximately half the wrench torque. Chapter 10.4.2 Axial Load. Power screws are subjected to P divided by A tensile and compressive stresses. Thread fasteners are normally subjected to only tension. The effective area for threaded fasteners is the tensile stress area, AT. For power screws, a similar tensile stress area could be computed, but this is not ordinarily done because axial stresses are seldom critical. A simple and conservative approximation of power screw axial stresses can be based on the minor or root diameter dr. The distribution of the axial stress near the ends of the loaded portion of a screw is far from uniform. It is not of concern now because axial stresses are quite low in power screws, and because the threaded fasteners should always have enough ductility to permit low local yielding at thread roots without damage. When we consider the fatigue loading of bolts, the stress concentration is very important. Chapter 10.4.3 Combined Torsion and Axial Load. The combination of stresses that have been discussed and can be treated in the normal fashion presented in sections 4.9 and 4.10, with the distortion energy theory used as a criterion for yielding. With threaded fasteners, it is normal for some yielding to occur in thread roots during initial tightening. Thread bearing stress and its distribution among the threads in contact. Figure 10.11 illustrates the force flow through a bolt and nut to clamp two members together. Compression between the screw and nut threads exists at threads numbered 1, 2, and 3. This type of direct compression is often called bearing. The area used for P divided by A stress calculation is the projected area for each thread, pi d squared minus d squared initial divided by 4. The number of threads in contact seen from the figure to be T divided by P. Thus, the diameter DI is the minor diameter of the internal thread. For threaded fasteners, this can be approximated by dr, which is tabulated in table 10.1. Exact values are given in ANSI B1.1 1974 in various handbooks, but these are not usually necessary because thread bearing stresses are seldom critical. Equation 10.10 gives an average value of bearing stress. The stress is not uniformly distributed because of factors of bending in threads as cantilever beams and manufacturing variations from theoretical geometry. Furthermore, a study of 10.11 reveals two important factors causing thread 1 to carry more than its share of the load. The load is shared among three threads as redundant load carrying members. The shortest path is through thread 1, thus it carries the greatest portion of the load. The applied load causes the threaded portion of the bolt to be in tension, whereas the mating portion of the nut is in compression. The resulting deflection slightly increased bolt pitch and decreased nut pitch. This tends to relieve the pressure on threads 2 and 3. The problem of overcoming this tendency and obtaining more nearly equal distribution of loads among the threads in contact is an important one, as will be seen when considering the fatigue loading of bolts. This problem continues to challenge the ingenuity of engineers concerned with fastener design and development. These three following ideas have been used. Making the nut softer material than the bolt so that highly loaded first thread will deflect, thereby transferring more of the load to other threads. This may require increasing the number of threads in contact in order to maintain adequate strength. Manufacturing the nut threads with slightly greater pitch than the bolt threads so that the two pitches are theoretically equal after the load is applied. The thread clearances and precision of the manufacturer must, of course, be such that the nut and bolt can be readily assembled. Modifying the nut design as shown in 10.12. Here the nut loading puts the region of the top threads in tension, thus causing elastic changes in pitch that approximately match the changes in the bolt pitch. Such special nuts are expensive and have been used only in critical applications involving fatigue loading. Oh shit. Modifying the nut design as shown in figure 10.12. Here the nut loading puts the region on top of threads in tension, thus causing the elastic changes in pitch that approximately match the applications involving fatigue loading. Chapter 10.4.5 Thread shear, stress, and nut thickness requirement. With reference to 10.11, the nut material is weaker than the bolt material in shear. A sufficient overload would strip the threads from the nut along the cylindrical surface A. If the bolt material is weaker in shear, the failure surface would be B. From the geometry shown in figure 10.2, the shear area is equal to pi d, where d is the diameter of the shear fracture surface involved. Let us now determine the nut thickness needed to provide a balance between the bolt tensile strength and thread stripping strength if both members are made of the same material. The bolt tensile force required to yield the entire threaded cross section is AYF bolt, where D is the major diameter of the thread with reference to 10.11. The bolt tensile load required to yield the entire thread stripping failure surface of the nut is based on parabolic stress distribution. Since nuts are usually softer than bolts in order to allow slight yielding of top threads and thus distribute the load more uniformly among the threads in contact, the standard nut thickness is approximately 7 divided by 8D. Transverse shear loading and providing transverse alignment. Bolts are sometimes subjected to transverse shear loading as illustrated in figures 4.3 and 4.4 and discussed in section 4.3. Often these shear loads are transmitted by friction, where the friction load carrying capacity is equal to the bolt tension times the coefficient of friction at the clamped interface. For the double shear illustrated in figure 4.4, the friction load capacity would be twice this amount. Sometimes bolts are required to provide precise alignment of mating members and are made with pilot surfaces as shown in figure 10.13. Chapter 10.4.7 Column loading of power screws and associated design details. Long power screws loaded in compression must be designed by buckling mind. Sections 5.10 and 5.14 apply. Before we become involved with this, however, it is important first to make sure it is necessary to subject the screws to compression. Often the simple redesign permits the screws to be in tension. For example, 10.14a shows a press with the screws in compression. 10.14b shows an alternative design with the screws in tension. The second is obviously to be preferred. The two presses in 10.14 provide excellent examples for using the force flow concept described in 2.4. In the press shown in 10.14a forces the flow from the moving press head through the screws to the ball thrust bearings, then through top, sides, and bottom of the frame, and finally into the bottom surface of the material being compressed. Because all sections of the frame carry load, they are drawn heavily. In contrast, the press shown in figure 10.14b has a short load path from the press head through the screws to the ball thrust bearings and then through the bottom of the frame to the material being compressed. Because they carry no significant loads, the sides of the top of the frame can be much lighter. It is almost desirable to keep a load paths as short and compact as possible. Another advantage of the press figure in 10.14b is the axial free play of its screws is easily controlled because all four thrust bearings involve surfaces of the bottom frame member. In contrast, the screw axial free play in figure 10.14a involves tolerances and deflections of the screw length between the thrust bearings and frame height between thrust bearings. A construction detail of the press is worth noting. For the assembly of press in figure 10.14b, the thrust collars bearings against the plain thrust washers at the top surface of the bottom frame member must be removable from the screws. Note that the only load carried by these thrust collars is the gravity load of the press head when no material is being compressed. Chapter 10.5 Threaded Fastener Types. In figure 10.15 shows 4 basic types of thread fasteners. Screws and bolts are by far the most common types, so the difference between them is the only one of intended use. Bolts are intended for use with nuts. Screws are intended for screwing into tapped holes. Sometimes screws are supplied with a captive washer under the head, in which case they are called sems. Sems have assembly time and eliminate the possibility that a screw will be installed without its specified washer. A stud is threaded on both ends until it is usually screwed permanently into a tapped hole. Threads on the two ends may or may not be identical. A threaded rod is the least common type. It is usually used when a very long threaded member is desired. A thread rod can often be purchased in lengths of few feet and then cut off as required. Technical reference charts are available online at AmericanFastener.com for cap screws, bolts, nuts, machine screws, studs, washers, and so on. Grade markings and mechanical properties for steel fasteners and thread terminology are also given. The website MachineDesign.com provides general information for thread fasteners as well as other methods for fastening and joining. Figure 10.16 shows the most common fastener head types. As a rule, a bolt can serve as a screw by using it with a tapped hole. An exception of this rule is carriage bolt. Carriage bolts are used with soft material so that square corners under the head can be forced into the material, thereby preventing the bolt from turning. Hexagonal head screws and bolts are commonly used for connecting machine components. Sometimes they cannot be used because of insufficient clearance to put a socket or end wrench on the head. In such cases, the hexagonal socket head is often used. In recent years, the need for screws that are resistant to tampering by unauthorized personnel has increased. Figure 10.17 illustrates the several proposed solutions that have been marketed, and an almost endless number of special threaded fastener designs continue to appear. Some are specially designed for the specific application. Others embody proprietary features that appeal to a segment of the fastener market. Not only is the ingenuity required to devise better threaded fasteners, but also to use them to the best advantage in the design of a product. Chow gives several examples of reducing a product cost through judicious selection and application of fasteners. Chapter 10.6 Fastener Materials and Methods of Manufacture. Materials for screws, nuts, and bolts are normally selected for the basis strength of weight, corrosion resistance, magnetic properties, life expectancy, and cost. Most fasteners made from steel specifications standardized by the Society of Automotive Engineers and summarize tables 10.4 and 10.5. Heading is done cold for diameters up to 3 4/4 inches and heated for larger sizes. Threads are usually formed by rolling between dies and force the material to cold form into thread contour and die grooves. Threads thus formed are stronger than cut or ground threads in fatigue and impact because of cold working, favorable residual stresses at the thread roots, and more favorable grain structure. Because of these advantages, high-strength screws and bolts should have rolled threads. Furthermore, the greatest fatigue strength is obtained if the threads are rolled after heat treatment, so that the resulting work hardening and favorable residual stresses are not lost. Fasteners are also made of aluminum, brass, copper, nickel, mono, Inconel, stainless steel, titanium, beryl, lithium, and various plastics. For any application, the fastener material must be considered in connection with the potential corrosion problems associated with the anticipated environment and in other metals involved. In addition, appropriate coating should be considered for corrosion protecting to reduce the friction and wear. Bolt tightening and initial tension. For most applications, screw and nut bolt assembly should ideally be tightened to produce an initial tensile force Fi, nearly equal to the full proof load, which is defined as the maximum tensile force that does not produce a normally measurable permanent set, where A is the tensile area of the thread and K is the constant, usually specified in a range of 0.75 to 1.0. For ordinary applications involving static loading, let K is similar to 0.9, or Fi equals 0.9 ASP. Briefly, the rationale behind this high-end and initial tension is the following. For loads tending to separate rigid members, the bolt cannot be increased very much unless the members do actually separate, and the higher the initial bolt tension and the less likely the members are to separate. For loads tending to shear the bolt, the higher the initial tension, the greater friction forces resisting a relative motion in shear. Further implications of the initial bolt tension for fatigue loading will be discussed in section 10.11. Another point to be considered is the tightening of a screw or nut imparts a torsional stress to the screw or bolt, along with initial tensile stress. During initial use, the screw or bolt usually unwinds very slightly, revealing most or all of the torsion. To illustrate this point, figure 10.18 shows the loads applied to a bolt and nut assembly during tightening. Remember that the frictional forces and associated torques vary considerably with materials, finishes, cleanliness, lubrication, and so on. This figure assumes the ideal case of the bolt axis being exactly perpendicular to all clamped surfaces so that no bending is imparted to the bolt. The difference between static and dynamic coefficients of friction has an important effect. Suppose that the wrench torque T1 is progressively increased to the full specified value of continuous rotation to the nut. The resulting clamping force Fi will be greater than the nut rotation is allowed to stop momentarily at say 80% of full torque. The greater the value of static friction may then be such that the subsequent application of full torque will not cause further nut rotation, with the result Fi be less than desired. Figure 10.18 also illustrates the bolt stress, both initially and finally. For clarity, the stress element shown in this is shank. The yield limited stresses shown would be more appropriately be associated with a cross-section in the plane of a thread. An important point that does not show up in figure 10.18 is the torsional stress is also dependent on thread friction between the bolt and nut. For example, if there is considerable thread friction, a substantial holding torque T4 will be needed to prevent bolt rotation, and for the torsional stresses in the bolt can be so great that yielding is reached to prevent bolt rotation, and the torsional stresses in the bolt can be so great that the yielding is reached at relatively low values of Fi. Figure 10.19 illustrates the implications of preceding terms of the initial tension that can be achieved with the given bolt, the amount of elongation that can be achieved before over-tightening fractures the bolt. An accurate determination of the bolt tensile load produced during tightening is not easy to make. One accurate way is to use a special bolt with axially drilled hole in which an electric resistance strain gauge is mounted. Another method employs ultrasonic equipment to measure the length of the bolt before and after tightening, a method long used for the low production rate assembly of critical parts is to measure with the micrometer the length of the bolt before the assembly and then to tighten the nut until the bolt elongates the desired amount. This can only be done, of course, if both ends of the bolt are accessible. A modern method suited for automated assembly operations involves continuous monitoring of the wrench torque and nut rotation. When a computer determines that the relationship of these quantities indicates the onset of yielding, the wrench is disengaged. For a more mundane but more often effective method is to seat the surfaces by tightening of the screw or nut or very tight and then loosening it. Tighten the screw or the nut finger tight and turn it a predetermined additional angle. The most common method of tightening a bolt a measured amount is probably use a torque wrench. The accuracy of this method can be seriously limited by the variations in friction. Normal torque wrench usage controls initial tension within perhaps plus minus 30%. With special care, plus minus 15% is considered reasonable. An equation relating to tightening torque to initial tension can be obtained from equation 10.4 by recognizing that the load W of a screw jack corresponds to Fi for a bolt, and collar friction in the jack corresponds to friction in the flat surface of the nut or under the screw head. When we use 0.15, an average rough coefficient of the friction, equation 10.4 gives for standard screw threads, where D is the nominal measured diameter of the thread. Remember, this is only the approximate relationship dependent on the average conditions of thread friction. A common way to tighten a screw or nut is, of course, summarily to choose a conventional wrench and tighten it until it feels right. Although this method would never be specified for a critical fastener, an engineer would have some idea how tight ordinary mechanic might be expected to tighten bolts of various sizes using ordinary wrenches. A study made near the turn of the 20th century indicated to be F equals 16,000 D diameter inches. Despite its limitations, EQE does not reveal the important fact of natural tendency to tighten the initial tension values that increase the first power of the diameter, whereas the tensile load carrying capacity of bolts increases with the square of the diameter. This means that small bolts and screws tend to get twisted off and that very large ones tend to be under-tightened. A word of caution is in order regarding the lost bolt initial tension during operation. When rigid parts are bolted together, the elastic deflection of the parts may be hundredth of a millimeter or less. Should the loading cause any creep or subsequent flattening of minute high spots on the surfaces, much of the bolt initial tension will be lost. Initial tension can also be lost through wear or corrosion of the mating surface by squeezing out the surface films. Tests have shown that a typical joint loses about 5% of its initial tension within a few minutes, and that various relaxation effects result the loss of about another 5% within a few weeks. Long-term stress relaxation is a problem of high-temperature joints, as in jet engines and nuclear reactors. These applications require bolts made of special high-temperature alloys. Because of these losses in initial tension, it is sometimes necessary to retighten bolts periodically. Chapter 10.8 Thread Loosening and Thread Locking. An inherent advantage of these thread fasteners for many applications is that it can be easily and non-destructively disassembled. A disadvantage has plagued engineers since early days and sometimes loosen and disassemble themselves. The concept explaining why threads loosen, a very simple one, is given in the next two paragraphs. In figure 10.6, the tightening of a nut is represented by a small block on an inclined plane. If friction is sufficient to prevent the block from sliding back down the plane, the thread is said to be self-locking. All threaded fasteners are designed to have small enough helix angle and high enough coefficient of diffraction F to be self-locking under static conditions. However, if any relative motion occurs between the bolt and nut threads, the nut tends to loosen. This relative motion is often caused by vibration, but it can have other causes such as differential thermal expansion or slight dilation and contraction of the nut with changes in axial bolt load. This dilation and contraction represents very small changes in the nut thread diameter and is due to the wedging action of the loaded tapered threads. For example, this would not occur with a square thread. To understand why any relative motion tends to cause thread loosening, place a small solid object on a slightly inclined plane and lightly tap the edge of the plane in any direction with the tapping diameter just sufficient to cause the slightest relative motion. The small object inexorably slides down the incline. An analogy familiar to car drivers in northern climates is that of car on an ice-covered crown road. If traction is lost by braking or by applying too much torque to the driving wheels, the car slides laterally to the side of the road. Here, the friction between rubber and ice is ample to prevent lateral sliding as long as there is no relative motion, but not when there is sliding in any direction. But the following are among factors influencing whether or not threads loosen. The greater the helix angle, the greater the loosening tendency. Thus, coarse threads tend to loosen more easily than fine threads. The greater the initial tightening, the greater the frictional force that must be overcome to initiate loosening. Soft or rough clamping surfaces tend to promote slight plastic flow, which decreases the initial tightening tension and thus promotes loosening. Surface treatments and conditions that tend to increase the friction coefficient provide increased resistance to loosening. The problem of thread loosening has resulted in numerous ingenious special designs and design modifications, and it continues to challenge the engineer to find effective and expensive solutions. A brief summary of the common solutions used to date follows. Figure 10.2 shows the familiar helical and tooth-locked washers. They work on the principle of flattening the hard, sharp corner projections that tend to bite into the mating metal surfaces and resist loosening by a wedging action. Slotted and castle nuts are used with cotter, pin, or wire that fits in a diametrically opposite slots and passes through a drilled hole in the bolt. This provides a positive lock but may require slight over-tightening or under-tightening in order to align a pair of slots with the bolt hole. Lock nuts generally are of two types, free spinning and prevailing torque. Figure 10.22 shows three varieties of free spinning lock nuts. These spin on freely until seated and then produce the deflection when tightened. That also causes a gripping of the mating bolt threads. The lock washers shown in 10.2 are also free spinning. Thread locking devices, these sites, MachineDesign.com and AmericanFastener.com, present additional information about lock nuts and locking devices. Figure 10.23 illustrates a representative prevailing torque lock nuts. These develop a friction torque as soon as the threads are fully enlarged. Hence, they require wrenching to the final seated position and have strong tendency to stay in position even when not tightened. Prevailing torque nuts or fasteners usually provide the best solution in critical applications, particularly when extreme vibration is involved. Sometimes two standard nuts are used together to obtain a locking action. The extra standard nut or jam nut is installed first and then tightened gently. Then the standard nut is installed and fully tightened against the extra nut. Another means of providing thread locking is to coat the mating threads with special adhesive or lacquer, which may act to seal the threads against fluid leakage. These adhesives are available in various grades, depending on whether or not the ease of subsequent disassembly is important. Sometimes the adhesive coating is contained in a small capsule that is attached to the threads during manufacture. The capsule breaks during assembly, and the adhesive flows over the threaded surfaces. Note that all the thread locking methods discussed can be applied to screws as well as to nuts and bolt combinations. Bolt tension with external joint separating force. Chapter 10.9. Bolts are typically used to hold parts together in opposition forces, tending to pull or slide them apart. Common examples are connecting rod bolts, cylinder head bolts, and so on. Figure 10.24a shows a general case of two parts connected to the bolt and subjected to external force tending to separate them. Figure 10.24 shows a portion of this assembly as a free body. In this figure, the knot has been tightened, but the external force has not been applied. The bolt axial load FB and the clamping force between two plates FC are both equal to the initial tightening force Fi. Figure 10.24c shows the same numbers as the free body after external force Fe has been applied. Equilibrium considerations require one or both of the following: an increase in FB and a decrease in FC. The relative magnitudes and changes FB and FC depend on the relative elastics involved. To assist the reader in visualizing the significance of relative elasticities in bolted joints, figures 10.25 and 10.26 illustrate two extreme cases. Figure 10.25a shows a covered plate bolted on the end of the pressure vessel. The key feature is the thick rubber gasket, which is so soft that other parts can be considered infinitely rigid in comparison. When the nut is tightened to produce initial force Fi, the rubber gasket compresses appreciably. The bolt elongates negligibly. Figure 10.25b and 10.25c shows the detail of the bolt and the clamped surfaces. Note the distance defined on grip G. On initial tightening, Fb equals Fc equals Fi. Figure 10.25d shows the change of Fb and Fc as separating load Fe is applied. The elastic stretch of the bolt caused by Fe is so small that the thick rubber gasket cannot expand significantly. Thus, the clamping force Fc does not diminish the entire load of Se. Goes into increasing bolt tension. Figure 10.26 illustrates the extreme in relative stiffness. The clamped members are rigid metal parts with precision ground mating surfaces and no gasket between them. The bolt has a center portion made of rubber. In this case, the initial tightening stretches of the bolt. It does not significantly compress the clamped members. Figure 10.26d shows that this is the case. The entire separating force is balanced by decreased clamping force with no increase of the bolt tension. The only way a tension in the rubber bolt can be increased to increase its length, and this cannot happen with external force great enough to separate physically the mating clamped surfaces. The extreme cases illustrated in figures 10.25 and 10.26 can, at most, be approximated. Let us now investigate the realistic case at which both the bolt and the clamped members have applicable stiffness. Joint tightening both elongates the bolt and compresses the clamped members. From figure 10.24, the separating force must be equal to the sum of the increased bolt force plus the decreasing bolt force, or Fe equals delta Fb plus delta Fc. By definition, delta Fb equals Kb squiggly and delta Fc equals Kc squiggly, where Kb and Kc are the spring constant of the bolt and clamped members, respectively. Equations 10.13 are represented graphically in figure 10.27. Also represented in figure are two additional points worthy of notice. When external load is sufficient enough to bring clamping force to zero, the bolt force and the external force must be equal. Hence, the figure shows Fc equals 0 and Fb equals Fe for values of Fe in excess of A. When the external load is alternately applied and removed, fluctuation of Fb and Fc are conveniently determined from the figure as shown, where the grip G represents the approximate effective length for both. Two difficulties that commonly arise in estimating Kc are the clamped members may consist of stack of different materials representing springs in series. For this case, the use of formula for the spring rate of springs in series. The effective cross-sectional area of the clamped members is seldom and easy to determine. This is particularly true if members have irregular shapes, or if they extend a substantial distance from its bolt axis. An empirical procedure sometimes used to estimate AC is illustrated in figure 10.28. An effective experimental procedure for determining the ratio of Kb and Kc for a given joint is to use a bolt equipped with an electric resistance strain gauge to monitor bolt length ultrasonically. This permits a direct measurement of Fb both before and after Fe is applied. Some handbooks contain rough estimates of the ratio Kc divided by Kb for various general types of gasketed and ungasketed joints. For a typical ungasketed joint, Kc is sometimes taken as 3 times Kb, but with careful joint design, Kc equals 6 Kb is readily attained. Chapter 10.10 Bolt or selection for static loading. The primary loading applied to bolts is tensile shear or a combination of the two. Moreover, some bending is usually present because clamp surfaces are not exactly parallel to each other and perpendicular to the bolt axis, and because the loaded members are somewhat deflected. Before we consider more sophisticated examples, it is important to recognize that screws and bolts are sometimes selected rather arbitrarily. Such is the case of non-critical applications whose loads are small, for example, and the attachment of license plates to automobiles. Almost any size would do, including sizes considerably smaller than those used. Selection is a matter of judgment based on such factors in appearance, ease of handling and assembly, and cost. Even in bolt applications with known significant loads, larger bolts than necessary are sometimes used because the smaller size doesn't look right, and the cost penalty for using larger bolts is minimal. Chapter 10.11 Bolt selection for fatigue loading. Fundamentals. Bolt fatigue involves fluctuating tension, commonly accompanied by small amounts of alternating friction forces or separate members such as dowel pins. This section involves the application of principles and concepts of Chapter 8 to bolts. Because of initial tightening to tension, bolts inherently have mean stress. In addition, stress concentrations are always present in thread roots. These 2 points are treated in sections 8.9 and 8.11. Table 10.6 gives approximate values of fatigue strength, stress concentration factor Kf for standard screws and bolts. Note that one-rolled threads have lower values of Kf because the work hardening of residual stresses, and hardened threads have higher values of Kf because of their greater notch sensitivity. For thread finishes of good commercial quality, these values may be used with a surface factor Cs of unity. Section 10.4 and figures 10.11 and 10.12 explain the tendency for the bolt load to be carried by the thread nearest to the loaded face of the nut, and noted to the degree to which the stresses were concentrated in this region was influenced by the nut design. This is one reason why actual values of Kf may differ from those given in Table 10.6. Chapter 10.11 Analysis of bolt fatigue strength at high and low initial tightening tension. This is a lot of tension. Oh my god. Oh my god. 5-minute break. Chapter 10.11 Analysis of Point 1. Figure 10.34 represents analysis of fatigue strength of M10 times 1.5 bolt fabricated from steel from having properties identical to the listed of SAE class 8.8 in table 10.5. The bolt is installed in a joint with Kc equals 2 kb and subjected to the external load, which fluctuates between 10 and 9 kN. The case 1 curves in figure 10.34a correspond to an initial tightening force of 10 kN. Each time an external load is applied, the bolt force increases, the clamping force decreases, with the sum of two effects being equal to the external load of 9 kN, where when the external load Fe is removed, the bolt axial load of Fe and the clamping force Fc revert to the initial value of 10 kN. The case 2 curves correspond to a bolt initial tension equal to the full yield strength. It must be understood that this represents an extreme value that would never be specified. Following the procedures given in Chapter 8, recall particularly Section 8.11 and Figure 8.27, the treatment of yielding and the residual stresses, and Section 4.14, Figures 4.42 and 4.43, the assumed idealized stress strain curve in figure 10.34b is used with the bolt tightened to the full yield strength. All materials in the cross section is stressed to SY. This means that any small additional bolt elongation causes no increase in load. That is the effective modulus of elasticity for increased load that is not 204 GPa but 0. The associated bolt stiffness is also 0. Hence, the first time joint separating force Fe is applied, all of it's reacted by decreased clamping force. None goes to increasing the bolt load. This is shown in the top curves of figure 10.4a. When Fe is released, the bolt relaxes slightly, and this relaxation is elastic. Hence, corresponding changes in FB and FC are controlled by the elastic values of KB and KC. Elastic bolt relaxation is reversible, so it means that load can be reapplied without yielding. The external load continues to cycle. The bolt and clamping forces fluctuate as shown by the case 2 curves. Let us now determine stress fluctuation at the critical thread root location for cases 1 and 2. For case 1, initial tightening produces a computed thread root stress of sigma Fi divided by AT times Kf. On initial application of the external load, FB is increased to 13 kN with the associated elasticity computed thread stress 672 MPa. The slight yielding reduces the stress to 660 MPa. The elastic reduction stress when FB is reduced to 10 kN is 155 MPa. Thus, the fluctuation in thread root stress corresponds to the case 1 line of figure 10.34b. This is exactly the same fluctuation as shown in case 2. In both cases, the maximum stress corresponds to XY. The minimum stress results from elastic relaxation during the removal of load. Hence, the two cases are represented by the same point in the mean stress alternating stress diagram. The only difference between them is the greater yielding that occurs during tightening and the initial application of load in case 2. Point 2 on figure 10.34c applies to any value of initial tension between 10 and 38.3 kN. If the initial tension exceeds 12.8 kN, the thread root stress reaches point 1 upon initial tightening. Point 3 shows the initial thread root stress after external loading is discontinued. The difference between points 1 and 3 is caused by the bolt yielding during the initial application of Fe. When the machine operation resumes, the thread root operating point moves from 3 back to 2. The safety factor with respect to eventual fatigue failure is 139 divided by 73, or 1.9, because an overload to failure would have increased the alternating stress to 139 MPa. In order to reach the infinite life Goodman line, point 4 corresponds to the external load fluctuation between 0 and 1.9 times 9 kN, or 17.1 kN. Note that with case 1 initial tightening, this overload would not be possible because of the clamping force would drop to 0 and the joint members would separate. It is important to remember that the actual bolt fatigue performance would deviate somewhat from the indicated by the foregoing analysis because deviations of the actual stress strain curve from the assumed idealized curve. Chapter 10.11.2 Advantages of high initial bolt tension. Although tightening bolts to full yield strength should not be specified, it is desirable to specify tightening to the full proof strength where sufficiently close control over the tightening operation can be maintained. The advantages of tightening this tightly are: 1. Dynamic load on the bolt is reduced because the effective area of the clamped members is larger. 2. There is maximum protection against the overloads which can cause joints to separate. 3. There is maximum protection against the thread loosening. It is important to recognize that small amount of thread yielding that occurs when nuts are tightened to a full-proof load that is not harmful to any bolt material of acceptable ductility. Note, for example, that all steels listed in tables 10.4 and 10.5 have an area of reduction by 35%. Chapter 10.12 Bolt Selection for Fatigue Loading Using Special Test Data. The procedures of preceding section indicated for any reasonable bolt tightening, the alternating load capacity of the bolt is independent of initial tightening. Tests confirm that this is generally true unless higher values of initial bolt tension cause significantly greater stiffness of clamped members. The intersection points corresponding to fatigue limited alternating bolt stress for various bolt steels indicate the allowable alternating stress does not increase with ultimate strength, rather, it remains about constant. This too has generally been confirmed by testing. For example, table 10.7, discussed later, makes no distinction between the steels with ultimate strengths 120 and 260 ksi. Despite the points of general verification just discussed, determination of allowable alternating load for bolts by procedures and used in the previous section is clearly very rough. The fatigue limiting the intersection point is highly influenced by small variations in the value taken for SY. Assuming a sharp cornered idealized stress strain curve is of questionable validity in case. Furthermore, the Goodman line is assumed to be valid for a stress variation far removed from the only fatigue test point used as its basis. Similarly, the use of average values KF cannot always reflect accurately the influence of thread profile, thread surface, finish, and treatment, the design of mating threaded member. In order to provide a much more accurate basis for designing critical fatigue-loaded connections and selecting appropriate high-strength bolts, extensive fatigue strength of bolted connections have been made. Some of the results are summarized in Table 10.7, which gives the fatigue-limited alternating nominal stresses for several bolts when properly installed, with the corresponding specified nuts. In views of the fact that the allowable alternating load capacity of 120 ksi, ultimate strength bolt tightened to half its proof load is about the same as of a 260 ksi bolt tightened to its full proof load. We might be tempted to conclude that the two are equivalent for fatigue applications. This is decidedly not the case. Actually, the key to designing modern successful fasteners for critical fatigue application is maximizing initial tension. As previously mentioned, increased initial tension usually increases the stiffness of clamped members, gives greater assurance that the joint separation and increases resistance to thread loosening. Furthermore, increasing initial tension with bolts that are relatively small but highly stressed reduces the bolt stiffness. Smaller bolts may permit the size and weight of associated parts to be reduced. Chapter 10.13 Increasing bolted joint fatigue strength. It may be helpful at this point to bring together a list of various ways by which we can improve the bolt and fatigue strength. Modify its stiffness to decrease the portion of external load that increases bolt tension. Increase KC by using higher modulus materials, flat and smooth mating surfaces, and greater area and thickness of plates and compression. Figure 10.28 how increasing grip can increase AC. Decrease KB by securing the desired clamping force with smaller bolts of greater strength, and by fully utilizing the material strength through more precise control of initial tensioning. Another effective means by reducing KB is to reduce the shank area, as in figures 7.10b and 7.11 and 10.13. Ideally, the shank should be reduced with a very large radius fillet, so that stresses in the fillet are very nearly as high as stresses in the critical thread root. Reducing the modulus of elasticity helps too. Of course, if this can be done without losing material fatigue strength. Modify the nut to equalize the load carriers by the several threads in contact, and be sure that the number of threads in contact is adequate. Reduce the thread root stress concentration by a larger root radius. By U.S. government standard developed for military aircraft, MILB 7838 calls for modifying the basic profile of the external thread given in figure 10.2 using the 0.144p thread root fillet radius. This form is used in some industrial fasteners and in most aerospace tensions bolts up to 180 ksi tensile strength. Standard MILS 8879 specifies the fillet radius of 0.180p, which is used with the aerospace bolts of 180 ksi tensile strength and higher. Obviously, these special bolts materials go beyond the SAE grade listing of table 10.4. Ultra high strength steel bolts have tensile strengths of 220 and 260 ksi. Exotic aerospace bolts of Colombian tantalum, beryllium, and other highly notch sensitive materials sometimes use fillet radii of 0.224p and even 0.268p. A limiting factor to use these fillets with very large radii is associated reduction in thread depth. However, when difficult bolt fatigue problems are encountered, it is well to consider going to a fillet radius of at least 0.144p. Use a material of highest practical approved strength in order to obtain maximum initial tension. Use tightening procedures that ensure values of PI as close as possible as AT/SP. Be sure that the threads are rolled rather than cut, and that threads are rolled after the heat treatment. The greater the strength, the more important it is to roll after hardening. This has been experimentally verified for tensile strengths as high as 300 ksi. After reducing stress concentrations and strengthening the thread as much as possible, be sure that the fillet radius under the bolt head is sufficient to avoid failures at this point. Cold roll this fillet if necessary. Minimize bolt bending. Guard against partial loss of initial tension in service because threads loosen or materials take are a permanent set. Retighten bolts as necessary. Also take steps to ensure the proper tightening when bolts are replaced after being removed for servicing, and to replace bolts before they yield objectionably because of repeated retightening. Oh man, so many problems on tightening. That's not that hot. That's not that tight. Oh my god. It's not that tight. We gotta make more equations. Anyways, Chapter 11, Rivets, Welding, and Bonding. Chapter 11.1, Introduction. As with screw and bolts, rivets exist in great variety and often exhibit remarkable ingenuity. The brief treatment given here attempts to help the reader acquire some familiarity with the choices available and gain a better feel for applying the basic principles of load and stress analysis to them. One might question the appropriateness of including a material on welding and bonding in this book, as these are not really machine components, but since the engineer is frequently faced with the need to choose between various threaded and non-threaded fasteners and the alternatives of welding or bonding, it seems appropriate to treat them here, at least briefly. Had space permitted, another provision of assembly that could have been included in this designing of members so they can be joined with a snap fit. The snap fit assembly can be designed to be permanent or readily disassembled. The potentially very economical and satisfactory joining method is well presented. Other fastening and joint methods are also discussed in 3, and the engineer concerned with the design of mechanical equipment should be familiar with all of these. Chapter 11.2 Rivets. Conventional structural rivets, illustrated in figure 11.1, are widely used in an aircraft, transportation equipment, and other products requiring considerable joint strength. They are also used in the construction of buildings, boilers, bridges, and ships, but in recent decades, these applications have been increasing use of welding. Because of vital safety considerations, the design of riveted connections for these latter applications is governed by construction codes formulated by such technical societies in American Institute of Steel Construction and the American Society of Mechanical Engineers. Figure 2.19 illustrates a typical riveted joint. An analysis of the loading taken by its redundant force paths is discussed in section 2.6. The analysis of tensile and transverse shear stresses in rivets is comparable to that given for bolts in section 10.4. Also, sample problems 10.3, 10.4, and 10.5 are applicable to rivets. Significant initial tension is attainable in rivets by installing them in when they are red from heat. Tension develops upon cooling and thermal contractions, whereas the development of modern welding equipment has reduced the importance of rivets for heavily structural applications. The development of modern riveting machines has greatly expanded their use in fastening smaller components in a multitude of industrial products associated with the automotive, appliance, electronic furniture, business machine, and other fields. Rivets have frequently replaced threaded fasteners with these applications because they cost less to install. Rivets are much cheaper than bolts, and modern high-speed riveting machines, some of which fasten over 1,000 assemblies per hour, provide assembly at low cost. Rivets can also serve as pivot shafts, electrical contacts, stops, and inserts. In comparison with threaded fasteners, rivets are not susceptible to intended loosening, but in some cases, they impede desired disassembly and disservicing. Many readers have had the experience of wanting to disassemble an electrical appliance to make simple repair, only to find that rivets have been used. The appliance is then usually discarded and in a new one purchased. Thus, despite the initial manufacturing economy, these applications of rivets sometimes make questionable economic and ecological sense. On the other hand, making an electrical device so that it cannot be disassembled and tampered with by the lay user may constitute a safety feature. This point illustrates how seemingly simple engineer decisions often require in-depth consideration to many factors. The best overall solution may require imaginative new design approaches to optimize economic safety and ecological decisions. Rivets can be made from ductile material. The most commonly used are carbon steel, aluminum, and brass. Various platings, paints, and oxide coatings may be applied. In general, a rivet cannot provide as strong an attachment as a bolt or screw of the same diameter. As with bolts, care must be taken in selecting materials to be used together because of possible galvanic action. Industrial rivets are of two basic types, tubular and blind. Each type comes with a multitude of varieties. Several tubular rivets are shown in figure 11.2. The semi-tubular version is the most common. The depth of the hole at the end of the shank does not exceed 112% of the shank diameter. Self-piercing rivets make their own holes as they are installed by a riveting machine. Full tubular rivets are generally used with leather, plastics, wood, fabric, or other soft materials. Bifurcated or split rivets can be used to join light gauge metals. Metal piercing rivets can fasten metals like steel and aluminum with hardness up to about RB50. Compression rivets are made in two parts as shown. The diameters are selected to provide an appropriate interference fit at each interference. Compression rivets can be used for wood, brittle plastics, or other materials with the little danger of splitting during setting. One common application is in the cutlery field. The flush surfaces and interference of fits of riveted knife handles are free of the crevices in which food and dirt particles can accumulate. Figure 11.3 shows the situation where blind rivet requiring access to only one side of the joint is appropriate. Figure 11.4 illustrates varieties of blind rivets. More detailed information on rivets is available in references such as 457. Chapter 11.3 Welding Processes. Modern developments in welding techniques and equipment have provided the engineer with a range of attractive alternatives for fastening. As an alternative to bolts or rivets, and for fabricating parts, machine members can often be fabricated at a lower cost by welding than by casting or foregoing. Typical examples are shown in Figure 11.5. Most industrial welding is done by fusion, with workpieces melting at their common surfaces. Heat is applied by an electrical arc passing through the electrode and the rivet. That's a rivet. That's a joint. That's a rivet. That's a joint. Okay. Work by high amperage electric current passing through the mating workpieces or by gas flame. Electric arc welding takes several forms depending on how filler material is applied and the way molten weld metal is shielded from the atmosphere. Shielded metal arc welding, also called stick welding, is common manual process for repair work in the welding of large structures. The welder feels a consumable coated electrode in the work area. A flux coating on the electrode releases a high shielding gas and also forms slag around the weld metal. SMAW is usually used with steels. Cool. That is cool. Gas metal arc welding, GMAW. What's up, GMAW? Okay, also called metal insert gas welding, is a commonly automated process producing high quality welds at high welding speeds. With most metals, the consumable electrode is not coated, but it projects from the nozzle that supplies a shielding gas, argon for aluminum and other non-ferrous metals. Low-cost carbon dioxide for steels. Gas tungsten arc welding, GTAW, also called tungsten inert gas welding, employs a non-consumable tungsten electrode with a filler wire sometimes fed in separately. A nozzle surrounding the tungsten electrode supplies helium or argon gas for shielding. This process is slower than GMAW, but can be used with thinner metals, either ferrous or non-ferrous. The process gives high-quality welds of non-ferrous and similar metals and can be fully automated. Flux cord arc welding, FCAW, is much like SMAW, except that the flux is in a hollow core of consumable electrode rather than on its outer surface. A shielding gas is sometimes supplied from a nozzle surrounding the electrode. The process produces fast, clean welds on various metals. Submerged arc welding is done on flat workpieces. A mount or line of granular flux is deposited on the workpieces in advance of the moving consumable electrode. The flux melts to produce a protective molten slag under which the fresh weld is submerged. The process is commonly used with thick sections requiring deep weld penetration. In resistance welding, electric current generating heat at the rate of I²R passes through the workpieces while they are clamped firmly together. No flux or shielding is used, but process may be carried out in a vacuum or inert gas. Filler material is not normally used. Resistance welding is especially suited for mass production. of continuous welds or spot welds of most steels and aluminum alloys. Material thickness range from about 0.004 to 0.75 inch. Gas welding, usually performed manually with an oxyacetylene torch, is relatively slow, requires more generalized heating of the work, and is most often used for making repairs. A filler wire is usually but not necessarily used. Laser beam welding, plasma arc welding, electric beam welding, and electroslag welding are also fusion welding processes are used on a small scale for very special applications. Non-fusion or solid-state welding processes use a combination of heat and pressure to join is usually less than melting point of the materials. One example is inertial welding. Kinetic energy stored in a flywheel is converted to friction heat when a workpiece connected to the flywheel is forced against the stationary piece. In a second ultrasonic welding, workpieces are clamped down between a fixed anvil and vibrating horn bond as they are rubbed together at ultrasonic frequency. Note the parallel between these processes and seizure, discussed in adhesive wear in section 9.9. The suitability of several common metal and alloys to the arc and gas welding is summarized in table 11.1. Thermoplastics can be welded. I am learning, but this is a lot. Oh my god. Okay. Thermoplastics can be welded much like metals. How long has it been? Oh my god. Okay. 9 hours. Heat can be applied by hot gas, usually inert contact with hot metals plates, or electrically by dielectrical heating and induction heating. In dielectric heating, thin films most used for packaging, breaking down under high voltage and high frequency to produce heat needed for fusion. In induction heating, electromagnetic induction currents are generated in metal inserts or embedded metal powders. Listen, class. Inertial welding and ultrasonic welding techniques are applicable to the thermoplastics. Rubbing the mating pieces together at sonic frequencies is also effective, with bonding usually accomplished after 2 or 3 seconds. This is called vibration welding. Solvent bonding in thermoplastic parts is accomplished when the members are softened by coating with a solvent and then clamping down together for 10 to 30 seconds, during which the time of plastic molecules intermingle. The parts bond together with when the solvent evaporates. Chapter 11.4. Welding joints subjected to static, axial, and direct shear loading. Weldments such as those shown in figure 11.5 are usually fabricated from carbon steel pieces held in position by suitable clamps or fixtures while the welding is performed. The strength of the welded joints is dependent on many factors that must be properly controlled in order to obtain welds of high quality. The heat of welding may cause metallurgical changes to the parent metal in the vicinity of the weld. Residual stresses may be introduced through thermal gradients, which cause different expansion and contraction. The influence of clamping forces and the change of yield strength with temperature. Residual stress and warping problems are most pronounced when the welding pieces of varying thickness and irregular shape. Measures that can be taken to control these problems include heating the parts to uniform temperature before welding, following detailed good welding practice for the application involved, given the weldment of low temperature, stress relieving anneal after welding, and shot peening the weld area after cooling. For welded construction and used in bridges, buildings, and pressure vessels, the law requires that appropriate codes be adhered to. When there are uncertainties about the welding process to be used in critical applications, laboratory testing of prototype welded joints is often advisable. The basic concept of fusion welding is to fuse the metals together into a single, hopefully homogeneous member. Properties of the welding rod must, of course, be properly matched to those of the parent material. Ideally, the stress and strength analysis would then proceed as though the part were made from a single piece of stock. Welding electrode material strength and ductility specifications have been standardized by the American Welding Society and the American Society for Testing Materials. For example, welding electrodes in the E60 and E70 series are designated E60XX and E70XX, and the 60 and 70 indicate tensile strength of at least 60 or 70 ksi, respectively. The last two digits are about 12 ksi below the tensile strength, and minimal elongation is between 17 and 25%. These properties all apply to as-welded material. Figure 11.6 shows 4 variabilities of full penetration butt wheels. If these are... Oh my god, why did I'm so immature. Okay, let's go. I got this. If these are of good quality, the weld is as strong as the plate and its efficiency. Fillet welds illustrated in 11.7 are commonly classified according to the direction of the loading: parallel load and transverse load. For parallel loading, both plates exert a shear load on the weld. With transverse loading, one plate exerts a shear load on the and the other a tensile load on the weld. The size of the weld defined by the leg length h. Usually, but not necessarily, the two legs are of the same length. Conventional engineering practice considers the significant weld strength to be shear stress in the throat section for either parallel or transverse loads. Throat length T is defined as the shortest distance from the intersection of plates. 1. The straight line connecting the ends of the two legs to the weld bead surface, whichever is less. For the usual case of convex weld with equal legs, T equals 0.707 h. The throat area used for the stress calculations is one product TL, where L is the length of the weld. Figure 11.7b shows that for welds and convex weld beads, achieving significant penetration into the parent materials, the actual minimum weld section area can be significantly greater than TL, although welding codes and conservative standard practice do not give the weld credit for this extra throat area. There is no reason to consider it in design of members not covered by codes, provided the extra calculated load capacity can be verified by test and the production welding process is sufficiently well controlled to ensure that all welds actually achieve the increased section area. Weld size H could be reasonably proportioned in comparison to the thickness of plates being welded. For practical reasons, H is a minimum of 3 mm for plates less than 6 mm thick on up to a minimum of 15 mm for plates over the 150 mm thick. Chapter 11.5. 9 hour mark, guys. 9 hour mark. This is insane. Okay. Chapter 11.5. Welded joints subjected to stack torsional and bending loading. Figures 11.8 and 11.9 illustrate two examples of what is often referred to as eccentric loading. In figure 11.8, the load is in plane of the weld group, thereby subjecting the welded connection to torsion, as well as direct loading. In figure 11.9, the load is out of the plane of the weld group, thus producing bending in addition to load direct loading. Note that the additional to the torsion or bending, there is direct loading component of the welds corresponding to the load situations considerable to the previous section. Weld segments BC in figure 11.8 and BC and AD are subjected to parallel loading. All other weld segments in the two figures are loaded transversely. A rigorous analysis of the stresses on various portions of each weld segment in figures 11.8 and 11.9 would be very complicated, involving a detailed study of both rigidity of the parts being joined and the geometry of the weld. The various incremental segments of the weld serve as a multiplicity of redundant attachments, each carrying a portion of the load dependent on its stiffness. The following procedures are based on simplifying assumptions commonly used to obtain results sufficiently accurate for engineering in most applications. Stresses on the weld in figures 11.8 and 11.9 consist of vector sum of the following: direct shear stresses calculated on the previous section. These stresses are ordinarily assumed to be uniformly distributed over the length of all welds. Superimposed torsional stresses, bending stresses, or both calculated from conventional formulas TTR divided by J and sigma MC divided by I. The parts being joined are assumed to be completely rigid. Chapter 11.6 Fatigue Considerations in Welded Joints. When welded joints are subjected to fatigue loading, small voids and inclusions, which have little effect of static strength, constitute points of local stress concentration and reduce fatigue strength. In addition to the weld material extended beyond the plane of plate surfaces in butt welds, which is called reinforcement, causes obvious stress concentration at the edges of the weld bead. For static loading, the material may indeed provide slight reinforcement to compensate for possible voids or inclusions in the weld metal, but for fatigue loading, strength is increased by grinding the weld bead flush with the plates. Approximate fatigue stress concentration factors associated with the butt weld reinforcement and other weld geometries are given in table 11.2. Chapter 11.7 Brazing and Soldering. Brazing and soldering differ fundamentally from welding, and the temperatures are always below the melting point of the workpieces. The solder or brazing filler material acts somewhat like molten metal glue or cement that sets immediately on cooling. Thus, brazing and soldering can be classed as bonding processes. The processes of brazing begins with heating the workpieces to a specified temperature above 840 degrees Fahrenheit. On contact with the workpieces, the filler material melts and then flows into the space between the pieces. For capillary action, to draw the molten filler metal most effectively, clearances of 0.025 to 0.050 mm are normally recommended, but special wide gap filler alloys permit clearances 10 times this great. It is important that the surfaces can be initially clean. Either flux or an inert atmosphere is required. Brazing is usually accomplished by heating the parts with a torch or in a furnace. Filler metals are usually alloys of copper, silver, or nickel. Special care must be used when brazing aluminum parts because of the melting point of filler material is not much lower than the aluminum parts. Brazing has several advantages. Dissimilar metals, cast and wrought metals, and even non-metals, and metals can be brazed together. Complex assemblies can be brazed in several steps by using filler metals with progressively lower melting temperatures. Brazed joints require little or no finishing. Soldering is similar to the brazing, except that filler metal has a melting temperature below 840 and has relatively low strength. Most solders are tin lead alloys, but alloys include antimony, zinc, and aluminum are also used. Nearly half of the soldering applications involve the electrical and electronic parts. Another common application is sealing the seams in radiators in tin cans. Adhesives. Adhesive bonding of metal parts is rapidly growing field, one which influences the design of products of nearly all kinds. The website 3m.com/bonding represents a general and technical information and data on adhesive tapes and reclosable fasteners. The advantages of adhesive are many. No holes which weaken the part are required. As with screws and rivets, no temperatures high enough to produce warping and residual stresses are involved as with welding. When the joint is loaded, stresses are spread over the large area with only minor stresses concentration at edges of contact. This often permits the use of thinner members, resulting in a weight-saving. Adhesive bonding permits smooth, unbroken exterior surface for a good appearance, easier finishing, and reduce fluid friction in applications involving a flowing liquid or gas. As an airplane wing or a helicopter rotor blade, almost any solid materials can be bonded with a suitable adhesive. When bonding dissimilar metals, the adhesive layer can provide effective insulation against galvanic currents. On the other hand, the adhesive can be made electronically conducting if desired. Flexibility of adhesive material can be made to accommodate differential thermal expansion of bonded members. This flexibility also aids in absorbing impact loads. Furthermore, adhesive bonds can provide dampening to reduce vibration and sound transmission. Adhesive bonded joints can effectively seal against leakage of any liquid or gas that does not attack the adhesive. On the negative side, adhesives are more temperature sensitive than mechanical fasteners. Most adhesives currently in common are limited to the -200 to 550 Fahrenheit, -129 degrees to 260 degrees Celsius, most range. Adhesives vary greatly in temperature response and this must always be considered when selecting an adhesive for a specific application. Inspection, disassembly, and repair of adhesive joints may not be practical, and long-term durability of some adhesives is questionable. Oh my god. Perhaps a major factor motivating the proliferation of adhesives is cost reduction. It's only been 5 minutes? Oh my god. However, the cost to be considered is total cost of the assembled joint, and this can be either greater or less than the cost of using mechanical fasteners, depending on the multitude of factors. As previously noted, the adhesive bonding may permit thinner and lighter mating surfaces. What if I'm in the room, bro? Okay. Machining costs may be reduced by eliminating drilled holes and permitting wider tolerances. For example, the gap filling capability of some adhesives can eliminate the need for low tolerance and press fits. The cost of an adhesive itself can be either more or less than half of the competitive mechanical fastener. A major cost of the factor with bonded joints is often surface preparation. Extreme cleanliness is often required, although recent advances in adhesive research has made possible a relaxation of cleanliness standards in some applications. Automation for high production may be more costly with adhesives, particularly if elaborate fixtures and extended curing times are needed. Bonding adhesives function as one component of the composite bonding system, with interactions between the adhesive and bonded materials influencing the properties of both. This fact, plus the tremendous variety of adhesives on the market often makes the selection of the best adhesive for a particular application difficult. Current specialized technical literature information from adhesive suppliers and test results must be relied on. Oh my god. Safety and environmental factors are important considerations in the adhesives industry. Federal regulations control the use of certain solvent-based adhesives that gives off flammable or toxic gases. Some adhesives are not used for certain applications because they emit an objectionable odor until cured. Petroleum is the raw material for many adhesives, and research efforts are directed towards finding more alternatives. Several types of adhesives require heat curing at 95 degrees to 260 degrees Celsius, sometimes for several hours. Increasing energy costs add urgency to the need for developing equivalent adhesives that require less curing time and lower cure temperatures. When possible, mating temperatures should be designed so that adhesive joints are loaded in shear, as all adhesive bonds perform the best when loaded this way. Figure 11.12 illustrates a representative appropriate designs. Adhesive joints can also be loaded in tension, but peel and cleavage I don't know. I can't pronounce it. Okay. Loadings should be avoided. Most structural or engineering adhesives are thermosetting as opposed to thermoplastic types such as rubber cement, airplane glue, and hot metals. The latter are generally intended for light-duty applications requiring lower strength. The sheer strength of some Family Guy seems today that all you see is violence in movies. No. Some heat curing 1-part epoxies is as high as 70 MPa, but most structural adhesives have shear strengths in the 25 to 40 MPa range. Epoxies used in industrially since 1940s are the most versatile and widely used of the structural adhesives. The 2-part type cure room temperature but require pre-mixing. 1-part epoxies need no mixing but require heat curing, usually around 150 degrees Celsius for an hour. Epoxies can be formulated to sufficient viscosity to satisfy most gap filing requirements. Overall cost of high strength epoxy bonds can be relatively high. Urethanes are similar to epoxies in that they have great versatility, have relatively high strength, and are available in both a 2-part room temperature curve formation and a 1-part heat curve formation. They have good toughness, flexibility, and impact resistance. Anaerobics are 1-part adhesives that are easily to apply and occur in the absence of oxygen. If I read of airing, like I don't know, why am I doing? Okay. Okay. They are commonly used for thread locking and machine assembly, such as retaining bearings and keys in place on shafts. Rapid curing usually restricts the use of anaerobic adhesives to the assembly of relatively large parts. Some newer acrylic adhesives are tolerant of dirty surfaces. This can be important in high production assembly under ordinary industrial conditions. Cyanoacrylates are particularly appropriate when extreme fast set time is important. They are perhaps the easiest to apply and the fastest to cure all industrial adhesives. In order to facilitate production and reduce costs, most one-part engineering adhesives are available as films with removable backing. These are supplied in various thicknesses and even special shapes. Some adhesives are available in the form of a powder that is held in place electrostatically prior to the assembly and heat curing. Adhesives are sometimes used in conjunction with mechanical fasteners. The fast-moving field of modern industrial adhesives offers liberal opportunity for engineering ingenuity. Chapter 12.1 Introduction. Springs are elastic members that exert forces or torques and absorb energy. Which is usually stored and later released. Springs usually, but not necessarily, made of metal plastics. Hello? Chapter 12.1 Introduction. Spring are elastic members that exert forces or torques and absorb energy, which is usually stored and later released. Springs are usually but not necessarily made of metal. Plastics can be used when loads are light. Modern structural composites are being introduced for some applications requiring minimum spring mass. Blocks of rubber often constitute springs, as in bumpers and vibration isolation mountings of various machines, such as electric motors and internal combustion engines. Pneumatic springs of various types take advantage of the elastic compression of gases as compressed air in automotive air shocks, as hermetically sealed high-pressure nitrogen gas in the pneumatic suspensions of French Citroën automobiles. For applications requiring compact springs providing very large forces with small deflections, hydraulic springs have proved effective. These work on a basis of slightly compressibility of liquids, as indicated by their bulk modulus of elasticity. Product cost can sometimes be reduced by designing the required elasticity into other parts, rather than making those parts rigid and adding on a separate spring. Our concern in this book is with springs made of solid metals or reinforced plastic composites. If energy absorption with maximum efficiency is the objective, the ideal solution is unnotched tensile bar, for all the material is stressed at the same level. Unfortunately, tensile bars of any reasonable length are too stiff for most spring applications. Hence, it is necessary to form the spring material so that it can be loaded in torsion or bending. The following sections are concerned with the springs of common geometric forms that serve this purpose. Chapter 12.2 Torsion bar springs. Perhaps the simplest of all the spring forms in the torsion bar, illustrated in figure 12.1. Common applications include some automotive suspension springs and counterbalancing springs for the car, hoods and trunk lids, where small torsion bars fit inconspicuously near hinges. The basic stress, angular deflection, and spring rate equations are as follows. Chapter 12.3 Coil Spring Stress and Deflection Equations. Figure 12.2a and c shows helical coil compression and tension springs, respectively, of relatively small helix angle. Okay, I'm just going to Google Greek letters for math. There we go. Lambda. Angle lambda. Corresponding figure B and D shows up. How did I not know lambda? Shows up top portions of these springs as free bodies in equilibrium. For each external force, F is at least applied along the axis of the helix. In the compression string, this is commonly achieved by winding the end coils of zero pitch and then grinding the ends flat, so that the pressure applied to the end plates is essentially uniformly distributed. In the tension spring, the end hooks are formed to position the load force along the spring axis. In figure 12.2b and d, note that regardless of where the cutting plane is taken, equilibrium considerations require that the wire be subjected to a transverse shear force of F, a torque equal to Fd divided by 2. The shear force turns out to be of minor consequence. The important thing is that the entire length of active wire in the helix is subjected to torque. For springs made out of solid round wire, the resulting torsional stress is this equation, where D is the mean coil diameter, defined as the average of the inside and outside coil diameters. Thus, a helical compression or tension spring can be thought of as a torsion bar wound into a helix. The addition of basic shear stress represented by equation 12.1. The inner surfaces of a coil spring are subjected to two additional shear stress components. A transverse shear stress resulting from force F is applied to an arbitrary cutting plane in figure 12.2b and d. The inner coil surface, the direction of the stress coincides with that of torsional stress for both compressive and tensile spring loading. There is an increased intensity for torsional stress because of the curvature of the coiled torsion bar. The second effect is illustrated in figure 12.3. Suppose the torque transmitted through the curved torsion bar produces a 1 degree rotation between planes M and N. This 1 degree is distributed over a short length AB at the inside of the coil, and longer length CD at the outside. This gives rise to the stress gradient shown. The severity of this effect is obviously greatest for small values of spring index C, defined as the ratio of mean coil diameter to wire diameter. The first generally recognized analysis of the transverse shear and curvature effects was published by A.M. Weil of the Westinghouse Corp in the Transactions of the American Society of Mechanical Engineers. This analysis involved the derivation of the equation of factor Kw, by which the stress in equation 12I can be multiplied to give the total resultant shear stress on the inside of the coil, given with this equation right here. Equations are cool, but they don't really matter right now. When the loading on the spring is essentially static, the view is usually taken that the first term of EQ 12.3, which accounts for the curvature effect, should not be used when it's essentially a stress concentration factor. Setting this term equal to the union gives a correction factor of the transverse shear only of Ks equals 1 plus 0.615 divided by C, where the subscript designates static loading. Equation A is readily derived as followed. An exact analysis shows the transverse shear stress acting on the element inside the coil diameter to be 1.23 F divided by A. Adding this to the nominal torsion stress gives this equation, which reduces to 8FD divided by pi d cubed times k to the s, where Ks is defined by EQ A. After some yielding occurs with static loading, the stresses are more uniformly distributed and the factor of 1.23 is often omitted. This gives Ks equals 1 plus 0.5 divided by C. And actually, in applications with static loading and elevated temperatures, it is sometimes assumed that stresses become sufficiently redistributed that can be used without correction. And the preceding variety of stress corrections for static loading can lead to confusion. An important point to remember is that when using allowable stress data obtained from static load tests of coil springs made of specific materials, the same correction factor must be used as the reflected in the test data. In accordance with many authorities, it is recommended here that EQS 12.3 and 12.4 be used for fatigue and static loading respectively. These equations apply to springs of normal geometry. C is greater than 3, and then lambda is less than 12 degrees. It follows for fatigue loading. The equation for corrected stress is this equation. The corresponding corrected stress equation for the static loading is this equation, where Ks is defined in 12.4. Values Kw, Ks, and Kwc and Ksc are plotted in figure 12.4. The three body diagrams in figure 12.2 indicate no bending loading. For unusual cases with the pitch angle lambda greater than 15 degrees and the deflection of each coil greater than d divided by 4, bending stresses should be considered. In addition, it should be noted that the preceding treatment of helical string stresses tactically assumed two factors to be negligible. Load eccentricity. It is seldom possible to distribute the load on a spring end so that the resultant coincides exactly with the geometric spring axis, and essentially introduce the bending and changes the torsional moment arm. This causes the stresses on one side of the spring to be higher than that indicated by the foregoing equations. Axial loading. Reference to figure 12.2b indicates that the addition of creating a transverse shear stress, a small component of force F, produces axial compression of the spring wire. In critical spring designs involve relatively large values of lambda, this factor may warrant consideration. Derivation of the equation for a helical spring deflection is most readily accomplished using the Castigliano's method. The spring rate is commonly designated as K, where figure 12.5 shows a compression helical spring of unequal pitch. As this spring is loaded, active coils near the ends bottom out first, thereby becoming inactive. As successive turns bottom out, the spring becomes increasingly stiff. The number of active turns and progressively decreases, thereby giving increased values of K in equation 12.8. This is desirable in many applications, but in some applications, most but not all coil springs are helical. A few are conical, as shown in figure 12.6 with a steep enough cone angle. The coils can nest together, giving a solid height equal to the wire diameter. Since the torque Fd divided by 2 is applied to the smaller turns, it is less than for the turns for the large diameter. The torsional stresses throughout the length of the wire can vary accordingly. This means the wire is used less efficiently than a helical spring. Appropriately varying about the pitch throughout the length of the spring makes it possible to have all turns bottom out simultaneously if this is desired. The deflection and the spring rate of the conical spring can closely be approximated by using EQ 12.7 and 12.8, where the average value of the mean coil diameter is used for D. Cool. Stress and strength analysis for helical compression springs, static loading. Most helical springs are wound from a wire of solid round cross section. Not only will these be treated in this book, although spring wire was formerly manufactured primary in certain standard gauge diameters, it is now readily available in any desired size. The relative cost and minimum tensile strengths of commonly used spring wire materials are given in 12.1 and 12.7 respectively. This information is fine as far as it goes, but the spring design allowable values of shear stress are needed to use within 12.5. Working with the information at hand, we proceed as follows. The basic concern in designing springs for static loading is avoiding the set or long-term shortening of the spring load. Long-term shortening of the spring under load. Set is directly related to SSY and indirectly SN to SN. Experimental values of SSY are seldom available. Equation 3.12 gives for an average spring wire of SU equals 220 KSI, and estimate of SY equals 1.05 SU minus 30 KSI equals 1.05. 220 minus 30 equals 201 KSI. Most severe stress to which comparison helical spring can be subjected to correspondence to loading it is to its solid height. Although this condition should never be experienced in service, it can be either intentionally or accidentally encountered when the spring is installed or removed. Typically then, what letter is that? Tau should be less than SY, or from the preceding less than about 0.53 S mu. No, U. Experience indicates that less than 2% long-term set will occur in springs designed for T of tau of S, where S is solid, equal to 0.45 SU for ferrous spring or 0.35 SU for non-ferrous and austenitic stainless steel springs. Recommended stress values in step 3 thus appear to imply a safety factor for steel springs. About 0.53 SU and 0.545 SU is 1.18. This may seem small, but it actually illustrates the safety factor philosophy outlined in section 6.11. For example, it was stated that in that section that safety factor selection is based on 5 factors, 3 of which are degree of loading under uncertainty, degree of material strength uncertainty, and consequences of failure. For a helical compression spring, there are virtually no loading uncertainty. It is impossible for the spring to be loaded beyond the point of closing solid. The manufacturing operations associated with the high-quality spring production can be controlled to give a high degree of uniformity of spring shield strength. Finally, the consequences of failure are usually not serious. Since stresses are limited by the spring solid condition, it follows that the spring can be stressed mostly highly or at their working loads. If the maximum working loads come close to closing the spring solid, it is only necessary to provide the sufficient clash allowance to allow for any possible combination of tolerance, stack-up, differential, thermal expansion, and wear of parts. Moreover, since all portions of the springs do not become solid at precisely the same load, the spring rate begins to build up sharply just before reaching theoretical spring solid position. The usual recommendation is not to provide a clash allowance, which is approximately 10% of the total spring deflection and at maximum working load. Finally, coil springs in compression are ideal candidates to benefit from the favorable residual stresses caused by yielding. In section 4.15 stated that an overload causing yielding products residual stresses are favorable to future loads in the same direction and unfavorable to future loads in the opposite direction. Compression coil springs are loaded and only in compression, hence advantage can be taken of favorable residual stresses by initially cooling the spring longer than desired and then yielding it to the desired length by closing it solid. This operation, called presetting, is widely used. According to taking maximum advantage of presetting permits the design stress to be increased from 0.45 SU and 0.35 SU values given in step 3 to 0.65 SU and 0.55 SU. This increase is actually somewhat more than can be justified theoretically on the basis of residual stresses alone and may reflect some work hardening during presetting. Summarizing this discussion, to limit long-term set in compression coil springs to less than 2%, shear stresses calculated from equation 12.6 should be this equation on the page right here for a lot of different numbers. Okay, and designs of helical compression springs. The 4 standard end designs used with compression helical spring are illustrated in the figure 12.8, together with the customarily used equations for the solid height Ls in all cases. NT, total number of turns, and N equals number of active turns. The turns that twist under load and thereby contribute to deflection as calculated from EQ 12.7. In all ordinary cases involving end plates contacting the springs on their end surfaces. Equation 12.10 follows from the need for both end plates to be in contact with nearly a full turn of wire in order to satisfy the requirement that the resultant load coincide with the spring axis. The provision of essentially uniform contact pressure over the full end turns requires contoured end plates. For all end conditions except squared and ground, the choice between 1 contoured end plate and 2 squared and ground springs is usually made on the basis of cost. Some alternative end member designs are illustrated in figure 12.9. Note that all these except figure 12.9 represent special designs that provide for adjusting the number of active turns in the permit loading the spring in tension as well as the compression. The solid height equations given in figure 12.8 are those normally used, but in figures 12.8b and d, the actual solid height depends on the grinding operation. For springs with ground ends, the equations give a maximum solid height associated with normal grinding practice. For special applications in which the space is limited, ground springs can be obtained with a solid height of Ls equals Nt minus 0.5 parentheses 1.01 times d. Chapter 12.6 Buckling Analysis of Helical Compression Springs. Coil springs loaded on the compression act like columns and must be considered for possible buckling, particularly for those large ratios of free length to mean diameter. The column treatment in Chapter 5 applies. Figure 12.10 gives the results of two of the end conditions illustrated. In figure 5.27, curve A represents the most common condition. If buckling is indicated, the preferred solution is redesigning the spring. Otherwise, the spring can be supported and hence prevented from buckling by placing it either inside or outside of a cylinder that provides a small clearance. Friction and wear on the spring from rubbing on the cylindrical guide may have to be considered. Chapter 12.7 Design Procedure for Helical Compression Springs. Static loading. The two most basic requirements of a coil spring design are an acceptable stress level and the desired spring rate. To minimize weight, size, and cost, we usually design springs to the highest stress level that will not result in significant long-term set. Stress is usually considered before spring rate and in designing a spring because the stress involves D, capital D, and D, but not capital N. In general, the stress requirement can be satisfied by many combinations of D and D. The objective is to find one of these selected that best suits the requirement of the particular problem. With D and D at least tentatively selected, N is then determined by the basis of a required spring rate. Finally, the free length of the spring is determined by what length will give the desired clash allowance. If the resulting design is prone to buckling, or if the spring does not fit into the available space, or another combination of D and D may be indicated. If the spring comes out too large or too heavy, a stronger material must be considered. Solution. Chapter 12.8 Design of Helical Compression Springs for Fatigue Loading. This section discusses the design of helical compression springs for the fatigue loading. Figure 12.12 shows a generalized SN curve, calculated in accordance with Chapter 8 for reverse torsional loading of a round steel wire of ultimate tensile strength SU, any diameter not exceeding 10 mm. In a surface factor of unity, a corresponding constant life fatigue diagram is plotted in figure 12.13. Since compression coil springs are always loaded in fluctuating compression, these springs do not normally experience a stress reversal. In the extreme case, the load drops to zero and then reapplied in the same direction. Thus, as shown in figure 12.13, the region of interest lies between tau A divided by tau M equals 0, and tau A divided by tau M where equals to 1, where tau A divided by tau M is the ratio of alternating shear stress to mean shear stress. It is customary when working with coil springs to replot the information in figure 12.13 in the form used in figure 12.14. This alternative form of constant life fatigue diagram contains the only region of interest shown in figure 12.13. Note, for example, that point P of figure 12.13 corresponds to tau M equals to 0.2155 U, tau A equals to 0.215 SU, whereas in figure 12.14 points P as tau min and equals to 0 and tau max equals to 0.043 SU. Cool. Diagrams like figure 12.14 are usually based on the actual torsional fatigue test, with specimens loaded in the 0 to maximum fluctuation. Figure 12.15 shows SN curve based on 0 to maximum stress fluctuation. The top of the curve is drawn to agree with the values determined in figure 12.13. Note that the curve shows higher values of maximum stress than does the figure of 12.12 because the fluctuating stress drops only to 0 rather than completely reversing. The lower curves in figure 12.15 are 0 to maximum torsional S to N curves based on the experimental data and suggested for design by major spring manufacturers. These reflect production spring wire surface finish rather than CS equals to 1 as in the top curve. The spring manufacturers customarily present design stress data of this kind in terms of tensile ultimate strength, because the ultimate tensile strength was the easiest to obtain and the most reliable experimental measure of wire strength. Figure 12.16 is an independently obtained empirical constant life fatigue diagram pertaining to most grades of an engine valve spring wire. It represents actual test data. Design value should be somewhat lower. In the design of a helical spring or torsion bar, springs for fatigue loading, two previously mentioned manufacturing options are particularly effective: shot peening, see sections 8.13 and 8.14, and presetting, see points 6 and 7 in section 12.4. Recall that the presetting always introduces surface residual stresses opposite those caused by subsequent load applications in the same direction as the presetting load. The corresponding coil spring or torsion bar and torsional stress fluctuations with and without presetting are shown in figure 12.17. It can be shown that the theoretical maximum residual stress that can be introduced by presetting, assuming the idealized stress strain curve that neglects the possibility of some strain hardening, that is SSY divided by 3. The practical maximum value is somewhat less. The fatigue improvement represented by the fluctuation with presetting figure 17 is readily apparent when the stress fluctuations are represented in figures 12.13, 12.14, and 12.16. Maximum fatigue strengthening can be obtained by using both shot and peening and presetting. Springs used in high-speed machinery must have natural frequencies or of vibrations well in excess of the frequency of motion they control. For example, a conventional engine valve spring goes through one cycle of shortening and elongating every 2 engine revolutions. The valve motion is far from sinusoidal, and Fourier analysis of the motion typically indicates the harmonics up to about the 13th are significant magnitude. Thus, at 5,000 engine RPM, the fundamental spring motion has a frequency of 2,500 cycles per minute, and the 13th harmonic 32,500 CPM or 542 Hz. When the helical spring is compressed and then suddenly released, it vibrates longitudinally at its own natural frequency until the energy is dissipated by dampening. Similarly, if helical spring is fixed at one end and given sufficiently rapid compression at the other, the end coil is pushed against the adjacent coil before the remaining coils have no time to share in the displacement. If after sufficiently rapid compression, the free end is then held fixed, and the local condition of the excessive displacement will move progressively along the spring until it reaches the opposite end, where the disturbance is reflected back towards the displaced end, and so on, until the energy is dissipated. This phenomenon is called the spring surge and causes local stresses approximating those for spring solid. Spring surge also decreases the ability of the spring to control the motion of the machine part involved, such as the engine valve. The natural frequency of spring surge
which should be made higher than the highest significant harmonic of the motion involved. Typically, about the 13th is Fn equals to square root k divided m, where k sigmoid d to the 4g divided by d to the cubed times n. For steel springs, the natural frequency in hertz is Fn equals to 13,900 divided by nd squared. Designing springs with sufficiently high natural frequencies for high-speed machinery typically requires operating the highest possible stress level by taking advantage of presetting and shot peening. This minimizes the required mass of the spring, thereby maximizing its natural frequency, which is proportional to 1 divided by square root m. Helical extension springs. Most of the foregoing treatment of helical compression springs apply equally to extension springs, but a few points of difference should be noted. First, extension springs do not have the automatic overload stop feature of compression springs. A sufficient static overload can elongate any extension spring to failure. This sometimes makes them vulnerable to excessive overload stresses during installation. Furthermore, a broken compression spring may continue to provide a stop that holds the end plates apart. For these reasons, compression springs are generally preferred to extension springs in safety-critical applications. Accordingly, some safety codes require that all helical springs used for certain applications be loaded in compression. Extension springs are usually wound while maintaining a torsional stress in the wire. This results in the coils pressing against each other, as shown in figure 12.20. The initial tension is the external force applied to the spring when the coils are just at the verge of separating. Spring manufacturers recommend that the initial tension be such that the resulting stress computed is this equation over here to see the resulting stress. Okay, an extension spring wound in this manner does not deflect until loaded with a force exceeding the initial tension. Then the equations for stress and spring rate developed for compression springs apply. The critical stresses in an extension spring often occur in the end hooks. Figure 12.20 shows the location and equation for the critical hook bending and torsional stresses. Note that in each case, the stress concentration factor is equal to the ratio of mean to inside radius. Recommended practice is to make radius R4 greater than twice the wire diameter. Hook stresses can be further reduced by winding the last few coils with decreasing diameter d, as shown in figure 12.21. This does nothing to reduce the stress and concentration, but it does lower the nominal stresses by reducing the bending and torsional moment arms. Depending on details of the design, each end of the hook typically adds the equivalent of 0.1 to 0.5 helical turn when computing spring deflection. Chapter 12.10 Spring Beam Springs. Beam springs are usually arranged in cantilevers and simply supported beams in the form of quarter, half, or full ellipse, as shown in figure 12.22. These springs are also called flat springs, although they usually have some curvature when unloaded. Note that in each case, the basic element is the cantilever of length L loaded by force F. The common semi-elliptic spring can be thought of as two cantilevers sharing the load in parallel. The full elliptic spring has 4 cantilevers arranged in a series parallel arrangement. It is only necessary to analyze the stress and deflection characteristics of the simple cantilever or quarter elliptic spring for the same equations that can be readily be adapted to cover the other two types. Hey, how many of you guys in the chat know how to say cantilever? Cantilever? It sounds weird, right? Okay, leave a comment below in the chat. Leave a comment in the comments below if you can pronounce it right away. Okay, figure 12.23a shows a general cantilever beam with width W and thickness T, both of which vary in length X. If the bending stresses are to be uniform over the length of a cantilever of constant thickness, The width must vary linearly with x. For a uniform stress cantilever of constant width, the thickness must vary parabolically with x. The triangular beam of figure 12.23b is the basic model for design of leaf springs. The parabolic beam of figure 12.23 C is the basic model for analyzing the bending strength of spur gear teeth. Of course, constant strength cantilevers can be made by varying both W and T so that the stress 6Fx divided by Wt squared is constant for all values of x, and this is the concept behind the design of the single leaf suspension springs that have been used in automobiles. For any constant strength cantilever beam, the bending stresses throughout are equal to those of the fixed end. Sigma equals 6FL divided by BH squared. Figure 12.24 shows the idea behind cutting up the constant strength triangular beam of figure 12.23b into a series of leaves of equal width and rearranging them in the form of a leaf spring. The triangular plate and the equivalent multi-leaf spring have identical stress and deflection characteristics with two exceptions. Interleaf friction provides damping of multi-leaf spring, and the multi-leaf spring can carry a full load in only one direction. Because of the varying cross-section, the derivation of the deflection equation for idealized triangular leaf spring provides an excellent application of Castigliano's method. It is suggested that the reader use this method to verify that... What letter is that? Delta. Delta equals FL cubed. Oh, delta has two ways to write it. Okay, I did not know that. Divided by 2EI, where I equals BH cubed divided by 12, and E equals Young's modulus, or delta equals 6FL cubed divided by EBH3. The corresponding spring rate is this. Okay. That's pretty cool. Torsion springs, chapter 12.11. Torsion springs are of two general types: helical, shown in figure 12.28, and spiral, shown in figure 12.29. The primary stress in all torsion springs is bending, with a bending moment of Fa being applied to each end of the wire. The analysis of the stresses in curved beams developed in section 4.6 is applicable. The highest stress inside of the wire is equal to sigma I equals Ki MC divided by I, where Ki is given the figure 4.11 for some cross sections and given the figure 12.30 for the round and rectangular sections usually used in springs. Substituting the product Fa for bending moment and also substituting the equations for section properties of round and rectangular wire gives these equations. For fatigue applications, special care must be taken in the design of the end portion of the wire and its engagement with the loading member, as points of stress concentration at the ends are frequent sites of fatigue failure. Residual stresses are an important consideration in torsion springs. Recall the statement in section 4.15. An overload causing yielding produce residual stresses that are favorable to finding future loads in the same direction and unfavorable to future loads in the opposite direction. The coiling of helical and spiral springs involved obvious yielding, and the resulting residual stresses are favorable to subsequent loads tending to coil the spring tighter. It is extremely important to bear this in mind when designing applications for torsion springs because of the favorable residual stresses. Design stresses for a static surface can be 100% of the material tensile yield strength. The angular deflection of the beam subjected to per bending is beta equals ml divided by EI. And this equation can be applied directly to the helical and torsion of springs. For springs used with a great many terms, such as the spiral springs used to power clocks and toys, and the helical springs used to counterbalance garage overhead doors and roll up the window shades. The angular deflection can be several complete turns. Long helical springs with many turns usually have the center rod for support. Friction with the center rod and the friction between adjacent spring coils must sometimes be considered. Spiral springs are usually made of thin rectangular wire. Square or rectangular wire is almost more efficient for use in helical torsion springs, but round wire is often used in non-critical applications because it is more available and costs less. Chapter 12.12 Miscellaneous Springs. The variety of possible spring types and designs is limited to only by the ingenuity and imagination of the engineer. Novel designs are regularly submitted to the patent office. Although space does not permit a detailed treatment of additional types here, there are at least 5 other kinds of springs that should be mentioned. For more information, see 124. Spring washers are made in tremendous variety. 6 representative types are shown in figure 12.31. Belleville washers, patented in France by Julien Belleville in 1867, and also known as cone disc springs, are commonly used for carrying large loads with small deflections. Varying the ratio of cone height to washer thickness gives a constant spring rate of various progressively diminishing spring rates, which can become negative. Multiple of identical washers are used in combinations to obtain the desired characteristics, as shown in figure 12.32. Volute springs, illustrated in figure 12.33, are wound from relatively thin strips of metal, with each turn telescoping inside the preceding one. They have more lateral stability than helical compression springs, and the rubbing of adjacent turns provides damping. Garter springs are merely helical springs with ends connected to form a circle. They are commonly used in oil seals, where they exert radial forces to hold the sealing member firmly against the shaft. Other uses include piston ring expanders and small motor belts. Wire forms include a variety of spring members made by bending spring wire into various shapes. Wire forms have replaced helical compression springs in many bed springs, mattresses, and furniture applications. One advantage is that they can be formed flat for minimum thickness in the seat of the car or piece of furniture. Constant force springs, a form originally patented and introduced under the name Neg-Ador, are shown in figure 12.34. They consist of rolls of pre-stressed strip that exist a nearly constant restraining force to resist uncoiling. The strip has a natural or load-free radius of curvature about 10 to 20% smaller than the radius of the drum. Features include long extension capability and virtual absence of the intercoil friction. Figure 12.34b shows a form used with the electric motor brushes. Window sash counterbalance springs are another application. The constant spring motors in figure 12.34c drives mechanisms for timers, movie cameras, cable retractors, and so on. A lot of problems. Maybe I'll do some of them. Maybe not. Who knows? Okay, chapter 13. Lubrication and sliding bearings. Types of lubricants. The word bearing, applied to machine or structure, refers to the contacting surfaces through which a load is transmitted. When relative motion occurs between the surfaces, it is desirable to minimize friction and wear. Any interposed substance that reduces friction and wear is a lubricant. Lubricants are usually a liquid, but can be a solid such as graphite, TFE, or molybdenum disulfide, or a gas such as pressurized air. Liquid lubricants that are oils are characterized by viscosity. but other properties are also important. Oil lubricants have the name designating these properties. Modern oil usually contain one or more additives designed to cause the oil to flow at lower temperatures. The pour point depressants have less variation of viscosity with temperature. The viscosity index improvers resist foaming when agitated by high-speed machinery. The defoamants resist oxidation at high temperatures. The oxidation inhibitors prevent corrosion of metal surfaces. The corrosion inhibitors minimize the formation of engine deposits and reduce the rate at which they deposit on metal surfaces. The detergents and dispersants and reduce friction and wear when full lubricating films cannot be maintained. The anti-wear additives. Greases are liquids lubricants that have been thickened in order to provide properties not available in the liquid lubricant alone. Greases are usually used where the lubricant is required to stay in position, particularly when frequent lubrication is difficult or costly. Often by remaining in place to provide lubrication, grease also serves to prevent harmful contaminants from entering between the bearing surfaces. Unlike oils, greases cannot circulate and thereby serve a cooling and cleaning function. Except for this, greases are expected to accomplish all functions of fluid lubricants. A detailed discussion of the lubricants is contained in 13 and 14. Chapter 13.2 Types of sliding bearings. Sliding bearings require direct sliding of the load carrying member on its support, as distinguished from rolling element bearings where balls or rollers are interposed between the sliding surfaces. The site machinedesign.com presents general information for sliding bearings, rolling element bearings, and lubrication. Sliding bearings are of two types: journal or sleeve bearings, which are cylindrical and support radial loads, and thrust bearings, which are generally flat and, in the case of rotating shaft, supports loads in the direction of the shaft axis. Figure 13.1 shows a crankshaft supported in a housing by two main bearings, each consisting of a cylindrical sleeve portion plus a flanged end that serves as a thrust bearing. The cylindrical portions of the shaft in contact with the bearings are called journals. The flat portion of the bearing against the thrust bearings are called thrust surfaces. The bearings themselves could be integral with the housing or crankcase, but are usually thin shells that can be easily replaced that provide bearing surfaces of an appropriate material, such as a babbitt or bronze. When the radial load on the bearing is always in one direction, as the rail freight car axle bearings, which support the weight of the car, the bearing surface needs to extend only part way around the periphery, usually 60 degrees to 180 degrees, thereby providing a partial bearing. In this book, only the more common 360 degrees of full bearings will be considered. When assembly and disassembly operations do not require the bearing be split, the bearing insert can be made into a one-piece cylindrical shell that is pressed into a hole in the housing. This bearing insert is also known as a bushing. Chapter 13.3 Types of lubrication. Lubrication is commonly classified according to the degree with which the lubricant separates the sliding surfaces. Figure 13.2 illustrates three basic cases. In hydrodynamic lubrication, the surfaces are completely separated by the lubricant film. Man. The load tending to bring surfaces together is supported entirely by fluid pressure generated by relative motion of the surfaces. Surface wear does not occur, and friction losses originate only within the lubricant film. Typical film thicknesses are at the thinnest point, designated by H0, are 0.008 to 0.020 mm. Typical values of coefficient of the friction F are 0.002 to 0.010. In mixed film lubrication, The surface peaks are intermittently in contact, and there is partial hydrodynamic support. With proper design, surface wear can be mild. So coefficients of friction commonly range from 0.004 to 0.10. In boundary lubrication, surface contact is continuous and extensive, but the lubricant is continuously smeared over the surfaces and provides a continuously renewed absorbed surface that reduces friction and wear. Typical values of F are 0.05 to 0.20. The most desirable type of lubrication is obviously hydrodynamic, and this is treated in more detail beginning with the next section. Mixed film and boundary lubrication are discussed further in section 13.14. Complete surface separation can also be achieved by hydrostatic lubrication. A highly pressurized fluid such as air, oil, or water is introduced into the load-bearing area. Since the fluid is pressurized by external means, full surface separation can be obtained whether or not there is relative motion between the surfaces. The principal advantage is extremely low friction at all times, including during starting and low-speed operation. Disadvantages are the cost, complication, and bulk of the external source of fluid pressurization. Hydrostatic lubrication is used only for specialized applications. Additional information is given in 11. Chapter 13.4. Basic concepts of hydrodynamic lubrication. Figure 13.33a shows a loaded journal bearing at rest. The bearing clearance space is filled with oil, but load W has squeezed out the oil at the bottom. Slow clockwise rotation of the shaft will cause it to roll to the right, as in figure 13b. Continuous slow rotation would cause the shaft to stay in this position as it tried to climb the wall of the bearing surface. The result would be boundary lubrication. If the shaft rotating speed is progressively increased, more and more oil adhering to the journal surface tries to come in the contact zone until finally enough pressure is built up just ahead of the contact zone to float the shaft, shown in figure 13.3c. When this happens, the high pressure of converging oil flow to the right of the minimum film thickness position moves the shaft slightly to the left of the center. Under suitable conditions, equilibrium is established with full separation of the journal and bearing surfaces. This constitutes hydrodynamic lubrication, also known as the full film or thick film lubrication. The equilibrium eccentricity of the journal and the bearing is dimension E, shown in figures 13.3c. Figure 13.4 illustrates the influence of three basic parameters on type of lubrication and resulting coefficient of friction F. Viscosity: the higher the viscosity, the lower the rotating speed needed to float the journal at a given load. Increases in the viscosity beyond that necessary to establish full film or hydrodynamic lubrication to produce more bearing friction by increasing the forces needed to shear the oil film. Rotating speed in revolutions per second squared. The higher the rotating speed, the lower the viscosity needed to float the journal at a given load. Once hydrodynamic lubrication is achieved, further increases in rotating speed produce more bearing friction by increasing the time rate at which work is done in sharing the oil film. Bearing unit load, P, defined as load W divided by the bearing projected area, which is journal diameter D times the bearing length L. The smaller the bearing unit load, the lower the rotating speed and the viscosity needed to float the journal. But further reductions in the bearing load do not produce the corresponding reductions in the bearing friction drag force. Thus, the bearing coefficient of friction, which is the ratio of the friction drag force to the radial load W, increases. Numerical values for the curve in figure 13.4 depends on the details of particular bearing design. For example, the smoother the surfaces, the thinner the oil film necessary to complete separation of surface asperities, and therefore the lower the values of mu times n divided by p corresponding to point A. The clearance or fit of the journal and the bearing has the an important influence. This is to be expected when one considers the mechanism for building up hydrodynamic fluid pressure to support the shaft requires the journal run eccentrically in the bearing. Note that the achievement of hydrodynamic lubrication requires three things. 1. Relative motion of the surfaces to be separated. 2. Wedging action as provided by the shaft eccentricity. 3. The presence of a suitable fluid. The sport of water skiing provides an interesting analogy to hydrodynamic bearing lubrication, where three factors for achieving it are provided by forward speed of the skier, the wedge formed by the ski surfaces, and the presence of the water. Carrying this analogy a step further, note that mu times n divided by p curve of figure 13.4 is applicable to this case as well. For example, if a person tries to ski on a bare feet, the unit load p becomes very high. For the necessary mu times n divided by p values to be maintained, the product of viscosity and speed must be made correspondingly high. Filling the lake with more viscous fluid would help, but the more practical solution is to increase speed. With the understanding of hydrodynamic lubrication developed this far, the reader can appreciate why journal bearings have proved very, very successful as crankshaft bearings in modern engines, and why they are not very satisfactory, and have been largely replaced by roller bearings for supporting rail car axle shafts. An engine crankshaft turns slowly only when being cranked, and then bearing loads are small because there are no combustion loads. As soon as the engine starts, combustion adds greatly to the bearing loads, but the rotating speed increases sufficiently to establish hydrodynamic lubrication despite the higher loading. Furthermore, peak combustion loads are of momentary duration, and the inertial and transient squeeze film effects prevent the oil film from being squeezed as thinly as it would be if the peak load were constant. On the other hand, rail car axle bearings must support the full weight of the car when stationary or moving slowly. A common occurrence when the freight trains used journal bearings was that two locomotives were required to start a train that could easily be pulled by a single locomotive on reaching sufficient speed to establish hydrodynamic lubrication in the bearings. Chapter 13.5 Viscosity. Figure 13.5 illustrates the analogy between viscosity, mu, of a fluid, also called dynamic viscosity and absolute viscosity, and shear modulus of elasticity, g, of a solid. Figure 13.5a shows a rubber bushing bonded between a fixed shaft and an outer housing. Application of a torque T to the housing subjects an element of rubber bushing to the fixed displacement as shown as figure 13.5b. If the material between the housing and concentric shaft is Newtonian fluid, equilibrium of an element involves a fixed velocity as shown in figure 13.5c. This follows from Newton's law of viscous flow, which implies a linear velocity gradient across the thin lubricant film with molecular fluids layers adjacent to the separated surfaces having the same velocities as the surfaces. From figure 13.5c, the equation for absolute viscosity can be written as mu equals F times H divided by A times U. The unit viscosity in the English system is pound-second per square inch or rain. In SI units, viscosity is expressed as Newton seconds per square meter or Pascal seconds. The conversion factor between the two is the same for the stress. The rain and Pascal seconds are such large units that microrain, mu rain, and millipascal second, MPa times S, are more commonly used. The larger standard metric unit for viscosity, still widely found in the literature, is the poise. Conveniently, 1 centipoid is equal to 1 millipascal second. I did not know that. Did you know that? Okay. Fluid viscosities can be measured in several ways, including the use of apparatus patterned after figure 13.5. Alternatively, liquid viscosities are sometimes determined by measuring the time required for a given quantity of liquid to flow by gravity through a precision opening. In the case of lubricating oils, an instrument used is the Seibolt Universal Viscometer, and the viscosity measurements are designated as Seibolt seconds, or by any of the abbreviations SUS, Seibolt Universal Seconds, SSU, Seibolt Seconds Universal, and SUV, Seibolt Universal Viscosity. A moment's reflection reveals that these measurements are not true viscosity, since the intensity of the Earth's gravitational pull on the liquid is influenced by its mass density. Thus, a liquid of high mass density flows through the viscometer more quickly than does the less dense liquid of the same absolute viscosity. The viscosity measured by a Seibolt type viscometer is known as kinematic viscosity, defined in the absolute viscosity divided by mass density. That's a new Greek letter. Upsilon. Kinematic viscosity equals absolute viscosity divided by mass density. Unit lengths are length squared divided by time as cm squared divided by s, which is named the Stokes, abbreviated ST. Absolute viscosities can be obtained by the Seibolt viscometer measurements by these two equations, where P is the mass density in grams per cubic centimeter. For petroleum oils, the mass density at 60 degrees Fahrenheit is approximately 0.89 grams divided by cm cubed. At other temperatures, the mass density is rho equals 0.89 minus 0.00063, where rho has units of grams per cubic centimeter. The Society of Automotive Engineers classify oils according to viscosity. Viscosity temperature curves for a typical SAE numbered oils are given in figure 13.6. A particular oil may deviate significantly from these curves, for the SAE specifications define a continuous series of viscosity bands. For example, an SAE 30 oil may be only trifle more viscous than the thickest SAE 20, or a trifle less viscous than the thinnest SAE 40 oil. Furthermore, each viscosity band is specified at only one temperature. SAE 20, 30, 40, 50 are specified at 100 Celsius, whereas SAE 5W, 10W, and 20W are specified at -18 C. Multi-grade oils must conform to a viscosity of specific at both temperatures. For example, an SAE 10W minus 40 oil must satisfy the 10W viscosity requirement at -18 Celsius, and the SAE 40 requirement at 100 degrees Celsius. Industrial fluid lubricants are commonly specified in terms of international standards, which appear as ASTM D2422, American National Standard Z11.232, ISO Standard 3448, and others. The various viscosity grades are designated as ISO VG, followed by a number equal to the nominal kinematic viscosity at 40 degrees Celsius. 18 grades are specified, with kinematic viscosities at 40 degrees Celsius of 2, 3, 5, 7, 10, 15, 22, 32, 46, 68, 100, 150, 220, 320, 460, 680, 1000, and 1500 CST parentheses mm squared divided by s. Grease is a non-Newtonian material that does not begin to flow until a shear stress exceeding a yield point is applied. With higher shear stresses, viscous flow occurs when the apparent viscosity decreasing with increasing shear rates. Apparent viscosity must always be reported at a specified temperature and flow rate. Chapter 13.6 Temperature and pressure effects on viscosity. Multigrade oils as SAE 10W40 have a less variation of the viscosity with temperature than straight run petroleum oils that have single grade designation. The measure of variation in viscosity with temperature is the viscosity index. The first generally used viscosity index scale was proposed in 1929 by Dean and Davis. At the time, the least change of viscosity with temperature occurred in convenient refined Pennsylvania crude oils, and the greatest change occurred in oils refined from the Gulf Coast crudes. Pennsylvania oils were therefore assigned to VI value of 100 and the Gulf Coast oils a value of 0. Other oils were rated intermediately. A contemporary basis of viscosity index ratings given in ANSI that divide by ASTM specification D2270. Non-petroleum based lubricants have widely varying viscosity indices. Silicone oils, for example, have relatively little variation of viscosity with temperature, thus their viscosity indices substantially exceed the 100 of the Dean and Davis scale. The viscosity index of petroleum oils can be increased as in the production of multigrade oils by the use of viscosity index improvers. All lubricating oils experience an increase in viscosity with pressure. Since this effect is usually significant only at pressures higher than those encountered in sliding bearings, it will not be dealt with here. This effect is important. However, in elastohydrodynamic lubrication. Chapter 13.7 Petrov's equation for bearing friction. The original analysis of the viscous friction drag. Pause. In what is now known as the hydrodynamic bearing is credited to Petrov and was published in 1883. Hence, it applies to the simplified ideal case of no eccentricity between bearing and journal, hence no wedging action and no ability of the oil film to support a load, and no lubricant flow in the axial direction. With the reference to figure 13.5c, an expression for viscous friction drag torque is derived by considering the entire cylindrical oil film as the liquid block acted upon by force F. Solving the equation given in the figure F gives F equals mu A U divided by H. A small radial load W is applied to the shaft. The frictional drag force can be considered equal to the product F times W, with friction torque expressed as this equation, where P is the radial load, the input per unit of the projected bearing area. The imposition of load W, of course, will cause the shaft to become somewhat eccentric in the bearing. If the effect on this equation B can be considered negligible, equations B and C can be equated to give F equals 2 pi squared mu n times n divided by P, R divided by C. This is well-known Petrov equation. It provides a quick and simple means of obtaining reasonable estimates of coefficients of friction of lightly loaded bearings. More refined procedures will be presented in section 13.9. Note that Petrov's equation identifies two very important bearing parameters. The significance of mu n divided by p was discussed in section 13.4. The ratio of R divided by C on the order of 500 to 1000 and is the inverse of the clearance ratio. The importance will become increasingly evident with the study of section 13.8. Chapter 13.8 Hydrodynamic Lubrication Theory. The theoretical analysis of hydrodynamic lubrication is traced back to Osborne Reynolds' study of the laboratory investigation of railroad bearings in England by Beauchamp Tower during the early 1880s. The oil hole was drilled to test the effect of adding an oiler at this point. Tower was surprised to discover that when the test device was operated without the oiler installed, oil flowed out of the hole. He tried to block the flow by pounding cork and wooden stoppers into the hole, but the hydrodynamic pressure forced them out. At this point, Tower connected a pressure gauge to the oil hole and subsequently made experimental measurements of the oil film pressures at various locations. He then discovered that the summation of local hydrodynamic pressure times differential projected bearing area was equal to the load supported to the bearing. Reynolds' theoretical analysis led to this fundamental equation of hydrodynamic lubrication. The following derivation of the Reynolds equation applies to one-dimensional flow between flat plates. This analysis can also be applied to journal bearings because the journal radius is so large in comparison to the oil film thickness. The assumed one-dimensional flow amounts to the neglecting bearings side leakage and is approximately valid for bearings with L divided by D ratios greater than about 1.5. The derivation begins with the equation for equilibrium of forces in the x direction acting on the fluid element as shown in 13.11. In equation 13.1, the quantity F divided by A represents a shear stress T on the top of the block. In figure 13.11, the block is shrunk in differential element of height dy, velocity u, and top to bottom velocity gradient du. By making these substitutions in equation 13.1 gives r equals to mu parentheses du divided by dy, except in this case u varies with both x and y, so the partial derivative is used. Tau equals mu times derivative of u divided by y, derivative of y. Similarly, tau varies with both x and y, so the partial derivative tau y is used in figure 13.11 and equation A pressure. Pressure, on the other hand, is assumed not to vary in the y and z directions, so the total derivative dp divided by dx is used. Design charts for hydrodynamic bearings. Solutions of EQ 13.9 were first developed in the first decade of the 20th century. Although theoretically applicable to bearings that are infinitely long, these solutions give reasonably good results with bearings L divided by D ratios about 1.5. At the other extreme, the Ockwerk short bearing solution based on EQ 13.11 is quite accurate for bearings of the L divided by D ratios up to 0.25 and is often used to provide reasonable approximations for bearings in the commonly encountered range of L divided by D between 0.25 and 0.75. Computerized solutions of the full Reynolds equation have been reduced to chart form by Raimondi and Boyd. These provide accurate solutions for bearings of all proportions. Charts using the same approach are included in figures 13.13 through 13.19 for full journal bearings with several L divided by D ratios. The original Raimondi and Boyd charts also apply to partial bearings and to thrust bearings. Several quantities given in the charts used here are illustrated in figure 13.20. The journal bearing charts give plots dimensionless bearing parameters as functions of the dimensionless bearing characteristic number of Sommerfeld variable S, where bearing characteristic number S R divided by C parentheses squared mu times n divided by p. Note that S is the product of previously discussed in the parameter mu times n divided by p to the 6th power and the square of the clearance ratio R divided by C. The S scale on the charts is logarithmic except for a linear portion between 0 and 0.01. Give me a break. My tongue is dry. Okay. That's okay. Let's go. Figures 13.18 and 13.19 assume that lubricant is supplied to the bearing at atmospheric pressure, and that the influence on flow rate of any oil holes or grooves is negligible. Viscosity is assumed to be constant and to correspond to the average temperature of the oil flowing to and from the bearing. Values of any bearing performance variables plotted in figures 13.14 through 13.19 can be determined for any ratio L divided by D greater than 1/4 by using the following interpolation equation given by Raimondi and Boyle, where y is the desired performance variable for any L divided by D ratio greater than 1/4, and y infinity, y1, y1/2, and y1/4 are the values of the variable for bearings having L divided by D ratios of infinity, 1, 1/2, and 1/4 respectively. Chapter 13.10 Lubricant Supply. The preceding hydrodynamic analysis assumes that oil is available to flow into the bearing at least as fast as it leaks out at the ends. The principal methods for supplying this oil are briefly described below. See for and others for further information. Oil ring. The oil ring shown in figure 13.22 is usually 1.5 to 2 times the diameter of the journal from which it hangs loosely. As the shaft rotates, the ring brings oil to the top of the journal. Note that the bearing sleeve must be slotted at the top to permit the ring to bear directly on the journal. If the applied bearing load acts substantially downward, this removal of the part of the bearing area at the top will not be harmful. Experience has shown the ring oilers to be very effective. Sometimes a chain is substituted for the ring. Oil collar. A somewhat similar arrangement utilizes a rigid collar attached to the shaft that dips into the oil reservoir at the bottom. The collar carries the oil to the top, where it is thrown off into a small upper reservoir on each side of the collar. From there, it flows by gravity through holes to the bearing surface. Splash. In some machines, oil splashed by rapidly moving parts can be channeled to small reservoirs above bearings. In addition, small oil scoops on rotating parts can dip into the main oil sump or reservoir and thereby pick up oil. Okay, good. That flows into the bearings. Some readers will recognize this as the method of lubrication used with early automobile engines. Wow, it sometimes lags and I can't really do anything about that, but okay. Oil bath. The term oil bath usually refers to oil being supplied by the virtue of partially submerging the journal in oil reservoir, as is the railroad partially bearing shown in figure 13.10. Care must be taken with oil bath lubrication to avoid generating excessive turbulence and churning of a substantial volume of oil, thereby causing excessive viscous friction losses and possible foaming of the lubricant. Oil holes and grooves. Figure 13.23 shows the axial groove used to distribute oil in the axial direction. Oil enters the groove through an oil hole and flows either by gravity or under pressure. In general, such grooves should not be cut in the load carrying area because the hydrodynamic pressure drops to nearly zero at the grooves. This point is illustrated in figure 13.24, where the circumferential groove serves to divide the bearings into two halves, each having an L divided by D ratio, a little less than half that of the ungrooved bearing. A development of grooved patterns for adequately distributing oil over the full bearing area without objectionably disturbing the hydrodynamic pressure distribution can be a major problem in some applications. Oil pump. The most positive means of supplying oil is by an oil pump. Figure 13.25 shows the pressure-fed lubrication system of a piston-type engine or compressor. Oil supplied by the oil pumps fills the circumferential grooves on the main bearings. Holes drilled on the crankshaft carry oil from these grooves by connecting rod bearings. Circumferential grooves in the connecting rod bearings connect with rifle drilled holes and connecting rods that carry lubricant to the wrist pins. In most automotive engines, the rifle drilled connecting to the rod passages are eliminated and the wrist pins are splash lubricated. This is less costly and has proved entirely effective. Chapter 13.11 Heat dissipation and equilibrium of the oil film temperature. Under equilibrium conditions, at the rate at which heat is generated within a bearing is equal to the rate at which heat is carried away. It is essential that the oil film temperature at which this balance occurs to be satisfactory. Temperatures in the range of 71 degrees Celsius are commonly used. Temperatures above 93 to 121 Celsius degrees are generally unsatisfactory because of the possible deterioration of petroleum-based lubricants and damage to some common bearing materials. The friction power absorbed by a bearing is readily computed to the friction torque and shaft RPM. The portion of this power carried away by the oil is the product of the flow rate, QS, the oil temperature rise, and volumetric specific heat, CP. For petroleum oils at normal bearing operating temperatures, approximate values are CP equals 1.36 MP times A divided by Celsius, 110 pounds divided by inches squared Fahrenheit. Oil temperatures rise can also be estimated by the special charts devised by Raimondi and Boyd. The oil temperature at thermal equilibrium depends on the effectiveness with which heat is transferred on the bath to the outside of the environment. For its self-contained bearings, as low as using an oil ring, collar, or bath, the calculation of average oil film temperature is usually a rough ballpark procedure at best. And the experimental data under actual operating conditions must be obtained for applications close to the being critical with respect to overheating. For a rough estimate, we apply the equation H equals CATO minus TA. Chapter 13.12 Bearing materials. During thick film lubrication, any material with sufficient compressive strength and a smooth surface would be an adequate bearing material. Steel, for example, would be fine, but during startup and shutdown, these bearings experience thin film lubrication, and the journal will be damaged unless the bearing material resists seizing and welding with the journal material. Furthermore, any foreign particles larger than H0 that are present in the oil will damage the journal surface unless they can become embedded in a relatively soft bearing material. Thus, the following are important properties of bearing materials. Mechanical properties: conformability and deformability to relieve local high pressures caused by misalignment and shaft deflection. Embeddability or indentation softness to permit small foreign particles to become safely embedded in material, thus protecting the shaft. And low shear strength for easy smoothing of the surface asperities. At the same time, compressive strength and fatigue strength sufficient for supporting the load and enduring the repeated flexing of that accompanies cyclical loading. And bearing materials should have these properties at the operating temperatures of the machine. Thermal properties: heat conductivity to conduct heat away from the local points of metal-to-metal contact during startup and from the lubricant film during normal operation. Thermal coefficient of expansion not too different from the materials of the bearing housing and journal. Metallurgical properties: compatibility with the journal material for resistance to scoring, welding, and seizing. Chemical properties: corrosion resistance to acids that may form during lubricant oxidation and to outside contamination. The most common bearing materials are Babbitt's, both tin base as 89% SN, 8% PB, 3% CU, and lead base 75% PB, 15% SB, 10% SN, and copper alloys, primarily copper lead leaded. Bronze, tin bronze, and aluminum bronze. Aluminum and silver are also used fairly extensively. These Babbitt's are excelled in conformability and embeddability, but they have relatively low compressive and fatigue strength, particularly above 77 degrees Celsius. Babbitt's can seldom be used above about 121 Celsius. The bearing's metal surface layer is usually applied to thin steel backing shell, with Babbitt bearings The shell flexural deformation is independent of the thickness of the babbitt lining. Fatigue strength is greatest when the babbitt lining is very thin, on the order of 0.5 mm, in automotive main and connecting of the rod bearings, with the latter having a far greater fatigue resistance. Sometimes a thin babbitt overlay is added to the bearings made of other materials in order to combine the greater load carrying capacity of other material with the more desirable surface characteristics of the babbitt. Rubber and other elastomers make a good bearing material for applications like ship propeller shafts that run in water. These bearings usually fluted and are retained within a metal shell. The water flow through the bearing allows sand and grit to be flushed out with minimum damage. Chapter 13.13 Hydrodynamic Bearing Design. Sample problem 13.3 in section 13.9 illustrates analysis given by blah blah blah. Okay, unit loading. 13.2 summarizes representative values in common use. Note the dramatic influence of squeeze film phenomenon mentioned in the conclusion of section 13.9. Since the peak loads applied to engine bearings are of only momentary duration, the resulting bearing pressures can be of the order of 10 times the values in applications where loads are constant. Bearing L divided by D ratios of 0.25 and to 0.75 are most commonly used now, with older machinery having ratios averaging closer to unity. Greater ratios mean less end leakage and a reduced oil flow requirement, hence greater oil temperature rises. Short bearings are less susceptible to undesirable edge loading caused by shaft deflection and misalignment. Often shaft diameter is determined by strength and deflection requirements, and then bearing length is determined in order to provide adequate bearing capacity. Acceptable values of H0. The minimum acceptable oil film thickness, H0, depends on surface finishes. Various empirical recommendations are found in literature. For example, Trumpler suggests the relationship H0 is greater than 0.0002 and plus 0.00004. 0.00004. This equation to be used in the appropriate safety factor applied to the load. Moreover, applies to only bearings that have a finely ground journal surface whose peak to valley roughness does not exceed 0.005 mm or 0.0002 inches, that have good standards of geometric accuracy, circumferential out of roundness, axial taper, and waviness, both circumferential and axial, and that have good standards of oil cleanliness. For bearings subjected to rapidly fluctuating loads, simplified calculations based on assumption that peak loads remain constant may give calculated values of H0 of the order of 1/3 of actual values. This must be taken into account when using empirical criteria such as equation 13.15. More realistic calculations for such bearings take the squeeze film phenomenon into account and are beyond the scope of this book. Clearance ratios C divided by R or 2C divided by D. For journals 25 to 150 in diameter, the C divided by R ratio is usually of the order of 0.001, particularly the precision bearings. For less precise bearings, this ratio tends to be higher, up about 0.002 for general machinery bearings and 0.004 for rough service machinery in any specific design. The clearance ratio has a range of values depending on the tolerances assigned to the journal and bearing diameter. The following list is a list of important factors to be taken into account when designing and bearing for hydrodynamic lubrication. The minimum oil film thickness must be sufficient to ensure thick film lubrication. Use 13.15 as a guide to take into account surface finish and load fluctuation. Friction should be as low as possible, consistent with adequate oil film thickness. Try to keep the optimum zone of figure 13.13. Be sure the adequate supply of clean and sufficiently cooled oil is always available at the bearing inlet. This may be required forced feeding, special cooling provisions, or both. Be sure the maximum oil temperature is acceptable. Be sure the oil is emitted to bearing gets distributed over its full length. This may require grooves in the bearing. If so, they should be kept away from highly loaded areas. Select a suitable bearing material to provide sufficient strength and operating temperatures, sufficient conformability and bendability, and adequate corrosion resistance. Check the overall design for a shaft misalignment and deflection. If these are excessive, even a properly designed bearing will give trouble. Check the bearing loads for elapsed times during the startup and shutdown. Bearing pressures during these periods should preferably be under 2 MPa or 300 psi. If there are extended time periods of low speed operations, thin film lubrication requirements must be considered. Be sure the design is satisfactory for all reasonably anticipated combinations of clearance and oil viscosity. The operating clearance will be influenced by thermal expansion and by eventual wear. Oil temperature, therefore viscosity, is influenced by the thermal factors and by possible changes in oil with time. Furthermore, the user may put in the lighter or heavier grade of oil than once specified. Chapter 13.14 Boundary and Mixed Film Lubrication. The conceptual representation of boundary and mixed film lubrication was given in figure 13.2. The representation of F versus mu n divided by P curve was shown in figure 13.4. Even with a boundary lubrication of extremely smooth surfaces, actual contact extends over a small fraction of the total area. This means that the highly localized areas of contact, there are very high pressures and very high instantaneous temperatures. Were this to occur on unprotected metal surfaces, friction would be considerable. And the surface would usually be rapidly destroyed. Fortunately, even in ordinary atmosphere, oxide and other protective films on metal surfaces, introducing grease, oil, graphite, molybdenum disulfide, and others, allows them to form surface films that provide some lubrication. These films are relatively weak in shear, hence the films on surface peaks and asperities tend to shear off, with new film layers forming as old ones are worn off. With mixed film lubrication, only part of the load is carried by the film-coated solid peaks, the balance carried hydrodynamically. Continuing research efforts are directed towards the development of new lubricants and new combinations of surface materials, and lubricants giving the improved resistance to adhesive wear and reduced friction. Boundary lubrication is often improved by modifying the bearing. Common examples are sintered metal bearings. These are made by compressing powdered metal into desired shape and then heating at a temperature between the melting points of the two metals. The resulting porous matrix permits the bearing to soak up oil like a sponge before it is put into service. In use, the entrapped oil flows to the surface in response to heat and pressure, then flows back into the porous matrix when the machine is shut down. Another example of the indentation of the surface of a solid bearing to give a hammered effect, with some surface indentations providing a storage space for solid or semi-solid lubricants. Some bearing materials such as graphite and various plastics are said to be self-lubricating because of their naturally low coefficients of friction with smooth metal surfaces. Plastics such as nylon and TFE, with and without various additives and fillers, are widely used for moderate loads and speeds. Two limitations of plastic bearings should be noted. Cold flow occurs at heavy loads, and they do tend to run hotter than metal bearings that generate the same friction of heat because of the low thermal conductivities. These disadvantages are less pronounced when the plastic bearing material is the form of bonded coating. Although boundary lubrication is usually thought of in connection with bearings, the same phenomenon occurs with the relative motion of screw threads, meshing gear teeth, sliding of a piston in a cylinder, and with sliding surfaces of other machine components. Porous metal bearings are usually designed on the basis of an allowable product of pressure times velocity, or PV factor, for a given coefficient of friction. This factor is proportional to the frictional heat generated per unit of a bearing area. A maximum PV value of 50,000 psi times FPS is commonly applied to the porous metal bearings for long-term operation at high PV or for high temperatures. Provision should be made for additional oil. Oil can be applied to any surfaces as it will be drawn to the interior by capillary action. A grease reservoir next to the bearing can also be effective. Where long life is desired with no provision for adding lubricant, the PV value should be reduced by at least half. Table 13.4 gives more detailed recommendation except for the first three bearing materials listed in the table. Hardened and ground steel shafts should be used to resist shaft wear. The tabulated values are sometimes moderately exceed, but with a sacrifice in service life. Chapter 13.15 Thrust bearings. All rotating shafts need to be positioned axially. For example, the crankshaft shown in 13.1 is positioned axially in the flanked thrust surfaces where the integral with the main bearings that carry the radial loads. Sometimes the thrust load is carried by separate flat thrust washers. These flat bearing surfaces may not permit the wedging action required for the hydrodynamic lubrication, but if the loads are light, boundary or mixed film lubrication is adequate when the shaft axial loads are great. Hydrodynamic thrust bearings can be provided. Oil supplied to the inside diameter of the rotating collar or runner flows outward by centrifugal force through the bearing interface. As the oil is dragged circumferentially through the bearing, it experiences a wedging action, which is due to the tapered pads on the stationary member. This is directly analogous to the wedging action produced by the eccentricity of a journal bearing. As in figure 13.28, the fixed pads may have a fixed taper angle, or the pads may be pivoted and allowed to assume their own optimum tilt angle, or they may have partially constrained the permitted a small variation in tilt angle. If the pads have a fixed taper, it is obviously then that a load can be supported by hydrodynamically for one direction of rotation. Raimondi and Boyd charts are also available for thrust and bearing design. Okay guys, I'm gonna stop right here on page 557. We're nearing the 12-hour mark, and YouTube only allows 12-hour videos, so I do want to include a little short reflection on this book so far and what I think about it. But if you guys want me to read and finish this book, then I'll start right back here on page 557, right here on the dot, and I'll just set the timer to I'll restart the timer and I'll just add the 2. It doesn't matter, but yeah, here, let's get right to the here. Okay. Well, I'm gonna stop the recording now, but let's get right into the review. So, without matter of ado, what's up, guys? My name's Harvard, back at it with you. to go over this textbook that I've just read so far, this engineering textbook. So there are 5 things that I want to go over. Number 1 is context. For an engineering book, it sure goes over the structures, material defect a lot, including torsion effect and friction failure. Instead of the great, interesting ideas of designs such as the great forklift, there are many ways to design a forklift, but this book failed to go into a lot of them and how you even create a forklift. I guess designs are more often than not influenced by safety features in the real world, but I would like to get into the creative design because there are possibilities that probably have not been discovered yet, but I know a lot of man hours goes into making these things, so I'm not the best on the subject. 2. Interpretation. When I read and recited the words, whenever I came across a word that was familiar, maybe 1 in 10 words, these words would be popping up in my head like image to text translations, as it pulled out images from my history. Like maybe I went bike riding one day and I read the word bicycle. I would picture that bicycle in my head. I found that really strange and very interesting. Okay, 3. Study. The Pomodoro effect really freaking works. It was amazing to realize how well it worked. At the 25-minute mark, I studied fade away in my head and I couldn't really think. But after the 25 minutes were over and I took that 5-minute break, that 5-minute break really refreshed my memory and enabled me to continue on. 4. Huh? I do not know the Greek alphabet. Maybe I should add the Greek alphabet, singing the Greek alphabet right after this, like I sing my ABCs, but we'll see. 5. Pronunciation. I realized as I read the book, some words became more apparent than others, and some words I really couldn't pronounce, but at the end of the day, like, if I read the word more often, practice makes perfect, and some of the words became more easier in a way to read. So that was pretty good on my part, but I don't know about, like, there's so many words in the dictionary and maybe I'll have to read the dictionary one day, but probably not, because you'll probably have to read it like 5 to 10 to 20 times. But well, here's to it. If you want the rest of the book, let me know. Comment in the comments below, and I'll probably read it. If you found this entertaining or useful, let me know. Also, if you sleep to my voice, also let me know. Yeah. Here's the Greek alphabet. Math. Alpha, beta, gamma, delta, epsilon, zeta, eta, theta, iota, kappa, lambda, mu, nu, psi, omicron, pi, rho, sigma, tau, epsilon, phi, chi, psi, omega. A, B, C, D, E, F, G. It doesn't even follow the alphabet. Okay. Alright, that sounded a bit weird, so I'm gonna just say the alphabet backwards. Z, Y, X, W, V, U, T, S, R, U, Q, P, O, N, M, L, K, J, I, H, G, F, E, D, C, B, A. The end. Peace out, guys.